Hi everyone, my name is Hassan and welcome to my course Azure Cloud Design Patterns. If you are a software engineer, pretty much you'd have heard of software design patterns before. And it's simply a reusable solutions to common recurring problems in the software world. And over the last decade, cloud became more and more popular. Like we have these common recurring problems that we needed to create a reusable solutions for them. And this is from where the term cloud design patterns came from. And for consistency, I have created this course with a primary focus on Azure. However, all of these learnings you are going to learn in this course, you could apply them in any other cloud provider, like AWS or Google Cloud. And in this course, we are going to cover more than 25 different cloud design patterns in details. And what you see in front of you now is just some of them. So we are going to cover patterns like Asynchronous Request Response Pattern, Deployment Stamp Pattern, Cache Aside Pattern, and then move into one of my favorite patterns, Geode Pattern, and then Federated Identity, then moving to the gate patterns like GateKeeper, Gateway Aggregation, Gateway Offloading, and how we can use all of these patterns in details. And there is no particular order that you need to go through to watch this course. You can pretty much watch any pattern you would like to straight away without any prerequisites or dependencies. And I've tried as much as possible to follow the same structure for every pattern, starting from the pattern definition and what is the problem that pattern is trying to solve. Then move into the solution, how we can use this pattern to solve a certain problem. Then move into the considerations you need to know when you implement this pattern, and then move into when you should use this pattern and when you shouldn't. You will see this structure across all of the patterns in my course. Very important to mention that this course is hands-off. Like you will not see me demonstrating certain implementations on Azure portal. However, my main focus for this course is to help you understand what are the different problems those design patterns are solving, and how we can implement those patterns in Azure. However, there is no step-by-step demonstration on Azure at all. Having said that, if you are interested in more hands-on courses, you might need to check my Azure API Management course, which is completely hands-on course on Azure API Management. Also, I will make some of these patterns in this course publicly accessible to give you a chance to watch these patterns before you go ahead with this course. That's enough for an introduction for this course. Now let's get started and let's learn Azure Cloud Design Patterns together. Hi everyone, my name is Hassan and in this video we are going to talk about the Gatekeeper Pattern. Gatekeeper Pattern comes under security category of cloud design patterns, and it's all about adding additional layer of security to reduce the attack surface on the backend services. And related pattern to the Gatekeeper Pattern is Valet Key Pattern. Hopefully we are going to make a video about it in future. Now let's go to the examples to help us understand Gatekeeper Pattern better. Let's say that our system is built on microservices architecture, and we have hosted in some Azure serverless components, like Azure App Service, or Functions App, or Logic Apps. All of these are considered to be the application layer of our system. Then we are storing the structured data in SQL database, and the unstructured data in blob storage. Then we will have to have some kind of communication between the application layer and the data layer. Then we will have external clients that want to interact with our system, and obviously they are going to do so by interacting with our services in the application layer. Let's say that this is the URL of the Functions app that the external clients is going to interact with. So far we have done everything correct. We have Functions app that's exposed to external clients through HTTPS. Remember when we said this pattern is about adding additional layer of security that might be required in some situations. Now, let's talk about some of these situations that might require you to add additional layer of security in front of your application layer services. First, the challenge is when the external clients want to compromise our Functions app to have indirect access to the database to manipulate our data. Second challenge, maybe we want to implement OAuth authentication between the application layer services and the external client. Everyone knows that OAuth authentication is the best practice. However, it's out of the scope of this particular function app. The main purpose of this function app is to implement a small business logic and update some data in the database. And if we are going to go ahead and implement OAuth authentication in this particular function app, we are going to add more complexity to our function app. What's more, we might have hundreds of these functions app in our system. Then we will have to go ahead and add OAuth implementation in all of them, which is going to be a huge amount of effort. Finally, let's say that we want to protect our application layer services from public internet accessibility. So we are going to go ahead and add it in internal VNet. Then we will have to build a VPN connection between the external clients and the internal VNet. Although we have secured the application layer services by placing it in an internal VNet, the external clients still able to communicate with the application layer services using their endpoint. And if they succeeded to compromise it, they will have indirect access to our data store. And what we want to do is to protect or not to share the endpoints of the backend functions with the external clients. Those are the different scenarios or challenges that might require you to think about adding additional layer of security in front of your application layer services. Now we have talked about all of these challenges, let's see how can we use the GateKeeper pattern to resolve these problems. Now let's say that we are going to add additional layer of security. And in this case, I am going to add API management. So the external clients are going to send requests to the API management, and then the API management is going to interact with the application layer services. At that point, the external clients will know nothing about the endpoints of the application layer services. All the external clients will be able to know is the URLs that are hosted in the API management. At that point, we have achieved a level of security. By hiding the endpoints of the application layer services behind the API management, we have achieved some level of security to our system that should be appreciated. In addition to other security features that's going to be added by using API management. Most importantly is OAuth authentication. We are able to implement OAuth authentication at the API management level, so we have a consistent experience between the external customer and the API management, and we are assured that we are not duplicating our efforts for having OAuth authentication across all of our Azure functions. So this is the key of the pattern, having additional layer of security in front of the application layer services. So far we have described the pattern at a high level, but I am interested to go a little bit into the implementation of the API management to show you exactly how the API management will help you to secure your application layer services. So this is my Azure API management. As you can see here, it's split into backend and frontend. This is going to be exactly the same if you are using AWS API Gateway. It had the same split into backend and frontend. The backend is going to be linked to the application layer services, and in our example, is going to be linked to the functions app. While the front end will have a new endpoint that's going to be shared with the external customer so they can interact with the API management. At all times, the endpoint of the backend services are going to be hidden from the external clients, and they are never going to be shared with the external consumer. As we talked about the functions app example, let's consider another one. Let's assume that we have implemented a custom web service, and we hosted it in Azure App Service. And then of course, we are going to have a different URL in the API management for the external customers to use so they can access this new app service. But unlike functions app, when we implement a custom web service, API management is going to reveal more information about the backend service to the customer. As you can see here, in the response that the API management is going to send to the customer is going to send the API, the ASP.NET version and the platform, and what's worse, the URL or the endpoint of the backend service. Let's see how can we use the API management to protect this information. What we can do is to implement a policy that's going to delete these particular headers from the response. So the response that the API management is going to send will going to delete these two headers. But we still have the endpoint of the backend service that we still need to handle. And what we can do is to mask URLs in the content. So we ending up sending back to the customer the URL of the API management instead of the endpoint of the backend service. This was a quick overview of the transformation policies in the API management. If you are interested to learn more about it, I will put a link to my video so you can check it. If you know nothing about API management and interested to learn more about it, I will put another link to the API management course I put on YouTube as well. Now let's take it one step further. And let's say that we want to use Application Gateway, sometimes known as WAF, Web Application Firewall, into our solution. Web Application Firewall or the Application Gateway is going to protect our solution against some common security attacks like SQL injection, cross-site scripting, and other attacks. So we are going to make the external customers send their requests to the Application Gateway. And then the Application Gateway is going to route these requests to the API management. Both of them, the API management and the Application Gateway, provides different security lenses. The API management is going to provide the OAuth authentication and different policies we have talked about before, while the Application Gateway protects us against common attacks like SQL injection or cross-site scripting. And if you are interested to learn how you can set up the Application Gateway with the API management, I'm going to put a link to my video so you can review it later. Now you get the idea of this pattern, adding as many security layers as you like to protect your system. This is what the GateKeeper pattern is about. Now we have talked about the design and implementation of this pattern. Now let's talk about some considerations you need to keep in mind when you use this pattern. First of all, you want to make sure that the endpoints for the backend services are protected endpoints. What does it mean? Is that when we introduced the Application Gateway into our solution, you want to make sure that the external clients are not able to go ahead and connect with the API management directly, bypassing this layer that we have added. Same thing, you want to make sure that the external clients are not able to connect with the backend services directly as well. And to achieve this, you need to place these resources in an internal VNet and make sure that they are only accepted traffic from a valid source. So the backend services are going to accept the traffic coming only from the API management. And same thing for the API management is going to accept the traffic only coming from the Application Gateway. Then we have a common security principle that we need to apply the minimum security privilege for our gatekeeper, as well as we shouldn't implement any business logic to our gatekeeper. Then we get to the SSL offloading. SSL offloading means that we have encrypted communication between the external clients and the API management, and at a certain point we do the SSL offloading at the API management to continue the traffic using HTTP only. We do this for some reasons to improve the performance of the internal system communications. However, in some situations, you might have requirements to apply end-to-end encryption for your solution. In this case, you need to do the SSL offloading at the database layer and having all the traffic, external traffic and internal system traffic, all encrypted using HTTPS or SSL. Then we're coming to latency. As you are adding more layers to our solution, you should expect a little bit more latency to the overall performance of your system. And then finally, when we have one API management, we are introducing a single point of failure to our system. And you can overcome this by having multiple instances of your API management, either in the same region or in different regions. Now let's see when you should be using this pattern. When your application handles sensitive information, you want to make sure that you're adding additional layers of security to protect your application layer services. Also, when you have distributed applications that you want to perform request validations separately from the main tasks. As we said before, in this situation here, the API management is going to handle the OAuth authentication as well as different transformation policies, and the application gateway is going to handle the common security defenses against common attacks like SQL injection or cross-site scripting. Both of these has been handled separately, away from the application layer services. Now we are coming to the end of this video. I hope now it's clear for you what the GateKeeper pattern is about, how to design it in your solution, how to implement it in some Azure services, when you should use it, when you shouldn't, and what considerations you need to keep in mind when you use this pattern. I hope you enjoyed this video, and if you have any questions, please put it in the comments below. Thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Gateway Aggregation Pattern. Gateway Aggregation Pattern fits under two categories of cloud design patterns: design and implementation, and operational excellence. As the name suggests, Gateway Aggregation Pattern tries to aggregate multiple individual requests into one single request. Now it's good to mention the related patterns for the Gateway Aggregation Pattern. First of them is Backend-For-Frontends Pattern, and I'm going to put a link for this video if you are interested to review this pattern. Also, we have Gateway Offloading Pattern and Gateway Routing Pattern. Hopefully you are going to make a video about these two patterns in future. Now let's go to the scenarios to help us understand how the Gateway Aggregation Pattern will help us to send one single request instead of multiple individual requests. Let's assume we have three services: Service A, Service B, and Service C. Those services could be built on Azure App Service or Functions app. Then we have the client or consumer application that wants to perform one task that would need to send requests to multiple services, A and B and C. So the clients will have to send a separate request to service A and receive the response back. Same thing with service B and C. And this is the first challenge we have in here. We are putting too much pressure on the client by letting them sending separate requests to multiple services and receive multiple responses, and then they have to aggregate those responses to figure out what is the outcome of that task, whether it's been succeeded or failed or partially succeeded or declined or whatever. And it would be even better if we created an endpoint, so the client will have to send one single request to this endpoint and receive one single response about the outcome of this task. Also, we are allowing the client to get too much into the service architecture of our system. So in order to perform one task, the client has to communicate with three different services. This level of intervention is not required. It would be even better if we have something in between to hide all of these backend services from the client request. The client doesn't need to know all this information about our services at all. Now let's move to the second scenario. Let's assume that our task has been extended, and now it needs to get some data from service D. Then the client has to send a request to service D and consider service D response, along with other services responses, which is going to be a continuous changing process to the client's application. Every time we change something in one task, the client has to update their code to call or communicate with that new service. Now, after we have seen these challenges, let's see how the Gateway Aggregation Pattern will help us to resolve these problems. The solution lies in having one endpoint, our gateway. So the client will have to send the request to one endpoint. And then the gateway is going to split the request and send it to multiple services as required. And then the gateway is going to receive the responses back from different services and aggregate those responses and send one response back to the client. At that point, the client has to know nothing about all of the services that we have in our system. All the client has to know, just the gateway endpoint that he has to send the aggregated request to it. Also, when we extend our task and add service D, then we will have to build a communication between our gateway and service D and consider its response in the aggregation process, and the client will know nothing about service D in the solution. All the client might feel about is maybe adding more input parameters or receiving more data in the response, but at the end the client knows nothing except the endpoint for the gateway, and this is the solution for this problem. It has two lenses: operational excellence, where it's going to make the life easier for the customer. The customer or the client doesn't have to deal with multiple services in order to perform one task. It's a lot of overload for the clients. And also a security lens, because we are hiding our service architecture from the client, because they don't need to know the service architecture of our system. Now let's say that those services are implemented using Azure Functions app. The gateway could be Azure Durable Function. And if you haven't heard about Durable Function before, it's an extension of Azure Function that allows you to write stateful functions in a serverless environment. Now let's have a quick look at Durable Function implementation patterns. First one is fan out, fan in. When you get a single request and then fan it out to multiple Azure Function apps, and then you receive the responses from these different functions and aggregate them to have one output. This implementation pattern works well with the scenario we have talked about before. Also, we have function chaining, when the output of one function is going to be the input of another function and so on. And then you want to have one output at the end. Also, you could use it as an HTTP API or monitoring or home interaction or aggregator. I am not going to jump too much into the details of durable function implementation patterns. It's out of the scope of this video. I just wanted to touch on them really quickly to help you imagine how we can use durable function as an implementation for this pattern. However, I am going to put a link in the description of this video if you are interested to read more about these different implementation patterns for the durable function. Now let's get back to our scenario. And I have put down here the fan out, fan in implementation pattern, where the client is going to send the request to the gateway, and then the gateway is going to fan it out to multiple function apps. And then when the function apps finish the execution and send it back, it's gonna fan it back in to the gateway. So this pattern works well with the scenario that we have talked about. Hopefully this is now clear enough for you. Now let's talk about different considerations you need to keep in mind when using this pattern. You don't need to have any coupling between your gateway and the backend services. Also, to reduce latency, you need to make sure that the gateway is near as possible to the backend services. You don't need to put the gateway in a separate Azure region, or you don't need to put it in the front-end layer very far from the backend services. Try to make them as close as possible to each other, geographically, physically, and logically. As you might expect, it's going to be a single point of failure for our solution, so you need to consider have a containerization or multiple instances for the gateway. Also, it's going to be a performance bottleneck, since it's going to be one gateway to receive all requests from all clients. Then you need to monitor the performance of your gateway very carefully and have a scalability plans in place. You may have done load testing for the backend services separately, and you still have to do load testing for the gateway itself. You need to be very clear how many requests your gateway will be able to take from clients, and whether your scalability plans are effective or not. Also, you need to consider implementing some resiliency patterns like Bulkhead or Retry, and if you are interested, I am going to put a link for Bulkhead video if you are interested to review it. Also consider if it's okay for your gateway to return partial data if one of the services is unavailable for any reason. This is a business decision that you need to make with your stakeholders. Also make sure to use asynchronous I/O. This is to ensure that any delays in the backend services are not going to affect the gateway. Make sure you are using distributed tracing with correlation IDs. Monitor requests and responses between the client and the gateway, between the gateway and the backend services, and all the way back. Also consider return cached data as a failover strategy. Now let's see when you should use this pattern. When the client needs to communicate with multiple backend services to perform one operation. Also when the client may use a network that has a significant delays, like a mobile network. When you shouldn't use this pattern, when the client sends a number of operations to a single service. It's better if you implemented a batch operation for the service rather than implementing gateway aggregation pattern. Also, if the client or application is located near the backend services and the latency is not a big deal for your application. Now we are coming to the end of this video. I hope now it's clear for you what the gateway aggregation pattern is about. When you should use it, when you shouldn't. What are the different challenges that the gateway aggregation pattern is trying to solve? What are the best practices? How you can use Azure Durable Function as an implementer for this pattern. I hope you enjoyed this video. If you have any question, please feel free to put it in the comments below. Thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about the gateway offloading pattern. Gateway offloading pattern comes under two categories of cloud design patterns: design and implementation, and operational excellence. And it's all about offloading shared or specialized service functionality to a gateway proxy. And we are going to see what it means in more details in this video. Related patterns to the gateway offloading pattern are Backends-For-Frontends, gateway aggregation, and gateway routing. In the previous videos, we have talked about Backend-For-Frontends and gateway aggregation pattern, so I'm going to put links for these videos if you are interested to review these videos in details. And hopefully in future we are going to cover gateway routing pattern. Now let's go to the examples to help us understand what are the challenges that the gateway offloading pattern is trying to solve. Now let's assume that our system has two services, Service A and Service B. Then we have an external client that wants to interact with our services. Part of this interaction, we will find that we need to implement certain features in our services. Most importantly, authentication feature. We want Service A to be able to tell who is calling Service A, whether it's user or system or service account. Service A has to be able to tell who is trying to call Service A. This is one important feature that needs to be implemented. Since we have mentioned the authentication feature, we cannot ignore authorization. After we knew who is trying to call our service, we need to check whether this user or system or service account has the right permission or privileges to perform certain actions on our services. This has been done through the authorization. And these two features usually come together. And if you are implementing OAuth authentication, the client needs to send token in every request to your service. And from your side, from Service A side, we need to continuously check with every request that this token is still valid. So we need to perform some logic of token validation in our services as well. Also, you might need to have an SSL certificate to encrypt and secure the data being sent between the client and your services. Also, some industries have requirements to use certain encryption algorithms to encrypt the data before sending it through other third parties. So you might need to include encryption feature in Service A implementation as well. Also, throttling is very important to be implemented. We want to avoid a certain client from flooding our services with too many requests. ending up our services become completely unavailable or maybe too busy to process other clients' requests. Throttling could be implemented at number of requests per second or per minute, or the code, the amount of data that the client can upload or download from our services, but throttling features is very, very important to be implemented. Also, we have logging that needs to be implemented at different levels. From the clients sending requests to the services, to our services, sending responses back to the clients. Not only that, we want also to log all of the communications or requests being sent between service A and the backend functions or services and even the database. These will help us to troubleshoot and diagnose any kind of issues that might happen in our system and will help us to find the resolution of the problem sooner. Finally, we have monitoring feature. We need to have a strong monitoring mechanism that's going to help us to know what are the performance bottleneck of our services, how many requests it's able to process per second, what are the top exceptions, top faults, availability percentage. All of these things need to be covered in monitoring. All of these features need to be implemented in Service A in addition to the main business logic of Service A. Not only that, we will have to re-implement all of these features across all services in our system, which is going to be a huge amount of effort. And this is one of the challenges that the gateway offloading pattern is trying to solve. Looking at some of the features here like authentication and authorization, I know some of you already are thinking of some Azure services that we can leverage and use that will help us to offload these two features from our services and put it in other Azure services instead. And this is what this pattern is about. Some features could be shared across all services in our system, or some features could be very specialized, that it will be even better if we can offload these features from our services and put it in more specialized services instead. Whether using more of Azure or AWS out-of-the-box features, but we can offload these features from our services to free our services to focus on the main business logic. This is the challenge. Now let's see how we can use the gateway offloading pattern to resolve this problem. And the first thing that we need to do is to focus on Service A, just to make the view simpler for us. However, everything we are going to do in Service A, it's going to apply for Service B and any other service in our system. Now let's go ahead and add Azure Load Balancer, which is going to accept encrypted traffic from the user and then perform SSL offloading and continue unencrypted traffic with our services. This is called SSL offloading, which is perfectly fine in this example. However, in some situations you might need to perform end-to-end encryption. In this case, you cannot do SSL offloading at the Azure Load Balancer level, and you need to do it at the database level instead. Anyway, now let's get back to our example. At this point, we will find that we don't need to manage SSL certificates in Service A anymore, because we handed it over to Azure Load Balancer to do it for us. So now we can offload SSL feature from Service A implementation. And by adding Azure Active Directory, you might feel that we can offload other features as well, like authentication, authorization, token validation. We don't need to implement these features anymore in Service A, as long as we can leverage and use Azure Active Directory instead. Also thinking of Azure Applications Insights, which is going to provide a lot of data about our service performance, exceptions, errors, availability. At that point, we can offload the monitoring feature from Service A implementation and offload it to Azure Application Insights instead. Also, we can do the same using Logic Analytics Workspace, which is going to provide different logs for our services, and then we can offload logging feature from Service A. Then coming to the encryption feature, we will find that it will have to manage the encryption keys or secrets that's going to be used to perform different encryption functions. And then we will find that Azure Key Vault will be a better place to store those encryption keys. and then we can offload the encryption feature from service A to Azure Key Vault. Finally, coming to throttling features, we will see that we can use API management to offload throttling logic from service A. And also we can use API management to perform token validation like GWT token validation, as well as SSL certificate management. Also, if we are implemented our services using Functions app, we can still define some throttling limit at the Azure Functions app. This was an example to show you how we can leverage other Azure services to help us offload certain features from our service implementation. Gateway offloading is not limited to these services only. These are just the services that are relevant to the features we have provided in this example. You can go ahead and leverage as many Azure services as much as you like, as long as they are valid for your use case and for your scenarios. And then we can go ahead and leverage all of these Azure services to be consumed and used by all services in our system. This is how we can use the gateway offloading pattern to resolve the problems we have talked about before. Now let's talk about some considerations you need to keep in mind when using this pattern. You need to ensure that the gateway has high availability and it won't be a single point of failure for your application. Also, you need to consider the scalability of the gateway, whether it's gonna be scalable enough for your application requirements, so it won't be a bottleneck for your application performance later on. Also, you need to consider which features you will need to offload and which features you will have to implement it yourself. The idea is not to offload all features to other services or not to implement everything yourself. It's about having a good balance between both that works for your situation. Also, you should never implement any business logic in the gateway. Remember, the gateway is about offloading certain features, not to have a particular business logic implemented in the gateway itself. Finally, you need to use correlation IDs to help you track different transactions between the gateway and the backend services. Now let's see when you should use this pattern. When you have shared or common application features like SSL or encryption, or you want to move the responsibility to another team, like security team or networking team, by offloading certain features from your services to other Azure services. Now you allow networking team or security team or other team to be responsible on that offloading service. Now we are coming to the end of this video. I hope now it's clear for you what the gateway offloading pattern is about. What does it mean when we say offloading certain features from our services to Azure services? What are the benefits that we are gonna get from that? What are the considerations you need to keep in mind? And when you should implement this pattern? I hope you enjoyed this video. If you have any questions, please feel free to put it in the comments below. Thanks for watching. Hi everyone, my name is Hussein and welcome to my channel. If you are new to my work, I am creating some cloud design patterns videos with a primary focus on Azure. However, these concepts could work well with AWS or GCP or any other cloud provider you could think of. If you are interested to learn more about this topic, go ahead and check other videos in my channel. Also, make sure to click on the subscribe button to get notified about the upcoming videos. And for the like button, it's totally up to you. Today we are going to talk about the gateway routing pattern. Gateway routing pattern comes under design and implementation and operational excellence categories of cloud design patterns. And the whole idea of this pattern is to use a single endpoint to route requests to multiple services. And we are going to see this in more details in the examples. It's good to know what are the related patterns to the gateway routing. First of them, Backends-For-Frontends, gateway aggregation, and gateway offloading. I'm going to put links for these patterns if you are interested to learn more about them. Now, let's go to the examples to help us understand the gateway routing pattern better. Now, let's assume that we have an e-commerce application that consists of multiple services, like search service, order service, review service, and cart service. All of these services could be implemented using Azure App Service or Functions app. Then we have the client or the consumer application that wants to interact with these different services. And as you might expect, each of these services will have different endpoint that the client has to use in order to communicate with different services. And this is the first challenge we have in here. As the number of services are not going to be only 4 or 5, but in some situations it could reach to 100 or 1000 services. And in this case, the client will have to implement all the communications with all of these services, which is going to be a huge amount of effort on the client side. And the second challenge we have in here, if we decided to change our service architecture and split review service into 2 or 3 services. In this case, the review service endpoint will not be valid anymore for the client to consume, as we are splitting the review service into 2 different services: internal review service and third-party review service. And in this case, the client has to change their code to allow them to communicate with these 2 services separately. So these are the different challenges that might suggest you to use gateway routing pattern to improve your situation. Now, after we have addressed the problems, now let's see how we can use the gateway routing pattern to improve the situation. The gateway routing pattern suggests to have a gateway to receive all requests from the client, and then the gateway is going to route these requests to different services based on routing rules. The gateway could be something like Application Gateway or Azure Front Door, which we are going to see in a little bit more details in a minute. And then the client can use different URLs to access different services in our system. Now let's have a look at some examples of the Application Gateway and Azure Front Door to help us understand how the routing rules work. So this is Azure Front Door. As you might see, it has a front end that directs traffic to backend pools based on routing rules we have configured. And I've covered Azure Front Doors in more details in the deployment stamp video. If you are interested to learn more about it, I'm going to put a link for the deployment stamp video so you can review it. Same idea for the application gateway, which is going to route traffic to backend pools based on path-based rules. And I've covered application gateway in more details in the API management course, so I'm going to put a link to the application gateway video if you are interested to review it. Now let's get back to our example. Now let's focus on search service. And let's assume that we have implemented a new version of search service, and we called it search service 2. I know you already know that there is a versioning mechanism in Azure App Service and Functions app. Let's leave that aside for now to help me getting my point across. Let's assume that these 2 services has been implemented using different technologies, like the old one has been implemented using Azure App Service, and the new one has been implemented using Azure Functions app. And we want our client to consume search service 2. So all we need to do is to change the routing rules in the gateway. Instead of sending traffic to the search service, we are going to send the traffic to search service 2 instead. And the endpoint that the client consumes is going to be the same at all times. Also, the client doesn't need to change anything on their side to allow them to communicate to search service 2, since all of the changes has been already done in the routing rules in our gateway. This is one of the powerful features about the gateway routing pattern. Now let's talk about the review endpoint. If you remember, we have split our review service into 2 separate services: internal review service and third-party review service. And the question here is, can we configure the routing rules in the application gateway to send the traffic to both services at the same time? The answer is yes, however, you should never do that, because the routing rules in the application gateway can be configured to send 50% of the traffic to one service and other 50% of the traffic to another service. However, this should be only implemented for load balancing situation. When you have multiple instances of the same service and you want to distribute the traffic across them, not to have a totally different services and send 50% of the traffic to one of them and the other 50% of the traffic to the other service. Routing rules in the application gateway cannot send traffic to both services at the same time. What we can do instead is to introduce Gateway Aggregator, and then we are going to change the routing rules to send the traffic to the Gateway Aggregator, which is going to be responsible for communicating with both services at the same time. And then it's going to combine the response back and send it back to the client, all of that using a single endpoint for reviews. We have talked about Gateway Aggregator in a previous video, so I'm going to put a link for the Gateway Aggregator pattern if you are interested to review it in more details. Also, I want you to notice that you can combine as many cloud patterns as you like, as long as they are going to help you to solve your problem. In this case, we have used the Gateway Routing Pattern as well as Gateway Aggregator Pattern, and you can use as many design patterns as you like. Hopefully by now the Gateway Routing Pattern is much easier for you. Now let's talk about some considerations you need to keep in mind when you use this pattern. First of all is a single point of failure. Whether you are using Application Gateway or Azure Front Door, you are introducing a single point of failure for your system, since this is the only place that gets all requests to your services. Also, you need to be aware of the performance bottlenecks, since all requests are gonna be coming to a single place. Whether Application Gateway or Azure Front Door, you need to consider the performance implications of that. That's why it's very important to consider doing a load testing on the Application Gateway or Azure Front Door or the gateway routing layer in general, in addition to the load testing that you may have done for each service separately. Finally, gateway routing operates at layer 7. Now let's talk about when you should use this pattern. When you have multiple services that can be accessed behind the gateway. Also, when you want your clients to access your system using a single endpoint. Also, when you want to route external requests to internal virtual endpoints, like exposing ports on VM cluster. Now we are coming to the end of this video. I hope now it's clear for you what the gateway routing pattern is about, what problems it tries to solve, how you can use it, when you should use it. I hope you enjoyed this video, and if you have any questions, please feel free to put it in the comments below. Thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Priority Queue Pattern. Priority Queue Pattern comes under two categories of cloud design patterns, messaging category and performance efficiency. And Priority Queue Pattern is about prioritizing requests being sent to the consumer or a certain service, so that we get to process higher priority messages before than the lower priority messages. And we are going to see this in more details in this video. Now let's see other related patterns to Priority Queue Pattern. Competing Consumer Pattern and Throttling Pattern. Hopefully we are going to make a video about these two patterns in future. Now let's go ahead and see how can we implement this pattern. Let's assume that we have an application and we have a consumer. You may call the application producer or publisher or any kind of application that produces or publish events or messages that the consumer is interested to process. Then we will have a message queue that could be implemented using Azure Service Bus. And from one side, the application or publisher is going to send the messages or events to the message queue. And from the other side, the consumer is going to receive the messages from the message queue to process it. And of course, we will have many messages in the message queue waiting for the consumer to process them as well. Now, what if we have a high priority message that needs to be delivered to the consumer right away? And we want to give this message high priority to be higher than any other message in the queue. How can we achieve this? Usually message queues process messages based on order, first in, first out. However, the ordering of the messages in the message queue is not 100% guarantee until you are using a FIFO queues, for example, in AWS. But generally speaking, messages are processed in orders in the message queues. So according to this, when we have a high priority message and we place it in the message queue, it's going to stay there for a bit of time until the consumer is free and available to process the high priority message. And this is exactly the challenge that the priority queue pattern is trying to solve. How can we allow the consumer to process this high priority message before any other messages in the queue that has been already sent before? Now, after we have addressed the problem, let's see how can we use the priority queue pattern to solve this problem. Most message queue providers support something called priority queues. And it's something that allows you to specify a priority for your messages, and based on that priority, the message queue is going to order the messages in the message queue based on the priority of specified in your application. And priority queue feature is already supported by many message queue providers for Azure Service Bus or AWS SQS. And according to this, the messages are going to be placed in the message queue based on their priority. So our message queue is going to have the higher priority messages at the top. So the consumer gets to process these messages before other messages in the queue. Then it's going to be followed by medium priority messages, then followed by low priority messages. Now, when we get a new high priority message, then the message queue is going to place this high priority message before other lower priority messages that are already in the queue. And this is to ensure that the consumer gets to process higher priority messages before other messages in the queue, and once it's been sent or published by the producer application. And as I said before, the priority queue feature is already supported by most message queue providers. Now, what if your message queue provider doesn't support priority queue? What can you do in this situation? Well, if your message queue provider doesn't support priority queues, then what you can do in this situation is to implement or create a dedicated queue for each priority you have in your solution. So we are going to have 3 queues: high priority queues, the red queue, medium priority queue, the green queue, and then low priority queue, the blue queue. Then the application is going to send the high priority messages to the red queue, and the medium priority messages to the green queue, and then the low priority messages to the blue queue. And then you can have one or more consumers to process messages from the high priority queue, and you can have less number of consumers to process messages from the medium priority queue, and we can have one consumer to process messages from the low priority queue. So based on that, we have resolved the challenge that if your message queue provider doesn't support priority queues. And according to this, you might get concerned about the number of consumers we will have to create in this architecture. As a minimum, we will have to have 3 consumers based on the number of the queues we have in our architecture. And this might be too much for your architecture or your solution. And what you can do in this situation is to put all of the consumers in a pool. And instead of having a dedicated consumer to pull messages from a certain message queue, you are going to make all consumers pulling messages from all message queues at the same time, but with a condition. The condition here is that you cannot process messages from the low priority queue or medium priority queue as long as there are messages in the high priority queue. In other words, you have to process all messages in the high priority queue first before you process other medium priority queue and low priority queue. And if you follow that approach, you can have identical consumers to process all messages from your queues. And then you can scale them up and down as much as you like based on your requirements and workload. There is something I want you to think of. If you are receiving an overwhelming number of high priority messages, what would be the case for a low priority messages that's going to be in the queue? One of the cons of this architecture is that the low priority messages are going to stuck in the low priority queue until all messages, all high priority messages are going to be processed. So it's a critical decision that you need to make. Are you going to happy with the low priority messages being stuck until all higher priority messages are processed? Or you want to process low priority messages at a slower pace while you are processing the high priority messages? This is a very important decision that you need to make if you are going to follow this variation of the priority queue pattern implementation. Now let's talk about some considerations you need to keep in mind when you use priority queue pattern. And first of all is priorities. You need to define how many priorities are going to be implemented in your system, and you need to communicate them with your stakeholders so you can have a common understanding about what different priorities are going to be handled by your system. Also, you need to decide if the high priority messages must be processed before any lower priority messages. As you see in front of you here, in this architecture, high priority messages are going to be processed before medium priority and low priority. And in some situations, you need to follow or implement this approach to pause the processing of medium priority and low priority until you fully process all high priority messages. Also, you need to ensure that the higher priority messages are going to be processed first by the consumers in the multiple queue approach. Getting back to the diagram here, we need to ensure here when we pull a messages from the queue that there is no more messages in the high priority queue before we get to process medium messages or low priority messages. Also, in some situations, you might want the low priority messages to be processed at the same time while you are processing the high priority messages. In this case, you have to have a dedicated consumer to the low priority queue, as we said before. As you see in this diagram here, we have a dedicated consumer to process low priority messages at a slower pace comparing to the other higher priority messages. Also, you need to set up monitoring for your queues to be able to tell how many messages in the queue and how quick different consumers are processing these messages. Also, additional costs might be included while you are continuously checking your message queues for new messages. And you need to allow your solution to dynamically scale up and down based on the workload. Now let's see when you should use this pattern. If your system has multiple tasks with different priorities, or when you have different users or tenants that should be served with different priorities. Now we are coming to the end of this video. I hope now it's clear for you what the priority queue pattern is about, how we implement it, what are the different variations of the priority queue pattern, what you should do if your message queue provider doesn't support priority queue feature, and what are the different considerations you need to keep in mind when you use this pattern. I hope you enjoyed this video. If you have any questions, please put it in the comments below. Thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Publisher Subscriber Pattern, or some people prefer to call it PubSub Pattern. This pattern comes under messaging category of cloud design patterns, and it enables an application or a publisher to send messages or events to the consumer asynchronously. Also keep in mind that it could be one or more consumers, and this is one of the challenges that this pattern is trying to solve. How are we going to be able to send data or events or messages from one publisher to multiple subscribers or multiple consumers? And we are going to see this in more details in the examples. Let's assume that we have an application here, and this is going to be our publisher. And also we have a subscriber that's interested to receive information or events from the publisher. And in order to allow the publisher and subscriber to communicate without much dependency on each other, we need to introduce a message queue for the communication between them. By doing this, we allow the publisher to send as many data or messages as they like, without any dependency on how quick the subscriber is able to process these messages. And according to this, the publisher is going to send data or messages to the message queue. And from the other side, the subscriber is going to read or process these messages from the message queue to process them at their own pace. So far, we have integrated one publisher with one subscriber. Now, what if another subscriber is interested to join us? In this case, we would have to create another message queue and change our application code to allow it to publish messages to the new message queue as well. And then the yellow subscriber will be able to process these messages at their own pace. And for every new subscriber is interested to join, we are going to have to create an additional resource or additional message queue. And also we need to do some application code changes to allow the publisher to send the data or messages to the new message queue we have created. And this is not everything. We still need to create or apply some monitoring alerts mechanism for these message queues to see how they are performing, how many messages may be stuck in the queue, and how quick the subscriber is able to process these messages. So as we see in this architecture, it's not scalable enough, because every time a new subscriber comes in, we have to do something manually to allow them to receive our messages. And this is the challenge that this pattern is trying to solve. How are we going to allow multiple subscribers to receive the data or messages from the publisher asynchronously, without much dependency between them, and without doing manual work from our side, and to allow the solution to be more scalable for future? Now, after we have addressed the problem, now let's see how can we use the publisher subscriber pattern to resolve this problem. Now let's go ahead and clean this up. And then we are going to add one message queue. So the publisher is going to send or publish its messages to the message queue we have created. And then from the other side, the message queue is going to send its messages to all subscribers that are interested to receive our messages. And you might pause me here and say, this is not possible. One of the fundamental things about message queues is that it's able to send the message to one subscriber. Like we cannot send one message to multiple subscribers in message queues. And this is one of the fundamental things about message queues. So how are we going to be able to send one message to multiple subscribers, although it's not allowed by message queues technology? And to answer this question properly, let's go ahead and have a quick review of the different messaging services in Azure platform. So we do have Azure Storage Queues and Azure Service Bus Queues. And both of these services support each message to be processed by one consumer or one subscriber. However, there is another Azure service called Azure Service Bus Topics. But this one has an ability to process messages by multiple consumers. And this is the one that we are going to be used in our solution. And getting back to our architecture here, we are going to be using Azure Service Bus Topic instead of Azure Service Bus Queue. And if you are not very familiar with Azure Service Bus Topics, it's a pretty much message queue, but with an ability to deliver a message to multiple consumers at the same time. And this is one of the key differences between topics and queues in Azure Service Bus. So in our architecture here, the publisher is going to publish or send messages to the Azure Service Bus topic. And then from Azure Service Bus topic, we are going to distribute the message to all subscribers that are interested to receive events or messages from us. Now, you might be asking, what if a new subscriber wanted to join our solution? And in this case, the new subscriber would just need to subscribe to the Azure Service Bus topic, and they should be able to get messages from our system once they have subscribed to that topic. And by doing this, we don't have to do any code changes on the publisher side for any new subscriber that is interested to join our solution. Also, we are going to build only one Azure component, which is Azure Service Bus topic. We don't need to create multiple or dedicated Azure Service Bus queues for each subscriber that is interested to join our solution. Also, we will need to build our monitoring capabilities only once for the topic we have created. This is how can we use Azure Service Bus topic to implement publisher subscriber pattern in a really nice and simple way. Now let's talk about some key considerations you need to keep in mind when you use the publisher subscriber pattern. And the first thing you need to do is to use existing technologies. You've seen in this video I've already used Azure Service Bus topics. And also you can use event hubs or event grid. What you don't need to do is to go ahead and build your own pub sub module. You don't have to do that as long as there are existing technologies out there. Also, you need to think of how are you going to handle the subscriptions for your solution. Are you going to allow the subscribers to go ahead to subscribe or unsubscribe on their own pace, or you want to develop some approval mechanism around the subscriptions for your solution? Also, you want to make sure that the messages in the message queue or in the topic are encrypted and secure, and only the authorized subscribers are allowed to access your messages. In some scenarios, you might have some subscribers are interested about subset of messages. In this case, it might be helpful if you develop multiple topics, and then you deliver your messages to the appropriate topic, to make it easier to the subscriber to subscribe to the topic that they are interested into. Also, you want to develop or implement a wildcard subscriber. This is to allow your subscribers to subscribe to all your topics by one action. This is assuming that you have developed multiple topics for your solution. Also keep in mind that this pattern is one-way communication between the publisher and subscriber. If the subscriber wants to send something back to the publisher, like acknowledgement message, it won't be possible by this pattern. You need to implement another pattern called request reply pattern or request response pattern. And hopefully we are going to make a video about it in future. Usually in message queues, the order of the messages is not 100% guaranteed until you are using FIFO queues, for example in AWS. However, generally speaking, the order of the messages is not guaranteed. Message queues are trying to deliver your messages based on FIFO, first in, first out. However, it's not guaranteed. And when you design your messages, make sure that your messages are idempotent operations. They are not depending on any other messages in the queue because you are not sure when your message is going to be delivered. Also, you can use a priority queue to give more priority to a particular message to get delivered to the subscribers before other messages in the queue. And we have talked about this pattern before in a priority queue pattern. And I'm going to put a link for this pattern if you are interested to review this video. Also, you need to handle poison messages in your solution. Poison messages are messages that kept failing over and over and over until the number of retries are consumed. And what you need to do in this case is to deliver these poison messages to a poison queue. So you are freeing the main queue for other messages. Poison queue is already implemented in most cloud message queues, and it's already built in Azure Service Bus queues or topics. Also, you need to handle the repeated messages. Generally speaking, in cloud message queues, the message is guaranteed to be delivered at least once. And there is a little chance that your message is going to be delivered more than once, and you need to handle these scenarios. There is a duplication detection option you can use straight away in Azure Service Bus queues or topics. And usually, message in the message queues has an expiration time. Usually it's 14 days. And you need to define how long you need to keep your message alive in the message queue. And finally, you have an option to schedule your messages. So you are going to publish your message and put it in the message queue, but they are going to be available only at a certain time in future for the subscribers to process. Now let's see when you should use this pattern. When you want to broadcast information to multiple consumers. If you have only one consumer, you can still use Azure Service Bus queue. However, there is no reason that prohibits you from using Azure Service Bus topics. To be prepared for future and to be prepared if other subscribers are interested to join your solution. Also very important to highlight that you are sending messages to the subscribers and you are not expecting a real-time response from them. As we said before, this pattern is a one-way communication from the publisher to the subscriber, we are not expecting any acknowledgement messages to be sent from the subscriber. Now we are coming to the end of this video. I hope now it's clear for you what the publisher subscriber pattern is about, how you can implement it in Azure, what is Azure Service Bus topic, and how you can use it to implement this pattern to make the life easier for you to handle multiple subscribers at the same time. I hope you enjoyed this video. If you have any questions, please feel free to put it in the comments below, and thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about queue-based load leveling pattern. This pattern comes under many categories of cloud design patterns. First and foremost, messaging category. And this is very obvious because we are talking about message queues, and the messaging category is going to be at the top of our list. Also, this pattern adds a lot of reliability and resiliency and performance enhancement to your solution, as we are going to see in more details in this video. And this pattern simply uses a queue to work as a buffer between the source or the producer and the consumer or destination. And we are going to see this in more details in a minute. It's always good to mention other related patterns to the queue-based load leveling pattern. The related patterns are Competing Consumer Pattern and Throttling Pattern. Hopefully we are going to make a video about these two patterns in future. Now let's dive into the example to help us understand this pattern better. Let's assume that we have our users and we have our service. It could be a website hosted in Azure App Service, it could be an API hosted in API management, it could be Azure Functions app, anything you could think of. And then the users are going to interact with our service. Then we are going to have at the backend a SQL database engine that our service needs to interact with to perform different sort of read and write operations. So far, everything is perfect for our solution. Our SQL database is able to handle the read and write operations being sent by our service, and our service or website or API is able to handle all requests being sent by the external users. So we don't have any problems at the moment. Then over time, our service or website become more popular, and more users are started to interact with our service, sending more requests to our service, which is going to lead to an increased number of read and write operations that our service need to perform on the database side. And of course, our database engine hasn't been designed to handle this increase of the workload we are experiencing at the moment. And sooner or later, it's going to impact the performance between our service and the database engine. Now, there are few things we can do at the database level to help us mitigate this problem. I'm going to touch on them really quickly before we get back on track to our pattern. So what we can do at the database level is to scale it up to the higher tier, or maybe highest tier, which is going to assign more CPU and memory to our database instance, which is going to help it to handle this increased number of requests we are getting from our users. This could be one approach. Another approach, we could have one or more read replicas. So we are going to direct all of the read operations to the read replica databases instead of the primary database. And we do this to offload the read load from the primary database to free it up to perform the write operations, which is more resource intensive than the read operations. So these are the two approaches we could do quickly at the database side. Let's assume that we have gone with the upscaling our database engine to the highest tier, and we still have this problem. We still experience some performance or deadlocks or errors happening between our service and our SQL database. And in a way or another, it's going to be propagated to the end user while they are interacting with our service. And they will experience that their requests are not being executed on our website. This is why this pattern is listed under reliability and resiliency, because it could save your solution from being unavailable to external users or from being down or suffer performance issues. Now, after we have talked about the problem, let's see how can we use this pattern to solve this problem. But first of all, let's clean this up. And instead of having a direct interaction between our service and the database engine, we are going to introduce a message queue. It could be Azure Service Bus Queue, for example. And then our service is going to send the database operations or requests in the messages, in the message queue. And then from the other side, we are going to have an Azure Functions app that listens to the message queue and is going to be triggered for every message being placed in the message queue. And then the Azure Functions app is going to pull messages from the queue and execute it in the SQL database. And by doing this, we are buffering the database operations between our service and the database engine to be executed at a slower pace that the database engine can handle. And more importantly, it wouldn't affect the user experience while they are interacting with our service. Because the request has been already sent, when a service is placing a message in the message queue, the request has been already sent and the user operation has been fulfilled, in a way or another. Yes, it hasn't hit the database yet, but it's in the way through. Now let's consider that we are an e-commerce application, like Amazon for example, and you are a registered user and Amazon knows your delivery address and your credit card and everything about you. When you place an online order, it's not a time-critical operation that requires to hit the database in a real-time fashion. And I'm going to tell you a personal experience for myself while I was shopping at Amazon.com. Many times after I place an order, after I successfully place an order, I got an email back after a few minutes or seconds that tells me that my credit card might be expired or certain item is not available anymore in the warehouse. Then I can go back and put a valid credit card number or select another item that's still available in the warehouse. And what this tells you that order placement operation is not a real-time operation at Amazon.com because it's not a time-critical operation. It would perfectly be suitable to be implemented using queue-based load leveling pattern without any problems. Now let's move to another scenario. Assume that we are in a banking application and you want to perform a cash withdrawal operation. And it can be very tricky because you cannot queue cash withdrawal requests in a message queue while the actual balance hasn't been changed in the SQL database yet. You might end up that the client may be performing more than one cash withdrawal operation based on a smaller amount of balance that they have in the database. And you need to be very careful when you use this pattern with this kind of scenarios. And actually we are going to have it in more details to help you understand it better. Let's assume that the client is sending a cash withdrawal request by 100. And the client balance in the database is $100 as well, which would suggest that the cash withdrawal operation will be fulfilled successfully. Now, let's assume that our service has taken this request and put it in a message queue, and for some reason the message hasn't executed yet in the database and still is stuck in the queue. Maybe because the database engine is busy performing other operations. Alright, now the same user sent another cash withdrawal request by $50. If our service is going to check the client balance in the database only, it's going to be a problem. Because by checking the balance in the database only, it's going to tell that yes, this user can perform a cash withdrawal with $50 because they already have $100 balance in their account. And it neglects the fact that there is another cash withdrawal operation still stuck in the queue by $100, which if we take it into account, it wouldn't make the new cash withdrawal by $50 to be accepted. So, what we can do in this situation is, while our service is checking the client balance in the database, also, our service needs to take into consideration the other cash withdrawal requests that may be stuck in the queue, and consolidate both together and send back the actual client balance that they actually have. And if this happens, our service is going to tell the client that they cannot perform cash withdrawal with $50 anymore because they don't have enough balance in their account. This is what I meant, that you need to be very careful when you use this pattern, and you need to be aware of what kind of scenarios you are using this pattern for. And for the read operations, you need to have a very strong reason to use this pattern for the read operations. Actually, I couldn't think of any at the moment. I think it will be way more efficient to direct the read operations to read replica databases instead of buffering them in a message queue. Hopefully this is now clear for you. Now let's talk about some considerations you need to keep in mind when you use this pattern. Let's assume that your service has decided to put 1 million messages in a message queue, and this in return is going to trigger or fire 1 million executions of the Azure Functions app to execute these messages against your SQL database. And both of us know that the SQL database won't be happy about that. So you need to avoid overwhelming your target or destination with too many requests, even though you're using this pattern. So you need to specify the rate at which you are going to execute these requests against your destination. Also, you need to be aware of that message queues are one-way communication. It won't be suitable to send an acknowledgement message back. If you want to send an acknowledge message back, you need to implement other patterns, like request response pattern. Also, you need to be careful about auto-scaling the services behind the message queue, which is going to be the Azure Functions app in our example. You don't want to have many competing services competing for the same message. Or also, you don't want to confuse the message queue, which Azure function instance it should trigger when it receives a certain message. It might do more harm than good. Now let's see when you should use this pattern when your application is going to expect a heavy workloads that your backend database cannot handle, and you need to buffer them somewhere so you can execute these requests at a rate that the database engine can handle. And when you shouldn't use this pattern if you are expecting a real-time response from the target. As I said before, it doesn't make any sense to use this pattern for read operations because you are expecting data to be returned straight away. Now we are coming to the end of this video. I hope now it's clear for you what this pattern is about. What are the challenges it tries to solve? How you can use this pattern to improve the resiliency and the reliability of your solution? How you can use the message queue to buffer requests between the source and destination? When you should use this pattern and when you shouldn't. I hope you enjoyed this video. If you have any questions, please put it in the comments below, and thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about asynchronous request reply pattern. This pattern comes under messaging category of cloud design patterns. And in a previous videos, we have talked about how we can use the publisher subscriber pattern to decouple the backend processing from the front-end host. And what we are going to see in this pattern, how the backend process will be able to send an asynchronous response to the front-end. Now let's dive into the example to help us understand this pattern better. Let's say that we have a group of users are interacting with our website, which is running in a web client like a Chrome browser, for example. And because it's a client application, Chrome browser will need to call our APIs every now and then to perform some actions or get some data. And let's say that we are implementing our APIs to respond synchronously to all requests coming from the web client or coming from Chrome, so our APIs will be responding straight away to all of these requests. However, this could be really easy and simple to implement, but you need to be aware of other things that might add more latency to your API response. For example, the geographical location of the caller, which is the Chrome browser, and the backend, which is the API in our case. If they are in a totally separate regions, it's gonna add more latency to your solution. Also, the current workload, like how many users are currently using your website, and how many API calls they are calling against your APIs. In addition to the size of the request payload that's being sent to your APIs and how much time it's gonna be required from your API to respond to these different requests. In addition to some security components you might need to add at your API side to make sure that the requests are secure. And these are the different considerations or factors you need to be aware of if you are going to develop your APIs to respond synchronously to all requests coming from a web client like a Chrome browser. And let's say if we are running our APIs on an Azure Function app or on an Azure App Service, we definitely are able to scale these components up to the higher tier to be able to handle more workload and to be more efficient. And when we are scaling up our services, then our APIs will be able to respond quick enough to different requests coming from our users. And generally speaking, the response time for the APIs is measured by milliseconds. And some companies have different standards in this. Some companies have a 10 milliseconds response time as a standard, while other companies have 100 millisecond response time as a standard. Either way, you need to make sure that your API responds very quickly to different requests coming from your users. And we all know that this is not always the case. Some APIs might require few seconds or minutes or even hours to finish its processing before it's able to send a response back to the client or to the user. And if this is the case, we know that this architecture will not work well because we have kind of a long-running process that might take seconds or minutes or even hours to process, and then definitely we need to do something different. So we need to decouple the front end from the back end to remove the dependency between them. And this is going to allow the API or the backend to spend as much time as required to finish the backend processing without having any negative effect on the front end. And this is what we have talked about before in the pub/sub pattern or publisher-subscriber pattern. So what we are going to do is to introduce an Azure Service Bus. And then the client or the Chrome browser is going to send their requests to Azure Service Bus. And then from the other side, the APIs is going to pull these requests to process them independently from the front end. So what we have done in here, we separated the front end from the back end by using an Azure Service Bus. So we are allowing the API or the backend to spend as much time it needs to finish the backend processing without any dependency on the front end. And while we are doing this, we have added a little bit more complexity to our architecture. Because yes, we have improved it from one way to send the requests asynchronously to the APIs or to the backend to process. But the question now for our pattern to answer, how those APIs are going to send those responses asynchronously to the clients or to the Chrome browser. And this is exactly what this pattern is trying to solve. Now, after we have addressed the problem, now let's see how we can use the asynchronous request reply pattern to solve this problem. Now let's have a look at this diagram, which explains it really well. And what's going to happen is the client, which is a Chrome browser in our case, is going to send an asynchronous API call to our API endpoint to trigger a long-running process that might take seconds, minutes, or even hours. And then our API endpoint is going to respond with HTTP 202 accepted response code to acknowledge that the request has been received by the API endpoint and the API is working on it. And there is something very important here you need to be aware of. You need to perform input validation or request validation before you respond back to the client with 202 response code. Because if the request is invalid, you need the client to know as soon as possible that the request is invalid. There is no point for making the client hanging around for a few minutes or even hours before telling them that the request is not valid. So if this is the case and the client sent an invalid request to your API, you need to let them know about this as soon as possible. And you need to respond back with HTTP 400 bad request. So the client can change some inputs to make the request valid for your API endpoint. Now let's say that the API endpoint has done all of the request validations and everything goes alright and it responded back with HTTP 202 accepted response code. And in this response, it's going to have a location reference for the endpoint that the client is going to use to check or get the result of the long-running process. Then our API is going to send this request to probably Azure Service Bus queue to handle or trigger the execution of this long-running process. And while the operation is still in progress, the API or status endpoint is going to respond back with HTTP 202 response code to the client. Until the work is completed, then our status endpoint is going to send a response that indicates the completion of this process or even redirect the user to the resource URL using HTTP 302 response code. And then at that point, the client will be able to get the result of their request and they will receive HTTP 200 OK response code. Now let's go through it again really quickly. So the client is going to send a request to our API, and the API is going to respond back with HTTP 202 after performing the request validation. And as long as the request is still in progress, the client is going to receive HTTP 202 response code until the resource has been created or the request has been completed and the result is ready for the client. Then the client is going to receive HTTP 302 found response code. And then the client will be able to get the result of the request and they will receive HTTP 200 response code. Now let's have a look at this diagram, which is going to help you understand how we can make it work using Azure components. First step, we have that our Chrome browser is going to call our API, which is hosted in Azure function. And then our API or our Azure function is going to perform the request validation, and if everything is alright, it's going to place the message in Azure Service Bus queue. And then straight is gonna respond back to the client with the status endpoint. Then when we receive a message in the Azure Service Bus queue, it's going to trigger the execution of another function app, which is going to perform the long-running process. And if your long-running process is going to exceed the limits of the function apps, you may need to consider using step functions. Anyway, so this function app is going to process the backend processing for your long-running process, and then it's going to write the results to a certain blob storage. And then we have a third function app which is listening to this blob storage to see if the results are ready for the client or not. And once the results are ready, then the clients will be able to grab it while they are checking on the status endpoint. So this is exactly how we can make it work on Azure. Hopefully this is now clear enough for you. And definitely you can change the function apps and use Azure App Service. And also you can change the Azure Service Bus queues and use topics or even Event Hub. Also you can change the blob storage and use any cloud-based storage. Now let's talk about some considerations you need to be aware of when you use this pattern. And first of all, there are a different number of ways to implement this pattern over HTTP. And if we are going to follow the pure REST semantics, it says that we should return HTTP 404 not found response code as long as the response is not ready for the client. So you need to be aware of that and you need to decide which response code you are going to return to your client. Also in this response, you should indicate the location, which is the URL that the client is going to use to pull the results when it's ready. And also the frequency, which is an estimate of when the processing will be completed. So these are the two headers we are going to have in the response, location and retry after. And retry after is primarily designed to avoid or prevent the client from sending overwhelming requests to the status endpoint while the request is still being in progress. Also, you might need to use processing proxy or FASA to manipulate some response headers or a payload depending on your service or your response. Also, you want to make sure that you are using the right response code. So you want to make sure that you are responding with HTTP 302 or 303 if your status endpoint is going to redirect on completion. And when the client request is completed, you need to respond back with the right response code like either 200 or 201 or even 204. And if there is any error, you need to respond back with the right response code that indicates this error. Also, you need to be prepared of that not all solutions can implement this pattern the same way. Some solutions might need to add additional headers to the request or response. Some legacy clients cannot support this pattern at all. Also, you want to allow your client to be able to cancel this long-running process at any point of time. Now let's see when you should use this pattern. For your client-side code, such as a browser application, where it's difficult to provide a callback endpoint, or the use of a long-running connection is going to add more complexity to your solution. Also, you want to implement this pattern for service calls where only HTTP protocol is available. And the return service cannot fire a callback because of firewall restriction on the client side, for example. Also, when your service calls needs to be integrated with a legacy architecture that doesn't support modern callback technologies such as WebSockets or webhooks. Now let's see when you shouldn't use this pattern. When you can use any other built-in asynchronous notification like Azure Event Grid. Also when the responses must be streamed in a real-time fashion to the client. And when the client needs to collect many results and the received latency to those results is important. Also when you want to use a server-side persistent network connection such as a WebSocket. Or when the network design allows you to open up ports to receive asynchronous callbacks or webhooks. Now we are coming to the end of this video. I hope now it's clear for you what the asynchronous request reply pattern is about. What are the different problems it tries to solve? How we can implement it? What are the considerations you need to be aware of when you implement this pattern? When you should use it and when you shouldn't? I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hussein and in this video we are going to talk about the Bulkhead Pattern. Bulkhead Pattern lies under reliability category of cloud design patterns. As we are going to see through this video, this pattern contributes a lot in improving the reliability of your solution. As the definition says, it's going to isolate different application components or elements and put them into isolated pools. So if one component or pool has failed, others will continue to function as usual. It's good to mention other related patterns to the Bulkhead Pattern. Related patterns are Circuit Breaker Pattern, Retry Pattern, and Throttling Pattern. And in most cases, you will find yourself need to implement some of these patterns in your Bulkhead Pattern implementation. Now let's see from where the Bulkhead name comes from. And it came from ship building. Ships are not one big unit, as you may see from the outside. What's actually going on the inside is that they build the ships based on different sections, and they called it bulks. In the old days, when one of these bulks gets compromised or filled with water, water is going to leak to other bulks of the ship, ending up sending the whole ship to the deep water. Then a solution has been introduced to build a stronger barriers between the bulks, and they called it bulkheads. So if one of our bulks gets compromised or filled with water, the water is not gonna be leaking to other bulks, and the ship can continue its journey. Bulkhead is still in use in maritime, in building ships, navy, submarines, and we are using the same concept to make sure if one of our services got compromised, it won't affect the full solution. Now let's get to the scenarios and see how can we implement this. Let's say we have three services, Service A, Service B, and Service C. And some clients are sending requests to Service C. And in order for Service C to perform the client requests, Service C has to call Service B to get some data, and similarly, Service B has to call Service A to get some data as well. Now let's assume that Service A has got compromised or become unavailable. Now we know for sure that Service A will not be able to perform its function, and we are going to lose the part of data that Service A was supposed to get. But someone might say, as we are implementing service-oriented architecture and we have our solution built in different services, we should be fine. We have only one service down, but other services are up and running. But unfortunately, this is not the case. Because Service B is continuously trying to reach to Service A to get the data. And sooner or later, Service B is going to run out of resources because all of the Service B resources are going to be exhausted, trying to reach to Service A, which is not available anymore. So sooner or later, Service B will not become available as well as Service A. And to give an example on this, let's assume that our services are built on Azure App Service. And if you have used Azure App Service to implement a service that calls another service, you may come across SNAT port allocation or SNAT port exhaustion terms. And what it means that each Azure App Service has a defined set of SNAT ports that it can use to reach out to other services. Now back to our example. SNAT ports for service B is going to be fully allocated, try to reach to service A, which is not available anymore. The only thing that's going to release these SNAT ports is when the timeout has expired. And even though when it happens, it's gonna be reallocated by the requests that service B is continuously sent to service A. So bottom line is these SNAT ports are going to be allocated at all times and service B is not going to be available. And similarly, service C is not going to be available as well. And this is the first scenario that we are talking about here. Now let's talk about a different scenario. Let's assume we have a service. Let's call it service X. And we have a different clients sending requests to service X. However, one of these clients is sending an overwhelming number of requests to service X, and other clients are sending a standard number of requests. What we are gonna see that service X resources are going to be busy performing the requests coming from this particular client, and it's going to affect service X availability to perform the requests coming from other clients. And this is the second scenario that we are talking about here. One particular client is sending overwhelming number of requests that affects other clients to perform the requests. What we are going to do here is implement a connection pool in service C. This connection pool is going to be allocated a particular number of SNAT ports, and this connection pool is going to be dedicated for all communications with service B. And similarly, we are going to implement a connection pool in service B that's responsible for all communication with service A. And as well, we are going to allocate a particular number of SNAT ports for this connection pool. Now, when service A is down or become unavailable, all of the SNAT ports being allocated in the service A connection pool are going to be allocated trying to reach to service A, which is not available anymore, leaving the rest of service B SNAT ports and resources free to perform other operations that service B needs to perform. So this is our bulkhead that stops the damage in this situation. Now let's see another example. Let's say that the external clients are sending requests to service A, as well as internal system calls coming from service B. And the external clients are sending an overwhelming number of requests to service A compared to the requests that service B is sending. And what's going to happen is that service A is going to be really busy to perform the requests coming from the external clients, and it might affect service A availability to perform the internal system calls coming from service B. And what we need to do in this situation is to implement a container that's dedicated to perform the requests coming from the external clients, and have another container that's dedicated to perform the internal system calls coming from service B. And when we receive an overwhelming number of requests from the external clients, we can scale the containers up as much as we like to perform these requests. Now let's take it to the next level. Let's say that the external clients are launching a DDoS attack on our service, and that attack has successfully passed through your security defenses and firewalls. And what's going to happen in here is that it's going to affect the container that's been dedicated to receive the external client requests, leaving the other container up and running to be able to receive the internal system calls coming from service B. This is how we can use the bulkhead to stop that damage, and to allow service A to isolate different workloads coming from different clients. Now let's go to the second example. We have the different clients sending a different number of requests to service X, and I'm sure you will get it right. We will create different container for each client workload to make sure that they are going to be separate from each other. And if one client sending overwhelming number of requests to service X we can easily scale up the container that's been dedicated for that client, and leaving other containers able to perform other clients' requests. And on the other side, if one of the clients is performing a DDoS attack against our service, it's going to affect only one container that's dedicated for that particular client, leaving other containers up and running to perform other client requests. This is how to use the Bulkhead pattern to stop the damage in your solution. Now let's see some considerations you need to keep in mind when implementing this pattern. First of all, the level of isolation. How deep do you want to go in your isolation? Are you going to create a separate container for each client, or are you going to organize them differently? You need to combine the business requirement with the technical requirement in this area to make sure that you are putting the right level of isolation into your solution architecture. Also, I mentioned before that you may be able to use retry or circuit breaker or throttling patterns and combine them with the bulkhead pattern. In this example here, if we implemented the circuit breaker pattern in service B, that stop service B from calling or sending any more requests to service A as soon as service A becomes unavailable. This could be one of the ways to stop the damage as well. Also, if you are using Azure API Management or Functions app, you should be able to specify the throttling limit that each client is able to send to your service or your API. As we mentioned, the connection pool, you need to consider process or threads pool as well, also using separate VMs or container or processes for different workloads, and getting to the asynchronous communication, which is really interesting. If we use the message queue in between to loosely couple between service B and service A, then service B just sending the requests to the message queue, and it doesn't matter if service A is up or down. Service B, it's not going to be affected by the availability of service A, and this is one of the values of introducing the asynchronous communication in this kind of requests. Also, level of granularity, it ties well with the level of isolation, thinking of the business requirement and the technical requirement, finally getting to the monitoring to monitor all of these different partitions or isolations you have defined for your solution. Now let's see when you should implement this pattern. When you want to isolate resources used to consume the backend services. Also, when you have a different tiers of consumers, critical, standard, and free, and you have to do some level of isolation between these tiers. Also, when you want to protect your application from cascading failure or dominoes effects. Now let's see when you shouldn't use this pattern. When it's not required to have that level of isolation between different consumer tiers, it's not a business requirement for you, then you shouldn't implement it. Also, you need to avoid the added complexity if it's not necessary. As I said before, you should always aim for simplicity over just following or implementing a particular pattern. Now we are coming to the end of this video. I hope now it's clear for you what the bulkhead pattern is about, how you can combine it with other patterns, when you should use it, when you shouldn't. I hope you enjoyed this video. If you have any questions, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Retry Pattern. If we take a look at the different cloud design pattern categories and think of what might be the best category to classify or put Retry Pattern under it, we will not find any category better than reliability category. Because Retry Pattern helps your application to handle faults differently. Frankly speaking, many applications out there have proper error handling. So in case of any error happen in your application, you are going to catch it, send it to the user, and advising them what they need to do differently. But the question we need to ask ourselves is, does all of these errors really need to go back to the user, or there is a chance for us to catch or handle some of these errors and try them one more time or even few number of times before advising the user that their request has failed? Also, in most cases, when our application tells the user that their request has failed, the only action that the user can do is click the submit button one more time. And this is exactly what this pattern is trying to do, trying to improve the reliability of your application by retrying certain kind of errors, certain number of times, before advising the user that their request has failed. And we are going to see this in more details in this video. Also, it's good to know that circuit breaker pattern is very close to retry pattern in concept and target. Now let's dive into the example to help us understand this better. Let's assume that we have a group of users that are interacting with our service or our system. And let's assume that our system is hosted in Azure App Service. It could be also hosted in any Azure front-facing services like front door, API management, functions app, etc. And let's say that our system is interacting with a SQL database. And this is the architecture of our solution. So far it's reliable and stable, it doesn't have any issues. But every now and then our system experiences high workloads, coming from a large number of requests coming from the users. In a way or another, it's going to affect the database performance, because we already know that the SQL database has been designed to be as efficient as possible, and it can execute certain number of operations at any point of time. And if we are going to overwhelm the SQL database with too many requests, the SQL engine is going to kill the new operations to allow the SQL engine to have more resources to finish the execution of the operations that are already in progress. So in this case, the SQL is going to respond back with a deadlock exception. And our system has a proper error handling for this kind of exception and is going to send it back to the user, advising the user to try one more time, hoping that in the next try the SQL would be available to execute or finish this request. And what the user is going to do in this case is to send the request one more time by clicking on the submit button. And then in this case, the second retry has succeeded because the SQL engine was available to perform this operation. This is the main concept behind the retry pattern. Sending the request one more time, hoping it's going to succeed in the next retry. But the question we need to ask ourselves here, would it be even better if we handled this exception at the server side or at the system side? So when the SQL sends a deadlock exception to our application will handle this exception and send it one more time to the SQL database, hoping that in the second retry the SQL would be available to finish the execution of our request. This would be way better than sending the deadlock exception to the user or advising the user to try the request again sometime later. This is exactly the core concept of this pattern, and this is how the pattern is improving the reliability of our application. We are filtering out certain kind of errors that we can handle at the application level and try to execute them one more time against a SQL database or even another API, rather than sending the error to the end user and asking them to perform this action again. However, there are some constraints you need to be aware of and different retry strategies you need to know when you use this pattern. And the first retry strategy we are going to talk about here is cancel strategy. You want your application to kill this operation and send back an exception to the user as soon as possible, because there is no point for retry this failed operation one more time. Usually we use cancel strategy when the faults are not transient, and it's very unlikely for the faults to be succeeded if we repeated it again and again. And the best example I would like to give in this one is the authentication failure. If the user has provided incorrect credentials to our application, then our application tried to validate these credentials against identity provider, and the identity provider said it's incorrect credentials. There is no point that our system is going to send another retry request to the identity provider, hoping that the identity provider is going to say at some point, yep, this is a correct credentials. The best thing we can do for this kind of error is to kill the operation and save the application resources and send the error back straight to the user, hoping that the second time the user would provide a correct credentials. The second strategy we have in here is retry strategy. And we do this when we have uncommon or rare error, such as a memory error, for example, that is very likely to succeed if we tried it one more time. This kind of errors we need to handle in our application and send the request one more time, hoping it's going to succeed. The main difference between the second strategy here and the third one that we are going to talk about in a minute is the time. In the retry strategy, we are sending the retry request immediately when we get a failure, because it's an uncommon or a rare fault, and it's very likely to succeed if we send it again immediately, once we get the failure. However, in the third strategy, we are going to retry, but after a certain delay of time. And we use this when there is a connectivity or a busy fault, pretty much similar to the database example I was talking about earlier on in this video. And in this strategy, the error is unlikely to be repeated if we waited a little bit of a time before sending another retry request. This is why, and this is the main difference between the third strategy and the second strategy, is the number of time or a period of time that we need to wait before sending another request. Because if we rushed sending the retry request or had an aggressive retry policy, for the database engine, for example, probably the result is going to be the same. If we have received a deadlock exception from the SQL database, and immediately we send another request, another retry request to the SQL server, it's very likely it's going to fail. So we need to wait a little bit of a time before we send the retry request. And this is the main difference between the second strategy, which is retry only, and then the third one, which is retry after delay. Now let's talk about some considerations you need to keep in mind when you use any of these strategies for the retry pattern. And first of all, you need to consider the retry policies as part of your business requirement. It needs to be well communicated to the business stakeholders. Everyone needs to be aware of it. It's not a workaround that you do on your own or under the table to improve the reliability of your application. Also, you need to avoid sending an aggressive retry requests to the target system, hoping that one of them is going to succeed. Actually, you might be doing more harm than good. You might be burning out your application resources by sending too frequent retry requests. Also, you didn't give the target system a chance to recover from the heavy workload that they had. And after sending a certain number of unsuccessful retry requests, you need your application to stop sending any more retry requests, because at that point, it's going to burn the resources. And the best thing you can do in here is to implement the circuit breaker pattern. So after a certain number of unsuccessful retries, you are going to stop your application from sending any more retry requests for a certain point of time, because there is no point for sending these retry requests because the target system is not available or very busy performing other operations. Also, you need to be aware of the kind of operation you are performing the retry request for, whether it's an idempotent operation or not. Generally speaking, idempotent operations are safe to be executed or retried more than once without any problems. But if your operation is not idempotent operation, it might make some problems. For example, if a certain operation is going to send a request to the target and expects a response back, for any reason it didn't receive the response back, then the application will catch it as a fault and will send another retry, which is going to duplicate the request to the target in order to receive a response. And in this case, it's going to be an issue that you need to avoid. Also, you need to be aware of how much time you are going to wait between the different retry requests. You don't want to send an aggressive retry request. Also, you don't want to wait too much before sending a second retry request. You need to have a balance between both that works well with the type of the exception you are getting. For some exceptions, it's absolutely fine to send another retry request immediately. However, for other type of exceptions, you need to wait a little bit of a time before you send another retry request. Also, you need to consider if you are going to send a retry request for an operation that's part of a transaction. We already know that transaction is all pass, all succeed, or all fail kind of things, like you combine different kind of operations, so all of them can pass or all of them fail at the same time. And you need to avoid sending a retry request for a particular operation that's a part of a transaction, because it might harm the full scope of the transaction. Also, you should only send a retry request when the full context of the operation is understood. Maybe your service is sending another request to another service that's going to perform another actions. And if you kept sending retry requests, your service is going to send another services or another requests to the third-party services, and you have no idea what's happening in there. Definitely you need to test the retry mechanism and making sure it's working under different situations, and you need to log different actions so you can track and investigate these faults or these errors to fix them in future. Now let's see when you should use this pattern for a transient faults. For example, a remote service is not available or database server is very busy executing too many requests. These kinds of faults that are not permanent, and it's very likely to disappear if we send another retry one more time. And we consider these faults called short-lived faults. Now let's see when you shouldn't use this pattern for the long-lasting faults, also for the errors in the business logic. You don't want to send another retry if you already have an error in the business validation layer of your application. If your application has scalability or performance issues, like your application needs to be scaled out or up to the higher tier, and you're trying to avoid this by implementing a retry policy, this is not a good idea to use it, so you should avoid using this pattern if you are aware that your application needs to be scaled to the next tier. This pattern is to solve a certain number of errors. It's not a workaround for scalability concerns. That's all you need to know about this pattern. Now we are coming to the end of this video. I hope now it's clear for you what the retry pattern is about. What are the different retry strategies you can use? What are the differences between them? And in which cases the retry pattern could be beneficial for your system, and in which cases it could make more harm to your application. Also, we talked about when you should use this pattern, when you shouldn't, and the considerations you need to follow when you implement this pattern. I hope you enjoyed this video, and if you have any questions, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hussain, and in this video we are going to talk about static content hosting pattern. If you are new to my work, I'm creating a lot of cloud design patterns with a specific focus on Azure. However, these patterns will work well with AWS and GCP as well. If you are interested to view more, please go ahead and visit my channel. Also make sure to click on the subscribe button to be notified about the future videos. And for the like button, it's totally up to you. The static content pattern comes under design and implementation, data management, and performance efficiency categories of cloud design patterns. And this pattern is about deploying static content to a cloud-based storage, and then we can deliver them directly to the client. The cloud-based storage could be something like Azure Blob Storage or AWS S3. And we are going to see this in more details in this video. Related patterns to the static content hosting pattern is Valet Key Pattern. And hopefully we are going to make a video about it in future. Now let's go to the examples to help us understand static content hosting pattern better. Let's assume that we have a web application or website and we have clients that are using our web application. The web application could be implemented using Azure App Service. And as any web application, there is dynamic content as well as static content. Static content includes inline images, style sheets, client-side JavaScripts, or separate documents like PDF documents. Reaching to that point, this is exactly the challenge that the static content hosting pattern is trying to solve. And you might be looking at this architecture and say, so what? What might be the problem in this architecture? Everything looks normal. But if we pay more attention to this, we will be able to see that there are too many challenges in this architecture. And the first challenge here, we are using a compute service like Azure App Service instead of a storage account to serve static contents. And as you may already know, the compute service is way more expensive than the storage accounts, which is going to make us pay more money than we actually have to. So this is the first challenge, the cost. The second consideration we have in here is the performance. By having the compute service like Azure App Service has to serve both static content and dynamic content. Portion of the compute service power is going to be consumed to serve the static content. And then of course it's going to degrade the overall performance of that compute service. Or it might push you to scale it up to the next level and increase the tier, and then you pay more money as well. So the two main challenges we have in here is the cost and performance. And these are the challenges that the static content hosting pattern is trying to improve. Now let's see how we can use the static content hosting pattern to solve these challenges. As I said before, we are going to use a cloud storage. It could be either Azure Blob Storage or AWS S3, and then we are going to move the static content from the compute service from the Azure App Service and put it in the Azure Blob Storage instead. So when the clients are trying to use our website, the website is going to respond back with the URLs to the static contents hosted in the blob storage. And then the browser is going to grab this static content from our blob storage. So what we have done so far is offloading a static content from a compute service and put it in a storage account because they fit more in a storage account rather than a compute service. And this might remind you the gateway offloading pattern that we have talked about it before. And I'm going to put a link to the gateway offloading pattern if you are interested to review it. Now let's take it one step further. Let's assume that the Azure App Service is hosted in Australian region, as well as the blob storage as well. It might sound perfect if we have a user is connecting from Australia and trying to use our website. But what if a user from Brazil is trying to use our website? There are going to be a lot of network round trips between Brazil and the blob storage hosted in the Australian region, which is going to have a really high latency for the client. So what we can do instead is to use Content Delivery Network or CDN. Then the browser is going to direct or download the static content from the CDN instead of downloading it from the blob storage hosted in Australian region. CDN, if you are not familiar with it, it provides a geo-replication for resources in Azure Edge locations around the globe. So in our situation here, our static content is going to be replicated in Azure Edge locations, and if we have someone in Brazil trying to use our website, then the CDN is going to download this static content from an edge location closer to Brazil, which is going to be way faster than downloading it from the Azure Blob Storage hosted in Australia. And of course, we are going to have the Azure Blob Storage that's hosted in Australia at the origin of the CDN at all times. Now let's take it another step further. And let's talk about static website hosting, which is a feature available in Azure Blob Storage and AWS S3 as well. And what we are going to do in here is we are going to host our website in a blob storage. And then we are going to allow the client to access our website directly from the blob storage. Then we are going to have some serverless components like Functions app or Azure App Service to perform any API calls or any database calls that we might need to do. This is another style of using the Azure Blob Storage for static website hosting. And this might be helpful for you to implement in some scenarios. Now we have talked about the static content hosting pattern. Hopefully this is now clear enough for you. Now let's talk about some considerations you need to keep in mind when you use this pattern. You want to make sure that the cloud service supports HTTP or HTTPS, and you want to make sure that you are using the right protocol for your need. Also, you can use Content Delivery Network or CDN to provide maximum performance for your solution, as we talked about it before. Also, you want to make sure that the storage accounts are geo-replicated, so you don't need to use the IP because the IPs might change. What you need to use instead is the URL or endpoint of your storage accounts. Also, you want to avoid having a distributed static content. You don't want to have some static content hosted in a compute service and the rest of the static content hosted in a blob storage. It's going to make your life really hard if you decided to make a deployment for your static content. Also, you want to make sure that you have a public read access for the blob storage with no write access. You don't want to make anyone be able to change the static content of your website. Finally, you can use Valet Key Pattern to provide or control access to your resources hosted in a blob storage. Now let's see when you should use this pattern. If you want to minimize the hosting cost of your website by minimizing the cost or the tier of your compute service by offloading the static content to a blob storage or to a storage account. Also, when your web application is hosted on-prem and you want to increase the performance of the website, what you can do in this case is to lift and shift the static content from the on-prem data center to the blob storage. Also, when you want to locate your content around the globe, if you have a global audience or something and you want your content to be stored in more than one geographical area. Finally, when you want to monitor the cost or bandwidth usage of your website. Now let's see when you shouldn't use this pattern. When your web application tries to do some processing to the static content before delivering them to the client. Also, when the volume of your static content is very small, don't bother to implement this pattern. Now we are coming to the end of this video. I hope now it's clear for you what is the static content hosting pattern is about. What are the different implementation styles, how you can use it with the content delivery network to improve performance, and what is the static website hosting. Also, we talked about some considerations you need to consider when you implement this pattern, also when you should implement it and when you shouldn't. I hope you enjoyed this video. If you have any questions, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Claim Check Pattern. Claim Check Pattern comes under messaging category of cloud design patterns. Although this pattern comes primarily under messaging category, it still touches on other categories like performance enhancements and reliability, as we are going to see in details in this video. So what's going on in the Claim Check pattern is about splitting a large message content into a claim check and a payload. And then we are going to send the claim check to the messaging platform and then storing the payload in an external service. The external service could be a cloud-based storage, like a blob storage or even a database. And we are going to see this in more details in a minute. Let's say that we have a publisher and subscriber, and we are communicating between them asynchronously using Azure Service Bus queues. So the publisher is going to publish messages to Azure Service Bus queue, and from the other side, the subscriber is going to consume those messages from the queue. And so far we don't have any problems, until the publisher wants to send a really large message to the queue. And this is when it's gonna be problematic for us. Generally speaking, if we are going to send a really large message to a service bus, it's gonna consume a lot of resources and bandwidth of your message bus technology. And actually it's not even recommended to be used a large messages in a service bus technology, because this large message could slow down the entire solution. Also, there are different limits on the message sizes that you can send to different message bus technologies, and we are going to see them in more details in a minute. So we have two limits in here. First limit is the limit on the message size that we can send to the different Azure Service Bus technologies. And the second limit is if you even manage to get your messages to be just under those limits, it's still going to be a problem for your architecture, because one large message could slow down the entire solution, and it's going to consume a lot of resources and bandwidth of your architecture. Now let's have a quick look at the limits on the different Azure Service Bus technologies. And the first one we are going to talk about is the Azure Storage Queues, and the maximum message size it supports is up to 64Ks. While for Azure Service Bus queues, the maximum message size it supports is between 256Ks to 1 mega based on your tier. So if you are going to use the standard tier, the maximum message size is going to be 256Ks. And if you are going to use the premium tier, the maximum message size is going to be 1 mega. And similarly, Azure Service Bus Topics, which is exactly the same limits as Azure Service Bus queues. And finally, we have Azure Event Hub, which supports maximum message size to be 256Ks. So those are the different limits for different Azure Service Bus technologies. And bottom line is, there is a limit we cannot exceed. And the maximum limit we can use is 1 mega if we are going to use a premium tier for Azure Service Bus queues. And if you are in a situation that you want to send a really large message content or a large file on your message that exceeds the 1 mega, it's going to be a problem for your architecture and probably it's not going to work. Now let's get back to our example and see how we can use the claim check pattern to solve this problem. And what we are going to do is to introduce a blob storage or even a database or any other external storage that you would like to use. So when the publisher wants to send a really large file in a message, the publisher is going to send it in a different way. The publisher is going to split this message into two parts, the payload and the claim check. The payload in this case is the large file that we are talking about. So the publisher is going to store this large file directly into a blob storage, while keeping a reference to this file and put it in the message before putting it in the message queue. And then from the other side, when the subscriber receives this message, it will be able to get this file from the blob storage as well. So what we have done so far is we allowed our Azure Service Bus to able to process large files with the help of blob storage or any other external service like a SQL database, for example. And by doing this, we have overcome the Azure Service Bus limits we have just talked about in the previous slide. At the same time, we are allowing our solution to be able to process and handle large files through messaging architecture, with an assurance that it's not gonna slow down the entire solution, because what we are putting in the message is just a reference to the actual file location in the blob storage. That's exactly what this pattern is about. Now let's talk about some considerations you need to be aware of when you use this pattern. You need to consider the deletion strategy of those messages that you are going to store in the blob storage, if you are not planning to archive them. And primarily, there are two approaches you can follow, either to delete these messages synchronously, so when the subscriber receives a certain message and process the file from the blob storage, then the subscriber will go ahead and delete this file from the blob storage. And definitely it's gonna add a little bit more overhead and latency on the consumer to clean this up. Also, you can delete the messages asynchronously to be running in a dedicated separate process, to avoid having any overload or overhead or latency on the consumer side. Also, you need to be aware of that storing and retrieving files from a blob storage or any other external service might cause an overhead or latency to your solution. And one way you can overcome this is by checking your message size before moving forward. If your message size is small enough and way under the limits of Azure Service Bus queue, then feel free to submit your message to the Azure Service Bus queue directly, even though it might contain a small file. While if your message size is going to be over the limits of Azure Service Bus queues, then you need to consider implementing the claim check pattern and storing the file in a blob storage and keep its reference in the message before sending it to the Azure Service Bus queue. Now let's see when you should use this pattern. Whenever your message size is going to be way larger than the message limits of the message bus technology you are going to use. We've already seen the different limits of different Azure Service Bus components, and whenever a message size is going to exceed this limit, you need to consider implementing this pattern. You have no other option, otherwise the messages cannot be fit into the service bus if they are going to be over limit. Also, when you want to enforce security to your solution and make sure that only publisher and subscriber are only able to access a certain file in the blob storage. Now we are coming to the end of this video. I hope now it's clear for you what the claim check pattern is about, how we can use it, when we should use it, how we can use it to overcome the limitations of any message bus technology, how it can contribute to improve the performance and reliability of our application. And we have also talked about different use cases you need to be aware of to implement this pattern. I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hussein, and in this video we are going to talk about the ambassador pattern. Let's assume that our system is built on a microservices architecture, and it's hosted in containers. And one of our microservices, let's say microservice A, wants to initiate a remote service call to a remote service A. So it's going to be as easy and simple as sending a request to the remote service and receiving a response back. And this is just the first step that we can implement. Sending a request, receive a response. And there are other things that we need to consider and keep in mind while we implement this kind of a remote service calls. One of them is the retry mechanism. Let's assume a scenario that a remote service A has responded with a kind of error that tells you, try again later. And if you forwarded that error to the user is simply going to click the button one more time or sending the same request with the same input parameters again, hoping that remote service A will be able to process his request. So these are the kind of situations when you should consider implementing a retry mechanism to make the user experience better for the user and make your microservices implementation solid. And the perfect example I hope it's going to make the retry mechanism clearer for you is the database deadlock. Let's assume that you are trying to do a database operation, whether it's read or write, and you have received a database deadlock. And what the deadlock tells you that your process has got blocked because the database engine was busy executing other operations. And if you try to send your request or your query one more time, while the database engine is free, it should be able to get through and get executed. And here is the interesting part that's gonna show you how to use retry mechanism in the database deadlock scenario. And what you need to do is to catch a specific exception, the database deadlock exception. And within the exception handling, you send your request one more time to the database. You are hoping that other operations that had blocked your process are now executed and the database engine is free to process your request. This is what retry mechanism is about. There are certain kind of errors that we cannot do anything about them but try one more time. And this is what trying to handle here internally. Instead of sending the database deadlock exception to the user, and the user will just have to click on the button one more time, hoping that their request is going to get executed. Now let's talk about circuit breaking. And you can consider use circuit breaking pattern for a long-term failures that takes around 10-20 minutes or more, while retry is for the short-term failures. In a distributed environment, it's very likely that we can have any kind of errors. Network failure, or the remote service A is totally down. At that point, it's going to be pointless for microservice A to keep sends requests to the remote service, although it knows that it's already unavailable. It's not only that. Sooner or later, microservice A might be run out of resources because all of its resources has been allocated to try to initiate a remote service call for a service that's not available. So there is a risk for our microservice A to be unavailable as well. This is when circuit breaking pattern becomes really helpful. Circuit breaking pattern is going to stop microservice A from sending any requests to the remote service A as long as it's down. And once remote service A is back online again, microservice A should be able to send requests to the remote service A. And hopefully we are going to make a video in the future to cover circuit breaking pattern. Moving to the monitoring, and we should implement logging and monitoring for our microservice A to see what are the requests we are sending to the remote service and what are the responses we are receiving from them. Finally, we have security, including all security headers, encryption, SSL that needs to be implemented to secure the way microservice A communicates with the remote service A. So these are the different features we need to keep in mind when we create a remote service call. And let's assume we have implemented all of these features directly into microservice A. And in the microservices architecture, it's very common that you are going to have hundreds or even thousands of services in your system. And it's very likely that you are going to have more than one microservice that wants to call a remote service to get some results or to do a certain action. And we have already figured out things or features that we need to implement while we call a remote service through our implementation for microservice A. So it should be easy and straightforward for us to repeat the same logic over and over for microservice B and microservice C. And at this stage, all of our microservices in our system that requires to call a remote service will be compliant with the best practice. And here is the problem. We have gone against the dry principle, don't repeat yourself. By repeating the same logic over and over for every microservice in our system, we have gone against that principle. And also, Imagine a situation if we want to add a new security header, for example. You will have to do so for every microservice in our system. And what's more, you will have to do a deployment for every microservice got affected. So for such a tiny change, just adding a new security header, it requires you to do a massive amount of development work across multiple services, and to do massive deployments for different microservices in your system. And this is the challenge that the ambassador pattern is trying to solve. By pulling out all of these common features from the different microservices we have in our system and put them in a separate container, let's call it ambassador. Now when microservice A wants to make a call, it's going to send the request to the ambassador container, which is going to forward it to the right destination and then receiving the response back and send it through to the microservice A. So now we have kind of solved the duplication issue, and now we are compliant with the dry principle, since we have removed all of the duplication we used to have in our microservices and just put them in one container called the ambassador. But we have created another problem, if you may have noticed. Now we have a single point of failure, because if the ambassador container is down, all of our microservices will lose their ability to connect to any remote service. And we can resolve this by initiating multiple ambassador containers and make each of them dedicated for one of our microservices. So in this case, if ambassador A went down, it will only affect the microservice A ability to connect to remote services. Other ambassador containers will not be affected. Other microservices in our system will still be able to send requests to other remote services. And this is what ambassador pattern is about. Now let's talk about some considerations for the ambassador pattern. First of all, you should expect some latency to the overall remote service call, because you are adding a new layer in front of your microservices. However, you should aim to make that latency as minimum as possible. Moving to the nature of the operations and how it might affect the retry mechanism, you need to make sure that your operations are idempotent. Idempotent operation means it's an operation that can safely be executed more than once without making any harm or causing any data corruption. And this is something you should keep in mind when you apply your retry mechanism for different operations. You need to ask yourself, are those operations idempotent or not? Also, you need to give your clients or microservices an ability to pass some inputs or context to your ambassador container. For example, you should allow your microservices or clients to pass on number of retries that they would prefer for a certain operation. Maybe some microservices would prefer 3 or 7 or 5 retries, while other clients may tolerate 0 retries at all. You should allow your microservices to make that decision. Last consideration here is the style of the deployment. Whether you want to have one ambassador container shared across your microservices in your system, or you want to have separate ambassador containers and each of them is dedicated to one microservice in your architecture. Both are available for you. So when we should be using the ambassador pattern? When you have multiple microservices, different languages, frameworks, or different systems, and you want to apply a common set of connectivity features across all of them, this is the best use case for the ambassador pattern. Also, when you have multiple development teams and you want to have one team focus on the key features of your microservice and other team focus on the infrastructure connectivity aspect of things. Also, this is going to be very useful for you to use the ambassador pattern. Finally, if you have a legacy application that you cannot change easily and quickly, what you can do instead, you put an ambassador container in front of it, and the ambassador container is going to handle all the connectivity features you want to apply. Now let's talk about when you should not use the ambassador pattern. As we mentioned before, you should expect some network latency by using the ambassador pattern. And if the network performance is critical for you, you should not use the ambassador pattern. Also, if all of your microservices are built using a single language, it's going to be even better if you build a client library and distribute it to different teams and microservices. This is going to be more efficient than building an ambassador container. And finally, when your connectivity features cannot be common across your microservices and they are very different, then you should not use the ambassador pattern. Now we are coming to the end of this video. I hope now it's clear for you what the ambassador pattern is about, what the challenges it tries to solve, and when to use it and when not to use it as well. Thanks for watching. Hi everyone, my name is Hussein, and in this video we are going to talk about anti-corruption layer pattern, or some people know it as ACL pattern. And if we want to categorize where the ACL pattern should sit, we'll see that it sets under two categories, design and implementation, because as we will see, this pattern contributes a lot in how you design and implement the integration between two systems. And also the operational excellence aspects, because it's going to make the operational parts easier for you if you follow this pattern. And the ACL pattern is a layer that tries to communicate between two different subsystems without making any corruption to any of them. This layer could be a permanent layer or temporary layer, as we are going to see through the video. And it's good to mention that the ACL pattern is using adapter pattern and a facade pattern. You don't have to know these two patterns in details to continue watching this video, but it's good to know what other patterns ACL patterns depends on. Finally, our pattern ACL pattern is similar to Strangler Fig Pattern. Hopefully we are going to make a video about it in future. Now let's consider this scenario. Let's assume we have a legacy banking system that consists of three main services: client service, cache service, and transaction service. And there is some communications between these services. And then we have decided that we want to migrate our legacy banking system to a new system, and we have selected the client service to start with. Now, when we implemented the client service in the new banking system, it still will require some communications with the other two services. Client service will still need to communicate with the transaction service as well as the cache service. Now let's assume that all services either in the new system or in the legacy system are RESTful services. It's going to make the communication between them really easy and straightforward because all of them are using the same REST protocol. Then our client service is going to implement its ORM that updates the database based on REST protocol. Now let's make it a little bit difficult. What's going to happen if our legacy system uses SOAP instead of REST? And still, our client service still needs to communicate with the transaction service and the cache service. So the only option for us now is to go ahead and update the client service and allow it to communicate with other SOAP services. So let's go ahead and add SOAP implementation that will allow the client service to communicate with the cache service and transaction service. Now, what if we have planned that our new banking system will be based on RESTful services? We didn't have any plan to include any SOAP implementation in here. And we found ourselves that we just needed to implement SOAP implementation in our new banking system to allow it to communicate with other legacy system. So by adding this SOAP implementation here, we have corrupted the system architecture we have planned to do for the new banking system. And the corruption is in not something breaking feature or something is not working. The corruption in that we have added a new implementation for a certain technology, which is SOAP, that we don't really need in our new system. We just added it to allow it to communicate with other legacy system. This is the corruption, and this is what the ACL pattern is trying to solve. Now let's clean this up and see how we can use the ACL to resolve this issue. So let's place ACL in between of the new system and the legacy system. And our client service is going to communicate with the anti-corruption layer, and the ACL is going to communicate with the cache service and in the transaction service. Now let's have a look and see what's inside the ACL that's going to facilitate the integration between the new system and the legacy system. First thing we have in here is an API. This API is a RESTful API, which is going to make it easy for the client service to communicate with this RESTful API because this is pretty much the same protocol that the client service understands and using. Then we have a facade layer. This facade knows how to send SOAP request and receive a SOAP response, and how to deal with the SOAP services in our legacy system. And in between, we are going to add an adapter, which knows how to translate between these two protocols. And this is the value of the anti-corruption layer. We have allowed our new system to communicate with the old system without causing any corruption to any of these systems. And as we migrate other services from the legacy system to the new system, let's say we migrated the cache service to the new system. The communication between the client service and the cache service is going to be RESTful communication, because both of these services are RESTful services. And these services in our new system are going to use the ACL to communicate with the transaction service that still sits within the legacy system. And as we migrate the transaction service to the new system and have all of our internal communication been done using RESTful protocol, then we will find that our new system doesn't need to communicate with the ACL anymore, and we can drop these links and get rid of the ACL altogether as well. And this is how to use the ACL to help us to do a multi-stage system migration from a legacy system to a new system. And in this case, we have used the ACL temporarily. And also we can use the ACL layer permanently between two systems if we have a legacy system and a new system and they need to communicate with each other. And in this case, the ACL is going to live as long as these two systems has the need to communicate with each other. So we can implement the ACL permanently or temporarily, depending on our situation. Now let's talk about what are the different options we have to deploy and host the ACL. And we have three options: either to have it in a standalone deployment, or hosted in the new system, or in the legacy system. Now for the standalone style, pretty much similar to what we have seen before. We have a legacy system and a new system, and the ACL layer is going to be hosted in a separate container or service or whatever you like. And you can host the ACL on Azure Function or App Service or even AWS Lambda. Now let's see when you should consider using a standalone style deployment for your ACL. When you are doing a multi-stage system migration, pretty much similar to the examples that we have seen, or you want to build a permanent ACL between two systems, or when you have a certain requirement to have a specific scalability for your ACL layer and is going to scale away from the legacy system or the new system. And finally, you need to be aware of the extra cost that's gonna be included when you host your ACL in a standalone container or service. Then moving to the second style of deployment, deploying our ACL in the new system. And you should consider using this style of deployment when you have a requirement to build a permanent communication with the legacy system. And you want to avoid paying the extra cost that's going to be included for the standalone style of deployment. And finally, if you have no control over the legacy system. Then finally, we have the last style of deployment where we can deploy our ACL in the legacy system. And you should consider use this style of deployment if you want to have a permanent communication with the legacy system and avoid paying extra cost for a standalone deployments, and also you have no control over the new system. Now let's talk about some considerations you need to keep in mind when using the ACL. First of all, latency. We are adding a new layer between two service calls, and that includes a proxy and adapter that translate between two protocols, and we should expect some latency to happen. However, you should aim to keep that latency as minimum as possible. Then moving to the complexity. It's true that by using the ACL, we have avoided to cause any corruption to our systems, but we have added more services. We have added a proxy service, adapter, and facade implementations. And also, if you are going to deploy your ACL in a standalone deployment, you are going to have more Azure functions or app services that you need to be aware of. Then moving to scalability. If you are going to host your ACL in a standalone deployment, it's going to be really easy for you to scale it as much as you like, because it's going to be in a separate Azure services. But you need to think through what would be the case if you host your ACL in a new system or in a legacy system and you need to scale it as well. And this is a key point that will help you to decide what's the right deployment style for your ACL. Then let's move to multi-ACLs. If you remember, in our example we had two different technologies, SOAP and REST. And let's assume that we had a different message queue technologies as well. And what you should do is to implement a separate layer for the REST and SOAP communication and have a separate ACL for the message queue communications. You don't want to have all of these different technologies implemented in a single ACL, and you should consider have multi-ACL for this implementation. Also, you need to consider how you are going to monitor your ACL, especially if you are going to have a standalone style of deployment. Also, you need to be clear of the scope of your ACL, whether it's include or cover every single service in your system or just a certain amount of services. Finally, you need to consider whether you are going to have a permanent or temporary ACL. Now let's see when we should be using this pattern. As we've seen in the example, if you have a multi-stage system migration, you should consider using ACL. Also, if you have a multiple subsystems with different technologies. Similar to our example, we had a REST service and SOAP service, and we build an ACL to allow the communication between them without making any corruption to any of these services. Also, when you have different messaging processing systems. Finally, when you shouldn't use this pattern. When you don't have a significant difference in the technologies between different systems. Looking at this example here, all of these are RESTful services even though they are using different technologies for implementation. In this case, you should not use ACL pattern. Now we are coming to the end of this video. I hope now it's clear for you what is the anti-corruption pattern is about, when you should use it, when you shouldn't. I hope you enjoyed this video, and if you have any questions, please put it in the comments below, and thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Strangler Fig Pattern. And it enables you to migrate a legacy system to a new system while you maintain the system functionality up and running at all times. And it's good to know that anti-corruption layer is very close to Strangler Fig Pattern, and in this video we are going to see how we can use both in a migration scenario. Now let's dive into the example to help us understand this pattern better. Let's say that we have a banking system that consists of three simple services: client service, transaction service, and cash service. And let's say that we have a website that our clients are going to use to perform different sort of operations at our bank. And definitely the website has to communicate in a way or another with the backend services that we have in our system. So far everything is perfect until we decide that we want to migrate the backend services to a new system. And when this happens, we are going to migrate services one by one, and this is one of the powerful things about microservices architecture. So what we are gonna do is we are going to start with the client service and move it to the banking service. It's important to mention here that the client service in the new architecture is not the same as the client service that we used to have in our legacy system. For example, we might have one function in the client service in the legacy architecture, but in the new world, we want to split this function into multiple functions in the new system architecture. Or maybe the other way around, we might have multiple functions in the legacy system that we want to combine in one single function in the new architecture. And according to this, we will have to expect some kind of code changes to happen at the website while we are migrating our services from the legacy architecture to the new architecture, which is going to have many changes in different systems at the same time. And this is exactly the challenge that the Strangler Fig Pattern is trying to solve. Ideally, we don't want to have many patients on the table. We already are doing a big migration process for our backend services. We do want to introduce another change to happen at the website to making sure that the backend changes are done correctly and smoothly at the same time without breaking any of the client's functionalities. And to be honest, the website part is very critical because it's internet facing and it's customer facing, so any error might happen in this area will be a really big problem for our system. So the real challenge is, how are we going to make the migration process from a legacy system to the new system without making many changes to the website? And this is exactly what the Strangler Fig Pattern is trying to solve. Now let's see how can we use the Strangler Fig Pattern to solve this problem. Let's clean this up, and first thing we will have to do is to remove the direct communication between the website and the backend services. And we are going to introduce a facade layer. So the website is going to communicate with the facade layer, and then the facade layer is going to communicate with the backend services. I hear some of you already saying that by introducing another layer in our system architecture, we are going to expect a little bit more latency than usual, and this is absolutely correct. But the true benefit of having the facade layer in here is to isolate our website from any changes that are happening in the backend services. So when we migrate the client service to the new system architecture and we have done the changes that we need to do, either by combining or splitting certain functions, then we will have to reflect these changes in the facade layer. And the true benefit in here is that we are trying to avoid doing many changes in the website layer, and we pushed it down to make all of the changes that are related to the migration process in the facade layer. We are trying to avoid actually having a tightly coupling between our website and the migration process that we are having in our backend services. Because we need to expect rollbacks to happen or deployment failures and different sort of things that we don't want to be directly related to the website deployment. We want to make sure that both are going to be isolated at all times. And then we are going to carry on migrating other services like transaction service and cache service. And when we reach to this point, we can start thinking about decommissioning the legacy system because we don't have any services running into it anymore. And then at that point, the facade layer is going to communicate all together with all services in the new architecture. And then we can make a decision whether we keep the facade layer as it is in our architecture, or we can get rid of it completely and make our website directly communicate with the backend services in our system. This is how can we use the Strangler Fig Pattern to do a migration process between a legacy system and a new system without making many disturbance to the other systems. What I mean by other systems here is the website system, as we have talked about already. Now, let me take you one step back, and let's assume that after we have migrated the client service, that the client services already communicates with one of the services in the legacy architecture. And definitely it's not going to be a good idea to make the client service in the new architecture communicates directly with the cache service in the old architecture, because we know once it migrates to the new architecture, it's going to change. So what we are going to do instead is to use ACL or anti-corruption layer. So the client service is going to communicate with the anti-corruption layer, and then the anti-corruption layer is going to communicate with the cache service. And I have done a video about the anti-corruption layer pattern before, and I'm going to put a link for this video if you are interested to review it. This is just to give you an example how can we use different patterns to solve certain problem. Like in this scenario, we are going to use the Strangler Fig pattern alongside with the anti-corruption layer pattern to make our migration process easy. Now let's talk about some considerations you need to keep in mind when you use this pattern. You need to think of what you are going to do with the common services. Are you going to keep them in the legacy system, or you are going to migrate them to the new architecture, or probably you might need to duplicate them in both. So you will have to make your thinking which approach you are going to follow. Also, you need to think about the data stores, SQL, and any other blob storage that you might be using in this migration process. Also, when you build a new system, it's gonna be a good idea if you make it replacement ready or intercepted ready. Because at the end of the day, no system are going to stay with you forever. At a certain point of time, you'll have to replace it or you have to upgrade it. So as you build any new system, it's good to have the thinking at the back of your mind and make your application or your system ready to be replaced or ready to have a Strangler Fig pattern implementation on top of it. And as we said before, the facade pattern could be throwaway altogether after we have done the migration process, or we can evolve it to adapter layer for some legacy clients. Facade layer is not a one-off exercise that you will have to do just at the beginning of the migration process. It's something that you will have to maintain throughout the migration process Also, you want to make sure that the facade layer is not a single point of failure, or it won't cause any performance bottleneck for your overall architecture. Now let's see when you should use this pattern. When you want to migrate some backend services from a legacy system to a new system without making much disturbance to the front-end application part, which is the website in our example that we have talked about before. Now let's see when you shouldn't use this pattern. When the requests to your backend services cannot be intercepted. Also, when your system is very small, don't bother to implement this pattern. It's going to be much easier for you to replace your system altogether at one go rather than just implementing a Strangler Fig pattern. Now we are coming to the end of this video. I hope now it's clear for you what the Strangler Fig pattern is about, why we should be using it, how it can make the migration process much easier and simpler. And also we have talked about how we can migrate backend services without making much disturbance at the front-end part of our application. We have talked about some considerations you need to be aware of when you use this pattern, in addition to how you can combine this pattern alongside with the anti-corruption layer in your migration process. And we have talked about when you should use this pattern and when you shouldn't. I hope you enjoyed this video. If you have any questions, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hussein, and in this video we are going to talk about Backends-For-Frontends Pattern. This pattern lies under design and implementation category of cloud design patterns, and this pattern is about creating a separate backend service to be consumed by a specific front-end application or interface, and we are going to see this in more details in a minute. Also, it's good to mention other similar or related patterns to the Backends-For-Frontends pattern. Related patterns are Gateway Aggregation Pattern, Gateway Offloading Pattern, and Gateway Routing Pattern. Hopefully we are gonna make a video to talk about these patterns in future. And to help you to understand this pattern, let's consider this scenario. Let's assume that we have a web application that's been designed to work on desktop web browser. And we have a backend service, and of course, there is kind of communication is going to be required between the frontend and the backend service. And the backend service could be anything like Azure App Service, or Azure Functions App, or even AWS Lambda if you are more into AWS world. Then you have decided that you want to evolve your solution and implement a native mobile app for your solution. Be careful here, we are not talking about mobile web. We're talking about a native mobile app version of your solution. And since you have already done the backend service for your solution, then you are going to connect the mobile app to the backend service that you have already implemented. Then you decided you want to grow your solution and reach to more customers through different front ends, like Alexa, for example, and you decided to build a dedicated Alexa skill or Alexa app for your solution. And then you are going to connect the Alexa skill with the backend service of your solution. And for those who doesn't know what Alexa is a device developed by Amazon, similar to Google Home that's developed by Google. And these are voice-enabled devices that allows the customer to interact with these devices using their voice. However, some of these devices come with a screen to make the interaction with the user even better. So the user can still interact with these devices using their voice and touch interactions on the screen or scroll buttons on the device. And this is the new level of front ends that you need to be aware of when you design your solution. So we have a desktop or laptop, then we have a mobile or tablet devices, then we have voice-enabled devices like Alexa or Google Home. Also we have a smartwatch. So it's always good to consider what different front ends needs to be implemented for your solution before you start the implementation process. Now let's get back to our solution. And let's say that the desktop version wants to display the full profile details, including name, date of birth, city, phone number, email address. However, the mobile version is less interested in all of this information and just wants to display username, date of birth, and phone number. While the Alexa skill it just wants to display the first name of the user. Now let's look at the backend service and see what it's able to provide. As you can see here, the backend service is able to return the full profile details. So you might be asking, what is the big deal? We have the backend service that returns the full profile details, and then we have a different front ends that's going to display different amount of information as required. And this is exactly the challenge. Because if we decided to make a change to one of the front ends, the chance is really high that we might cause disruption to other front ends. And the reason for this is because all of these front ends depends on one general backend service. And this is the challenge that the Backends-For-Frontends pattern is trying to solve. Now let's see how can we resolve this challenge. So we are going to slice the general backend service into multiple services. Desktop backend service, mobile backend service, and Alexa backend service. And then we are going to connect the desktop front end with the desktop backend service, and the mobile front end with the mobile backend service, and the Alexa front end with the Alexa backend service. Now, the desktop backend service is going to return the full profile details that's exactly required to be displayed on the desktop front end of our solution, while the mobile backend service is going to return the amount of information that's exactly required to be displayed by the mobile front end, while the Alexa backend service is going to return just the first name that's required to use in the Alexa skill front end of the solution. Now, if we decided to make a change on the Alexa display and add more fields, then we can make updates to the Alexa backend service without worrying about making any disruption to other front ends of our solution. And this is the true value of the Backends-For-Frontends pattern. Now let's say that our solution wants to transfer money somewhere. Then we are going to implement a transfer module in all of our backend services. So from one perspective, we have improved our solution by implementing Backends-For-Frontends pattern, but from the other side, we have violated the RY principle, don't repeat yourself. And we have repeated the transfer module over and over across all of our backend services. And this is not the right way to do it. And the right way to do it is to pull out all of these transfer modules from the backend services and put them in a separate service. Let's call it transfer service. Then we are going to have communications between the different backend services and the transfer services or any other common service. Now you might be asking, what should stay in the backend service and what should be moved to the transfer service? And the answer for this is whether it's a business logic or a client-specific logic. Client-specific logic is the logic that's specific to a particular frontend. For example, Alexa backend service here is going to have the Alexa-specific logic that's required to run your solution on Alexa, similar to the mobile backend service and the desktop backend service. While the business logic will have the business rules or validations that needs to be applied across all of these backend services. And having this in mind, it will help you to determine what should stay on the backend service and what should be moved to other transfer service or common use service. Now let's talk about some considerations you need to keep in mind while using this pattern. First of all, the number of backend services. You need to be clear of how many front ends are required to be supported in your solution, and then you will get sense of how many backend services you will have to implement in your solution as well. Also, you need to decide whether to implement a backend for each front end or to have just a single backend for all front ends in your solution. As we have already seen before, in this situation, each front end is going to display different amount of information. Then it makes sense to have a separate backend service for each front end. However, if all of your front ends are going to display same amount of information, which is the full user profile, then it will make sense to have single backend service to be consumed from all of your front ends. Then you need to be aware of code duplication. While creating separate backend service for each front end, there is amount of code duplication is going to happen. However, you should aim to keep this as minimal as possible. Also, client-specific logic and business logic, as we have seen before, we should aim to have only client-specific logic stay in the backend service. Other business logic should be moved to other common services to be consumed in your solution. Then talking about development team responsibilities. Are you going to have each development team responsible for a backend service or making all development teams responsible for everything? That's depending on your operating model. Also, finally, the implementation effort. In addition to the coding and development, you need to be aware of the CI/CD pipeline, deployment effort, debugging effort that you will have to do when implementing or creating multiple backend services for your solution. Now let's see when you should use this pattern. When you have a significant development overhead in a general backend service. As we've seen before, we have a single backend service to be consumed from different front ends. Each front end is going to display different amount of information. Then accordingly, we will have to do a lot of customization in the backend service to be able to serve these different front ends. And this is exactly when you should consider using this pattern. Also, when you want to optimize the backend for a specific front end or a specific client interface, also sometimes you might find that another language is better for the backend service for a certain or a specific front end, like Alexa presentation language. Now let's see when you shouldn't use this pattern. If your interfaces are making the same request to the backend. Consider this scenario here. If all of your front ends are required to display the full profile details, then it doesn't make any sense to implement this pattern and have a separate service for each front end, as long as all of them is required to display the full profile details. And it will make more sense to implement a general backend service to be consumed from all front ends, as long as all of them are going to display the full profile details. Also, when you have only one interface in your interaction with the backend, if you have only a mobile app, then you don't need to implement this pattern. You don't have an Alexa skill, you don't have a desktop version or a smartwatch, just a mobile app, then you shouldn't use this pattern. Now we are coming to the end of this video. I hope now it's clear for you what the Backends-For-Frontends pattern is about, when you should use it, when you shouldn't. I hope you enjoyed this video. If you have any questions, please feel free to put it in the comments below, and thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Sidecar Pattern. Sidecar Pattern comes under many categories of cloud design patterns, like design and implementation, operational excellence, and data management. And this pattern is all about deploying certain modules of your application in a separate process or a separate containers to be totally isolated from your primary application, but at the same time, they can interact and provide additional functionality to your application. And we are going to see this in more details in this video. It's good to know that the Ambassador pattern is very close and related to the Sidecar pattern, and we have previously done a video for the Ambassador pattern, and I'm going to put a link for the Ambassador pattern if you are interested to review it. Before we dive into the examples, let's first understand from where the name comes from. Sidecar name came from motorcycle world, where you have the motorcycle and you have a sidecar. You can attach the sidecar, detach it, upgrade it. It's a totally separate component from your motorcycle. And if we are going to reflect this into our world, we will see that the motorcycle is going to be our primary application. That consists of the core functionalities of our system. And then in the sidecar, we are going to have the additional modules that are not part of the primary or core application, but they are still important to complement our application with additional functionalities and features. This is just to give you a little bit of idea from where the name comes from. Now let's dive into the example to help us understand this pattern better. Let's assume that the core functionalities or core services of our primary application consists of 3 services: client service, transaction service, and cache service. And we are going to have an additional modules which are not actually part of our core functionalities of the primary application, but they are important to complement our application and make it enterprise level. We are going to need a logging mechanism, configuration management, and a proxy as well. And by having these 3 modules implemented and hosted in the primary application, this is exactly the problem that we are trying to avoid. Because in case of any error happen in these modules in the runtime, it's going to affect the primary application, because usually both of them are going to be running on the same process, right? Also, the second challenge we have in here by having all of these modules implemented as part of the primary application is that it restricts us to write all of these modules with the same language as the primary application. And assume that if you have 10 different applications in your organization and you want to implement these 3 modules in all of these applications, you will have to duplicate these 3 modules across all applications in your organization, especially if they have been written with different languages. So this is the second challenge as well. And we might think that a quick fix for this problem might be to pull out these 3 modules and put them in a separate service. Then we are going to communicate between this new service and the primary application. But this is not going to be efficient, because by doing this, we are going to add some level of dependency between the services of our primary application and the new service that we have just created. So those are the different sort of challenges that we are facing if we try to host all of these 3 modules within the primary application. Now let's see, how can we use the sidecar pattern to resolve these problems? And what we are going to do is to host the primary application services in a separate container and then pull out these 3 modules and host them in a separate container, let's call it sidecar. And then we are going to have some sort of communication between the primary application and the sidecar. And by doing this, we have kind of resolved all of the challenges we have talked about before. Now the sidecar is running in a separate container, separate process, totally isolated from the primary application. In case any error or any corruption happened to the sidecar container, it wouldn't affect our primary application at all. Also, we should be able to use the sidecar container with all applications in our organization, because what we need to do is just to connect sidecar container with the primary application or any application we want to connect to it. And one important thing you need to know about is the sidecar container is very linked to the instance of the primary application, exactly similar to the motorcycle. We cannot share one sidecar across multiple motorcycles. It's not going to work. What's going to happen here, if we have more than one instance of our application, what we are going to have is to host multiple sidecar containers. Each of them is dedicated to one instance of our application. This is to ensure that each of our application instances is communicating and have a dedicated sidecar container that can coordinate with it. And also, one of the benefits of using the sidecar, if we decided to change the logging mechanism, instead of logging to a file, we are going to change the logs to applications in sites. And what we are going to do in this case is to change our repo and change it to write the logs to application in sites. And then when we want to initiate or create a new container from our sidecar repo, it's going to create all containers using the application insights logging rather than the file logging. Sidecar pattern is very common in container world, especially in Kubernetes. Sidecar is very well-known pattern in Kubernetes world. Now let's talk about some considerations you need to keep in mind when you use this pattern. First of all, the deployment or packaging. You need to think of how are you going to deploy or package the sidecar container to be deployed or packaged with your primary application instances. Also, it will be really helpful for you if you are going to implement or develop your sidecar container using a language or a framework agnostic technology. This will allow you to use it across multiple applications. Also, before you go ahead and implement or put a certain feature in a sidecar container, you need to think a little bit what else might be more efficient. Is it going to be better for you if you are going to host these features as a separate service, or maybe as a traditional daemon? Or in some scenarios, just to use a simple library, or a traditional extension mechanism. All of these might be a replacement to the sidecar. In other words, sidecar containers shouldn't be the only way to go if you want to pull certain modules out from your primary application, and you need to think carefully before you go ahead and put certain containers or certain modules in a sidecar container. Now let's see when you should use this pattern. When your primary application consists of a set of different languages and frameworks, and then the modules you are going to put in the sidecar, it's going to be consumed by all of these languages and frameworks within your primary application. Also, when you have a certain component developed by a remote team and you want to use it in your organization, then it will make more sense to put it in a certain container to be consumed by your primary application. Also, when you have a certain component that must be located in the same host as your primary application, Sidecar will be the perfect implementation for this scenario. Also, when you want to independently update modules in your Sidecar without affecting any modules in your primary application, this would be perfect for you to implement Sidecar Pattern. Now let's see when you shouldn't use this pattern. If the latency between the primary application and the sidecar cannot be tolerated, because we already know that we should expect a little bit of a latency when we pull out some modules from the primary application and put them in a sidecar and having the communication between them, there is a little bit of latency. And if your application cannot tolerate this latency, you shouldn't use this pattern. Also, if your application is very small, don't bother and implement this pattern. It's gonna add more complexity to your system and you wouldn't feel the benefit of this pattern. Also, if you have a different scaling requirements between the primary application instances and the sidecar instances. As we've already said, the sidecar is very linked to the primary application instances. If you are going to launch a new primary application instance, you are going to have a sidecar container being created for you as well. And if you have a different scalability requirements between the primary application and the sidecar containers, you shouldn't use this pattern. Now we are coming to the end of this video. I hope now it's clear for you what the sidecar pattern is about, where the name was coming from, when you should use this pattern, when you shouldn't, what are the different considerations you need to keep in mind when you implement sidecar pattern. I hope you enjoyed this video. If you have any questions, please feel free to put them in the comments below, and thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Throttling Pattern. Throttling Pattern comes under two categories of cloud design patterns: reliability and performance efficiency. And the main target of the throttling pattern is to control the consumption or the rate at which users are sending requests to our service. So if one of the users decided to send too many requests to our service, throttling pattern is going to stop them from doing this. And by doing so, we are going to improve the reliability of our system. Because if one particular user decided to send too many requests to our service, then our service will be too busy serving traffic coming from this particular user. And in a way or another, it's going to affect our service ability to serve traffic coming from other users. And throttling pattern help us to achieve this target. Also, it's good to know other related patterns to throttling pattern, like priority queue pattern and queue-based load leveling pattern. And I'm going to put links for these videos if you are interested to review them. Now let's dive into the example to help us understand throttling pattern better. Let's assume that we have a group of users that are interacting with our service. And our service could be hosted in Azure App Service or Azure API Management. And so far, our service is able to handle the requests coming from the clients perfectly without any problems. Then over time, our service become more and more popular and more clients now interacting with our service and sending more requests to our service. And somehow, our service is still able to handle these extra number of requests as a result of the large number of users that are interacting with our service. And here comes to the interesting point. What if a particular group of users decided to send more requests to our service? In a way or another, our service will allocate most of its resources to serve traffic coming from this particular user. And definitely, it's going to affect our serviceability from serving traffic coming from other users. And because we haven't specified any throttling limit on our service yet, then our service will be executing requests or rejecting requests randomly. Maybe this particular group of users are sending 1,000 requests per second, for example, and they are going to allocate most of the resources of our service. And most of these requests will be accepted. But for this particular user, if they are trying to send 5 requests per second, for example, those 5 requests might get rejected because our service is extremely busy serving traffic from this particular user. And then these other users are going to question themselves about our service reliability and whether or not they should continue using our service or maybe switch to something else. Because somehow we weren't been able to meet the SLA we have put in our contract. And this is exactly why Throttling Pattern is going to improve the reliability of your system, because you are specifying a quote or certain number of calls that each user is allowed to call for your system. And if they exceeded that limit, Throttling Pattern is going to block them from exceeding that limit. And I hear some of you already saying that, okay, maybe you are getting too many requests, then maybe let's go and auto-scale our service to the higher tier. And it's a really good point, but before we go ahead with auto-scaling, we need to ask ourselves a very important question. Does our service really need to be scaled to a higher tier, or it's a workaround because we haven't specified the proper throttling limits for our service yet? Sometimes this extra number of requests might be an attack, trying to penetrate through our service by doing a denial of service attack, flooding our service with too many requests, aiming to disable our service or make it unavailable to serve requests coming from other clients. And if this is the case, and we go ahead and scale our service to a higher tier, then guess what? The attacker is going to increase the number of requests they are going to send to our service, until we reach to the highest tier that we cannot scale anywhere further. Then the attacker is going to increase their number of requests, and sooner or later they will be able to penetrate through our service and make it unavailable to serve other user requests. So if it's a denial of service attack, auto-scaling will give you more time until your service becomes unavailable, but it will not solve the problem. Now, we have understand the problem. Now let's see how can we use the throttling pattern and what are the different strategies we can use to apply the throttling pattern in our solution. And the first strategy we have in here is we start to reject extra requests that we are receiving from a particular client. And we can do this out of the box in API management. You can specify limit call rate by key or by quote, and you specify this as easy as that. You specify number of calls or bandwidth over a period of time for a certain counter key, whether IP address or subscription key. And I'm going to put a link that covers the throttling limit and access restriction policies for the API management if you are interested to review this in more details. Then the second strategy we can do is to disable or degrade the functionality. So we disable or degrade the non-essential services to allow the essential services to take place and to be executed. And the best example I would like to give in here is YouTube or any other video streaming application. When it experiences an extreme workload, it will switch to view the videos in a lower resolution. This is to save the platform to perform other essential services or other essential functions, rather than just stopping altogether. So this could be one of the throttling strategies you could do in your solution as well. And the third strategy we have in here is you can use a queue-based load leveling pattern. So what's happening behind the scene when the users are sending too many requests to our service is that our service needs to send these requests to a data store. And any data store has a limited capacity. At a certain point, the data store will not be able to execute all of the incoming requests at the same time. And at some point, the SQL will start to send failures to our service, and then we are going to send it back to the user. And if we are going to use a queue-based load leveling pattern, which is as simple as buffering the requests in a message queue. In this case, it's going to be an Azure Service Bus. And then we have an Azure Functions app on the other side that's going to be triggered for every new message being placed in the queue. And then the Azure Functions app is going to go ahead and execute these requests against the SQL database. So queue-based load leveling pattern could be used as one of your throttling strategies. And I'm going to put a link for the queue-based load leveling pattern if you are interested to view it in more details. Also, other pattern you can use is to use a priority queue pattern. Usually if you are using a message queue, messages are going to be delivered in a FIFO way, first in, first out. However, in some cases you might have a really high priority message that you want it to be executed straight away. And the good thing about this is that Azure Service Bus supports priority queue. That, for example, when you get a high priority message, you can specify it's a high priority, so Azure Service Bus is going to place it at the top of the queue to be consumed before other messages that are already in the queue. So priority queue pattern could be implemented as well. And I'm going to put a link for priority queue pattern if you are interested to review it. And the last strategy you can do is deferring operations that are performed on a lower priority application. So as simple as we are going to choose what are the low priority services or features that our solution provides, and then we are going to stop them for a certain period of time. And let's have a look at this graph to help us understand it better. Let's assume that our service has 3 features, A, B, and C. And this is the time. And at T1, we started to hit the throttling limit. And what we are going to do in this case is we stop the execution of feature B because it's a non-essential feature. This is to allow our system or our services to continue the execution of other essential services. In this case, service A and service C. And when our resource utilization gets back to normal again, we will start the execution of feature B again. This is what we mean by deferring the execution of a certain or non-essential operation for a period of time. Also, throttling can be used for auto-scaling very well. All of us know that when we auto-scale a certain services, it doesn't scale immediately. It will take at least a few minutes for the new services to be effective. And throttling in here will help you to ensure that your system is still reliable and still able to serve user requests until the new auto-scaling services are effective. So we have time here and we have resource utilization, and at T1 we have hit the throttling limit and we have started to do the auto-scaling for our services. But until the auto-scaling become effective, we are going to slow down the execution on these resources to try to save our system from failure and make our system available to external users until the auto-scaling resources become available. So throttling in here will help you to ensure that your system doesn't fail while you are waiting for the auto-scaling resources to be effective. Now let's talk about some considerations you need to be aware of when you use this pattern. First of all, you need to be aware of throttling is an architectural decision. We already know that Azure makes it really easy for us to specify throttling limits for some services like API management or functions app. However, if you are going to follow up the strategy that's going to degrade certain services or disable certain features of your system as your throttling strategy, and you need to incorporate this early on in your system architecture and in your design phase. Also, when you apply throttling, you need to apply it as soon as possible. If you find that a particular user hits a throttling limit, you don't need to wait few minutes before taking the throttling action, because in these few minutes, the user can make really big harm to your system. So when your throttling limit has been reached, you need to apply your throttling strategy straight away. Also, it's good to let the user know that they have exceeded the throttling limit that we have specified in our system. Throttling doesn't always mean that we are under denial of service attack. It might be a genuine traffic coming from a valid user, but they are just sending too many requests to our service. And if we just let them know that they are sending too many requests to our service, probably we would be able to solve the problem before it's even started. And there is an HTTP response code which is 4 to 9 we can use, which is going to indicate that the user is sending too many requests to our service. Last point is that we can use throttling with auto-scaling as we have talked about already in the last slide. Now let's see when you should use this pattern. When you have an SLA for your system that you need to maintain. And in order to maintain this SLA, you need to make sure that not a particular user will be able to consume all of the computing power or resources of your service by sending too many requests to your service, which is going to affect your service to meet the SLA that you are compliant with other users. And also it will help you to handle the bursts in activities. If your system is expecting to get a really high requests at any point of time, Throttling Pattern will help you to handle these requests. Also, it will help you in cost optimization. Remember, earlier on in this video, I have talked about scaling up our resources to handle this extra workload that we are experiencing, which is going to have a more cost associated with it. So if you are implementing the proper throttling strategy, it's going to avoid you from this extra cost that you have to pay if you decided to scale your services up to the next tier. That's all you need to know about the throttling pattern. Now we are coming to the end of this video. I hope now it's clear for you what the throttling pattern is about, why it's important, how we are using it, what are the different throttling strategies you can use, what are the considerations you need to be aware of, and what are the best use cases to implement throttling pattern. I hope you enjoyed this video. If you have any questions, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Valet Key Pattern. Valet Key Pattern comes under two categories of cloud design patterns: data management and security. And by using Valet Key Pattern, we are going to provide a restricted access to our clients in order to allow them to use a specific resource in our environment. And we are going to see this in more details in this video. It's good to know other related patterns to the Valet Key Pattern, like GateKeeper Pattern and Static Content Hosting Pattern. Now, before we dive into the example, let's first understand from where the Valet Key name comes from and how it's related to the cloud design patterns. All of us are aware of the valet parking service in different hotels or casinos or different places. This is when you hand over your car keys to the valet and they take your car to park it, and then when you finish, they bring it back to you. But we have a security concern in here, that you will need to provide your car key, and in this case provide unrestricted access to your car to the valet in order to allow them to just park your car and bring it back to you. And for this concern, many car brands have developed Valet Key, which is a key that allows you to use your car with a restricted access. Like for example, you can't open the car boot, you can't drive your car further than 10 miles away, etc, etc. Of course, you are not going to use the valet key yourself because you are the owner of the car and you are going to use all of the features available in your car. But the valet key you are going to hand over to the valet to allow them to drive your car or park your car and bring it back to you when you finish whatever you are doing in the hotel. So if we are going to translate this to the cloud design pattern terms, we will see that the valet key is going to provide a restricted access to the user to use a certain resource for a limited amount of time. This is exactly what this pattern is about. Now, after we have understood a little bit of a context about the valet key, let's dive into the example to help us understand it better. Let's assume that we have a group of users that are using our website that's hosted in Azure App Service. And then our website deals with a lot of static data, like video files, audio files, PDFs, or books. All of these static contents are stored in a cloud storage. And the website is going to handle a lot of data movement operations, like fetching data from cloud storage, maybe streaming it to the client, or even uploading data from the client to the cloud storage. All of these data movement operations are going to absorb a lot of resources from our website, like compute, memory, and bandwidth. And if we take a closer look here, we will see that the cloud storage by itself can manage the upload and download of the data. Look at the blob storage or Amazon S3. You don't have to have an application to provide you with an access to the cloud storage, right? So instead of our application manages or handles the data movement of our files, we are going to allow our clients to directly interact with the cloud storage to grab the files that they want to get. And by doing this, we are going to get a lot of benefits. We are removing a lot of load from our website to handle these different sort of data movement operations. Also, we are going to improve our website scalability and performance. And as we are doing this, we have dropped a really important point. Now, our website is no longer in charge of who is going to access our data in the cloud storage. And this is exactly the challenge that the Valet Key Pattern is trying to solve. How are we going to allow our clients to have a direct access to our contents in a cloud storage? At the same time, we want our application or our website to be able to manage the access control to our contents in the cloud storage. Now, after we have talked about the problem and challenges, let's see how can we resolve this using the Valet Key Pattern. But before we get into that, let's revisit quickly that the cloud storage cannot perform any authentication for our clients, as well as authorization. So cloud storage in general cannot perform authentication or authorization for different users. The only thing that the cloud storage could use to provide a secure access to our content that are hosted in a cloud storage is by using a token that's been generated from our application, passed back to the client, and then the client is going to use this token to have a secure access to our content in the cloud storage. And let's have a look at this diagram I have got from Microsoft documentation that explains it really well. The first step we have in here is that the user is going to request access to a specific resource from our application. Then our application is going to perform some validations and then generate the key or token, then pass it back to the user. Then the user is going to use this token to have a secure access to our resource that's stored in the cloud storage. And by doing this, our application doesn't need to handle the data movement operations anymore, which is in a way or another is going to improve our application's performance and scalability. Also, it's important to mention here that this token is a time-limited token, which is valid only for a specific period of time. After this period of time, the key or token won't be valid to provide access to any resources anymore. Also, in some situations, we can invalidate the token from the application side. For example, when the user completes a download operation, then the user can notify the application that the download has been completed, then the application can invalidate the token to prevent any further access to our resources. So what we have done in here is we are using a token to provide a secure access to cloud storage, instead of working with a lot of permission management or access control management in addition to different locations to provide access to different users. We replaced all of them with using a secure token that could be generated from the application at runtime. That's what the Valet Key Pattern is about. Now let's talk about some considerations you need to be aware of when you use this pattern. And first of all is you need to manage the validity status and period of the key. Because at the end of the day, the key could get leaked or compromised, and then an attacker might have a valid key to perform valid operations on our content in the cloud storage. And to minimize this risk, you need to provide a validity period for the key as short as possible. That will just allow the user to perform their operations. And also you need to be very careful. If you specified a very short validity period for the key, you might prevent valid users from performing valid operations on the cloud storage. So you need to have a good balance between both. Also, you need to allow your users to renew the key before the validity period expires, if they are going to perform multiple operations on your cloud storage. Then moving on to the control, the level of access the key will provide, which means we'll provide the minimum access required to the resources. If the user is going to perform a read-only operation, then we need to provide them with a token that's only valid for a read-only operation. Similarly, if the user is going to upload some data, we only will need to provide them with a write-only key or write-only permission for the key. This will mitigate the risk of the key gets compromised that we have talked about in the first point. Also, you need to think of how are you going to control the user's behavior. You might have a valid user with a valid key, but you don't have any control on how much data they can upload to the cloud storage, or how many times they can download a certain file. Even if this might sound okay from security perspective, but this might end you up with a really huge operational cost, coming from the big data transfer that the client is going to use over and over. One thing you can use to mitigate this point is to notify the application after a certain operation has been completed. So the application is going to invalidate the key to prevent the user from performing multiple operations. Generally speaking, you need to validate or sanitize all uploaded data, because as we have said before, an attacker might get access to the key and might update some data that could compromise our system. Also from the other side, a valid user might upload some data that are invalid for our system. And you need to log or audit all operations that you are performing, whether download or upload or failures that are happening. Also, when you deliver the key, you want to make sure that you deliver the key securely over a secure channel using HTTPS to make sure that the attacker is not going to have an access to the key to use it in our system. Also, after you provide the client with a key, you want to make sure that your content is going to be transferred safely. We have two concepts in security when it comes to data: secure at rest and secure in transit. Now, we want to make sure that when our client is downloading our data from the blob storage, that this tunnel or this channel is secured. We can enforce it using SSL or TLS to make sure that our data will remain safe in transit as well. Now let's see when you should use this pattern. If you want to minimize resource loading or maximize performance, as we said before, by using this pattern, you are going to offload the data movement operations from your applications to the cloud storage, which is going to have a really positive performance effect on your application. Also, when you want to minimize the operational cost, because you are going to avoid your application to have many network hops between the client and your website, and from your website to the data storage or to the cloud storage. Also, when your clients always upload or download data to your system, it's going to be better for you to put it in a cloud storage rather than to your web application. Also, when your web application has a limited compute resources, it's going to be more efficient to use the cloud storage to host all of this static content. Also, when you want to avoid paying a lot of data transfer cost, because you might have your website in Australia region and your blob storage or your cloud storage in America region, it's going to be way more efficient to direct the users directly to download or upload data from the cloud storage directly. Now let's see when you shouldn't use this pattern. When your application must perform some tasks before storing the data on the cloud storage or before sending the data to the client. Some of these operations like validations or data transformation, if this is the case, then you cannot use this pattern. Also, you need to be aware of that some existing application cannot incorporate or work well with the Valet Key Pattern because of the way how they have been designed. If this is the case with your system, don't try to enforce using the Valet Key Pattern on it. We have already mentioned that you need to audit all sorts of operations like upload, downloads, or failures. But if your requirement to audit the number of times the data got accessed, then you shouldn't use this pattern. Also, if you want to limit the size of the data being uploaded to your cloud storage, then you cannot use this pattern. Now we are coming to the end of this video. I hope now it's clear for you what the Valet Key Pattern is about, from where the name was coming from, how is it relevant to the cloud design patterns, what are the different challenges that the Valet Key Pattern is trying to solve, how it can improve the performance of your application. We have also talked about some considerations you need to be aware of when you implement this pattern. Also, we have covered when you should use this pattern and when you shouldn't. I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Federated Identity Pattern. Federated identity comes under security category of cloud design patterns, and it's all about delegating authentication to an external identity provider so we don't have to implement an authentication module in our applications. And we are going to see this in more details in this video. Now let's dive straight into our example to help us understand this better. Let's say that you have a group of employees in your organization that need to access some internal applications as well as external applications. And let's say at this point we don't have any authentication being handled using Active Directory, so each of these applications has its own authentication module so they can authenticate the different requests coming from your employees. We all know this is not the best thing that could be done in here, but let's assume this is the case just to help me get my point across. And our employees will need an access to these different applications. And imagine what would be the life for them if they need to remember different username and password for each of these applications in order to get authenticated with. So we have 3 challenges we need to fix here. And first one, we have already mentioned it, that the user will need to remember different username and passwords for different applications in order to be authenticated with them. And in some big organizations, these applications could reach hundreds of applications. And imagine what would be the life for the employees if they need to maintain and manage hundreds of different usernames and passwords. So this is our first challenge. And our second challenge, we are exposing a security vulnerability. Imagine when a certain employee leaves the organization and we need to disable their access to all of these applications at once. And as I mentioned already, these applications could reach hundreds of applications in certain organizations. So it's going to take a bit of time till the application admins go through all of these apps and disable the certain employee access to all of them, which might take few hours or even days until we have disabled their access to all of the applications being used within the organization, whether they are internal applications or external applications. Also, we are missing a really important point, the audit or the assurance. If we want to be sure that a certain employee doesn't have access anymore to a certain application, there is no way for us to assure this unless to go manually and check these different applications to make sure that this certain employee doesn't have access anymore to access these applications, which is going to be a nightmare for the application admins. And the third challenge we have in here is we have a complicated user management process. From one side, the employee will have to communicate with 100 different app admins to provide him with an access to the application. And from the application admin side, they have to maintain these different requests coming from different employees to grant them access to different applications. So we are all agreed this is not the best thing we could implement in our organization, right? So these are the challenges, and now let's see how can we use the federated identity pattern to resolve these problems. Let's clean this up, and first thing we are going to do in here is to introduce one Azure component. In this case, let's say it's an Azure Active Directory. It could be any other identity provider. So our employees are going to be authenticated with Azure Active Directory. And by doing this, we have ticked off many boxes at the same time. Most importantly, we don't have to implement an authentication module for all of these applications because we handed it over to Azure Active Directory to do it for us. So it's going to make the implementation time faster and quicker for different applications we implement within the organization, since we don't have to implement an authentication module anymore within the application. And by doing this, by delegating the authentication from your internal applications to the Azure Active Directory, you are going to make a really clear separation between authentication and authorization. And this is a really big challenge for us, because in most cases, some people prefer to mix them together or don't really sense what is the difference between authentication and authorization. So if you are going to hand the authentication to Azure Active Directory, and maybe the authorization to a completely different service like Azure Key Vault, you have decoupled both authentication and authorization and make them really separate and decoupled from each other. Also, by doing this, by handing over the authentication to an Azure Active Directory, our app admin doesn't need to manage the user management for different apps anymore because we handed it over to someone else to prove the user identity, which is going to make the user management process much easier and efficient. So what are our options of using the identity provider? Are we only restricted to use Azure Active Directory? The answer is no. You can use your corporate directory or even on-premise federated service, or also you could use any identity provider that could provide you with STS token, Security Token Service. So you could use Yahoo, Facebook, Microsoft, Google, or Amazon account to get you this STS token while you are handing over the authentication module to them. Now let's have a closer look at what's happening behind the scene between one of these applications and Azure Active Directory in order to authenticate users with Azure Active Directory. And I've got this diagram from Microsoft documentation which explains it really well. And the first step we need to do is to build a trust relationship between our application and the identity provider. So our application would trust this identity provider to send the security token service to the application. And then when an employee wants to authenticate with our application, then they are going to get directed to the identity provider, which is Azure Active Directory in our example. And then the Azure Active Directory is going to send back STS token that the customer or employee can use to communicate with our service securely. Now our service doesn't need to worry about the authentication module anymore because we handed it over to Azure Active Directory to do all of the authentication work is required, and all what we are care about is receiving a valid STS token when the customer or when the employee is interacting with our system or our service. And this model is called claim-based authentication because we can get Active Directory to provide more attributes in the user token to be used within our application. Maybe the user role or certain permissions or certain attributes that might be required in a certain application. Now let's come back to our three challenges that we have talked about before and see if this pattern is going to resolve them or not. First, the challenge we had is the bad user experience, because the user used to manage different usernames and passwords for different applications. And by using this pattern, the user only will have to remember one username and password for their corporate directory, which is going to make the life much easier for them. Second, the challenge, the security vulnerability. If a certain employee leaves the organization, it's going to take us hours, if not days, to disable their account across all applications we have. Now, when we are using Azure Active Directory or any other identity provider, we can simply disable their account on the identity provider with a click of a button, and they lose access to all of these applications we have in the organization, or maybe external applications as well. And the third challenge we had is the application admins would need to do a lot of work to assign or authenticate the users with different applications. Now, by using the identity provider, application admins doesn't need to do this anymore. This is what this pattern is about and how we can use it to tick off all of these boxes we have mentioned before. Also, it's good to mention that handing over authentication to Azure Active Directory is not the only thing you could do. You could actually offload many services from your application or from your application code to other Azure components to make the life easier for your application. So for example, this is one of the diagrams I've got from the Gateway Offloading Pattern, and I'm going to put a link for this video if you are interested to review it. The Gateway Offloading Pattern is primarily about offloading certain modules from your application to other Azure components so you get to do less customization in your code. And in this example, we could offload authentication and authorization and token validity to Azure Active Directory. And also you could hand over the encryption to a key vault, throttling limit and token validation or SSL certificate to API management. Also, you could have an SSL certificate management for Azure Load Balancer. Also, you can offload the logging and monitoring to Application Insights and Log Analytics. So this is just to give you an idea that the authentication is not the only module that you could offload from your application code. You could offload many things even not mentioned in this diagram. This is just to give you an example or an idea to leverage what Azure has already provided for you before you start implementing it in your own code. Now let's talk about some considerations you need to keep in mind when you use this pattern. And the first thing you need to be aware of that authentication with an identity provider could be a single point of failure for your architecture. And if we take an Azure Active Directory as an example, and we look at what happened in the availability of Azure Active Directory globally twice this year, yes, it was a short period of time, but this is just to give you an idea that if the Azure Active Directory or your identity provider wasn't available, it will stop all of the authentication to all of your applications until the identity provider is back online again. And this is a really good consideration that you need to communicate with your business stakeholders. Yes, by offloading the authentication module from your application code to identity provider, it's going to provide a single sign-on features and really good user experience, but they need to be aware of what might happen wrong in terms of the availability of the Azure Active Directory or the identity provider. Also, by using an identity provider is going to offer you to have a role-based access control, which is going to allow you to have a more granular level of control of permissions. Also, you need to be aware of an important point. We mentioned already if you are using an Azure Active Directory, you can specify which attribute you need to send along with the STS token. This might sound okay if this is the internal identity provider that you own in your organization, but you need to be aware of that the external identity providers doesn't provide much information or much flexibility. In most cases, they might provide you only with the email address or the name of the user, and you need to be aware of that when you are going to authenticate with an external identity provider. Also, in some cases, your application might have trusted multiple identity providers to send the STS token. And if this is the case, you need to detect which identity provider needs to be used to direct user for authentication. And this is called home realm discovery. Now let's see when you should use this pattern. When you want to implement a single sign-on in your organization, it's going to be way better and easier for the employees to remember just the corporate username and password in order to authenticate with 100 different applications that are used within your organization. Also, it's going to make the security management much easier for you. If one employee leaves the organization, you can disable their access to all applications with a click of a button. Also, you can use this pattern to authenticate employees in your organization and your business partners without creating accounts in your Active Directory by having these federated identity that's going to work between both of your identity providers. Also, as we have already said before, many SaaS applications now offer federated identity as a way for authentication in their services, which is going to allow it easy for other users or other companies to integrate with them and use their identity providers to authenticate with these different SaaS applications. Now we are coming to the end of this video. I hope now it's clear for you what the federated identity pattern is about. What are the benefits of using it? What are the challenges it tries to solve? What are the different considerations you need to be aware of when you implement this pattern? I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching. Hi everyone! In this video we are going to talk about one of the cloud design patterns for Azure. And today's pattern is going to be deployment stamp. We can use deployment stamp with any Azure resource or component like a VM, app service, API management, function app, or even with a data store like SQL Server. And it allows us to deploy multiple independent copies of your solution across different regions or in the same region. And each individual copy is called a stamp. We are going to get a lot of benefits by using deployment stamp pattern. One of them is improving the scalability of your solution. Also, the ability to deploy multiple instances of your solution across different regions or in the same region, and also it allows you to separate and isolate your customers' data completely. Now let's go to the Azure portal and see how can we implement this pattern. Let's assume we have a scenario. We want to create an Azure App Service and a SQL database and Application Insights instance. And of course, we can go ahead and create all of these resources using the Azure portal. However, we are not going to do that. What we are going to do instead is we are going to use an ARM template to create all of these resources for us, because it's very mandatory for using a deployment stamp to have ARM template for our stamp or our resources that we want to redeploy in different regions. Now, it's important to mention here that this ARM template will create a SQL database in general tier. So you might need to expect that you're gonna spend some money on this. If you are not ready, just follow along with me and don't create these resources. So let's go ahead and deploy to Azure. Now let's fill in the parameters for this template. Let's select a resource group. Probably I need to create a new one. Let's call it stamp1. And let's select a username and password for our SQL database. It's important to mention here that the password has to be complex, otherwise the deployment of this template is going to fail. Now let's go ahead and create this template. Now my deployment is completed, and the first thing I need to do now is to go to the SQL database and scale it down. Because if you remember, this template that we have used is going to create a SQL database in a general tier, and we don't want to pay for that. So let's go ahead to the resource group, and let's select the database instance, and let's scale it down to the basic tier, which is going to be much more cheaper. And let's go ahead and apply our changes. My SQL database instance changes has took place. Now let's go back to the resource groups and see what resources has been created for us after we deployed the template. We have a stamp1 resource group here, and we have got application insights instance, app service plan, SQL database, SQL server, and app service. So our architecture for this solution is pretty simple and straightforward. We have an app service hosted in an app service plan talking to a SQL database instance. But we all know that leaving our architecture like this is going to have a lot of limitations for our solution. And here is why deployment stamp pattern comes really helpful and handy, because it tries to solve all of these challenges and limitations of the architecture we are having at the moment. Now let's talk a little bit about the limitations of this architecture. First of all, scalability. Our architecture has an option to scale up, but it doesn't have an option to scale out across multiple instances. Since we have only one SQL instance and one Azure app service, we only can scale our resources up to the next tier. But sooner or later, once we get a higher workload, we are going to reach the maximum scalability limit for those resources. Also, we cannot separate customers' data or isolate customers' data. Some clients have a requirement to keep their data isolated from other people's data, and our current architecture cannot fulfill their requirements. Also, we have the ability to handle single and multi-tenant instances. Some clients do have a requirement to own the infrastructure underlying the working solution. This is to make sure that other customers' workloads are not going to interfere or slow down their own workloads. And our current architecture just supports some multi-tenant instances where everyone's data is stored in the same SQL instance. Moving to the update frequency. Some clients may tolerate frequent updates to their solution without any problem, while other customers might have a really strict requirements for the update frequency, and they can only accept one update every fortnight or every month. And it's going to be a challenge for us to meet both people requirements if we have everything in one instance. Finally, we have geographical restrictions. Some industries like finance or health might have requirements that restrict the data to be stored within the country's borders. And our current architecture is hosted in Australia East, then it won't be compliant for a global deployment for many countries around the world. So those are the limitations of the current architecture, and those are the challenges that the deployment stamp pattern is trying to solve. And now we are going to see how deployment stamp pattern is going to help us resolve all of these limitations. Now let's go back to the Azure portal and deploy one more deployment for these resources. Let's create a new resource group, call it stamp2. Could be in Australia East region or any other region. I'm going to leave it in Australia East and select a username as well and password. And remember, it has to be a complex password. And let's go ahead and create these resources. Now my deployment is completed, and the first thing I need to do now is to go to the SQL instance and scale it down. Scale it to the basic tier and go ahead and apply our changes. Now my SQL changes has completed. Now let's go back to the resource group and open the app service. And let's go ahead and browse this app service. And doing the same with the stamp1 resource group, going to the app service, and let's browse it as well. As you may notice here, these two web pages looks really identical, and it makes sense because it runs from the same sample. The only difference you may notice here is the URL difference, because each of these web pages is hosted in a different app service. So this is one of the scenarios that deployment stamp pattern can help to resolve. We can have as many stamps as we would like and assign each stamp to a set of customers or a single customer based on our requirements and their compliance requirements. And there is nothing wrong with that. Look at Dynamics 365 or Office 365, there is a URL difference for each client to join their tenant on Office 365. So some deployments you may be fine to having different URLs for different customers to log to their tenants. Now let's have a look at the deployment stamp architecture, and I've got this diagram from Azure Online documentation. As you can see here, we can have as many stamps as we would like, either in the same region or in different regions. Each stamp will have its own Azure App Service and the SQL database instance, and it's totally isolated from other stamps. And it's going to be up to us to choose which stamp is going to support a multi-tenant deployment like stamp1, or which stamps are going to support a single tenant deployment like stamp2. And each of these stamps could have a different computing or processing power based on the requirements or based on the performance metrics. And as I mentioned before, each of these stamps will have its own URL that clients have to use in order to log into your system. However, in some situations, you might have a requirement that requires you to have a single URL for all clients to use across all stamps. And then you have to manage the traffic internally to route each client to the right tenant or right stamp. Let's go ahead and see how can we do this. Now let's go back to the Azure portal and create an Azure front door, which is going to help us to manage traffic routing between clients and different stamps that we have in our solution. And I'm going to create a new resource group for Azure Front Door. I'm gonna call it Front Door Resource Group. And I'm going to leave it in US East region. Now moving to the configuration. First thing we need to do here is to specify the front end or the host name for our front end. And this is going to be the single URL that all clients have to use in order to access our solution across different stamps. So I'm going to call it deployment stamp URLs. And then leaving everything else to the default values. Now let's add backend pools. And given that we have two stamps for our solution, we are going to add two backend pools for this configuration. First one, we are going to call it backend pool 1. And in the backend pool, I'm going to choose app service and choose the host name, one of the Azure app services that we have, and leaving all values to the default values, changing the weight here to be 100. And let's add this backend pool. And again, leaving all of the configuration to the default values. And again, let's go ahead and add the second pool, backend pool. And let's select Azure App Service and let's select the second URL for our second stamp. And change the weight here to be 100 as well. And let's add the backend pool as well. Now let's go ahead and add routing rules. And I'm going to make it really simple, as if the traffic is coming on HTTP, I am going to route it to a certain stamp. And if the traffic is coming on HTTPS, I'm going to route it to a different stamp. So I'm going to call this one stamp1 routing through HTTP only. This is a front-end domain that we've specified for our front door. And in the backend pool here, I'm going to select the backend pool 1 and select HTTP only traffic. And let's add this routing rule. And let's go ahead and add another one for HTTP traffic. Stamp2 routing, and we select here HTTPS, and again the same front-end domain, and for the backend pool it's going to be backend pool 2, and select HTTPS traffic only. And let's go ahead and add this rule as well. Now let's go to next step, and let's review and create our Azure front door. Now my deployment is completed. Let's go to the Azure front door and let's browse to the front-end URL. And I'm going to browse it twice. One with HTTPS protocol, like this page, and the other one with HTTP only, because this is how I configured the routing configuration. Now we can't tell for sure if our routing configuration is working or not, given that it is still preserved the same front-end URL in both situations. So I'm going to go back to the Azure front door and do some routing configuration changes to help us see if our routing configuration is working or not. So let's go to the routing configuration and let's change it instead of forward to redirect. Before that, I need to copy the URL first. So let's go to the backend pool 1 and copy the backend host name. Then go to stamp rule routing 1 and change it to redirect. HTTP only traffic and replace the destination host with that URL. And let's go ahead and update this routing rule. And let's do the same with the stamp2 routing. But first I need to copy the URL of stamp2 and then go to stamp2 routing, change it to redirect HTTPS traffic and replace destination host with that URL. And let's save our changes. Now my changes is completed. Now let's go to the HTTPS URL and let's refresh this page. And as you can see here, the URL redirected to one of the stamps. And let's do the same with the HTTP traffic only. Again, it gets redirected to a different stamp. This is to prove that our routing configuration is working well, and it's going to direct the traffic to different stamps based on the calling protocol, whether it's HTTP or HTTPS. So this was a really easy, simple, straightforward routing configuration, but in real life scenarios you will have more complex routing configurations than that. That's why you will have to use of the rules engine configuration and bind it to the routing rules. So let's have a look. And let's go ahead and add a new engine configuration. Let's call it engine 1 and let's call the rule name rule 1. And in here, as you can see, we can specify different conditions based on device type, header, body, URL, path, whatever you like. And if the request met that condition, it's going to route the traffic to this destination based on our configuration. We can specify whether forward or redirect traffic to which backend pool and what protocol it will support. And this is not an Azure front door course, so we are not going to cover the engine configurations in detail, but you get the idea. It's working the same way the routing configuration works as I showed you in the HTTP and HTTPS traffic routing. Now let's have a look at the architecture after we have added the Azure front door to our solution. So this is the architecture diagram. I've got it from Azure documentation. And as you can see here, the front door plays as the single URL that all clients are going to use to access your solution. And based on the routing configurations you specify in here, you are going to route clients to different stamps. Also, the diagram shows you here a different scenario. If you are using an API management or Cosmos database, you are still able to route clients to different instances based on the routing configurations you specify in the front door. However, this orange section is not required in our solution that I demonstrated. Now you have two options. whether you are happy for your clients to use different URLs to access their stamps directly, or you want them to use a single URL to access your solution, and then you are going to route them internally to their stamps based on the routing configurations you specify in Azure Front Door. Both options are available for you based on your preference and your requirements. Now I hear some of you asking, what is the best way we can use to deploy different stamps across regions? It's okay to deploy it manually if we have only 2 stamps, like I did in the beginning of this video. But what if we have hundreds or thousands of stamps? Are we supposed to do it and deploy it manually as well? And the answer is no. We can use Azure Deployment Manager to help us automate the deployment for our stamps across regions and for different resources. Deployment Manager primarily using 4 files: topology template and its parameter file, and rollout template and its parameter file. The topology template answers the question of what resources needs to be deployed and where we need to deploy them, while the rollout template answers the question of when we need to apply those changes and the pre-deployment and post-deployment conditions that needs to be applied. However, I am not going to demonstrate Deployment Manager in this video, but I am going to refer you to the Deployment Manager overview link in here, which is going to cover these 2 diagrams in more details. And I strongly recommend you to do this Deployment Manager tutorial if you are keen to learn more about it. Now let's have a look at this topology template. As you can see here, it includes different regions for our solution, and in each region includes different resources that needs to be deployed. This is going to make it easier for us if we wanted to launch a new region or have a new stamp for our solution, or when we want to deploy a particular service in one region. Now let's talk about some of the considerations you need to keep in mind when you implement deployment stamp pattern. First of all, deployment. As we said before, you should have templates for all resources you plan to deploy using deployment stamp pattern. Otherwise, it's going to be really difficult for you to have or create all of these resources manually for each stamp. Then we have cross-stamp operations. This is when you have some requirements to run some queries across all stamps in your solution. And to achieve this, you can implement 2 ways. Either to implement or run each query in every stamp individually and then you aggregate the result at the end. Or you could consider replicate the data from each stamp to a central place like a data warehouse or something, and then you can generate your consolidated reports from the data warehouse. Moving to the scale-out policies. You need to keep an eye on each stamp individually and see the consumption of each stamp and the performance metrics. Then you can automatically determine when is the right time to provision a new stamp and then redirect the new clients to the newly created stamp. Then we have cost, and something important to keep an eye on, because deployment stamp pattern deploying multiple copies of the infrastructure components. And for every new stamp you are deploying, the cost is going to increase, so it's something important to keep an eye on. Then we have moving between stamps. We already know that one of the powerful features about deployment stamp pattern is that each stamp is deployed and operated individually. And if you have some requirement to move a tenant or a client from one stamp to another, it's going to be really difficult for you, and it's going to increase the complexity of your solution. Then we have traffic routing, and as we said before, we need to consider the traffic routing mechanism to route different clients to different stamps in our solution. Then we have shared components. We need to consider using CDN if we have a shared components that needs to be used or accessed from all stamps in our solution. Now let's talk about when we should be using deployment stamp pattern. First of all, when we have a natural limit on scalability. Like SQL Server, for example, you can scale your SQL instance up till a certain limit, and after that you cannot scale it up anymore. And this is one example when you should consider using a deployment stamp pattern. Also, when you have some compliance requirements that requires you to store some client's data away from other clients. Also, when you want to have some tenants of your solution running on a particular version, which is different than the other tenants of your solution. And this is a very useful use case you need to consider for deployment stamp pattern. Also, when you have a multi-region application, when you want to direct people or clients from certain countries to a certain stamps. Finally, when you want to achieve resiliency during outages. Stamps by nature are isolated, so if one stamp is down for any reason, other stamps will not be affected. Now let's see when we should not use deployment stamp pattern. If we have a simple solution, or if we have a system components that are really easy to scale out or up within a single instance, or when we need to replicate all the data across all deployed stamps, we should consider other patterns like Geode Pattern, and hopefully we are going to cover it in the future. Also, when we have a requirement or need to scale a certain components of our architecture and leave other components without scaling, deployment stamps are not going to be helpful in this scenario. Finally, if we have a static content solutions, you shouldn't be using deployment stamp with it. And at the end here, I have put a reference for the deployment stamp pattern in the Azure Online documentation if you want to go have a read. Now let's go back to the Azure portal and clean up all of these resources and go ahead and delete them. Now we are coming to the end of this video. I hope you have learned what deployment stamp pattern is about and how you can implement it in your solution. If you have any questions, please feel free to put it in the comments below, and thanks for watching. Hi everyone, my name is Hussain, and in this video we are going to talk about the Geode Pattern. Geode Pattern comes under reliability and operational excellence categories of cloud design patterns. And in the Geode Pattern, we are deploying a collection of backend services into a set of geographical nodes. Each of these nodes will be able to handle any request from any client around the globe. And we are going to see this in more details in this video. And while we are here at the definition of our pattern, let's see from where the Geode name comes from. It came from the first part of geographical word and the last part of nodes word, and when we combine them together, we are going to have Geode. And this is where the Geode pattern name comes from. Also, we are going to see that the ambassador pattern is very related to the Geode pattern. Also, deployment stamp pattern is very close to the Geode pattern. And we are going to see what is the key difference between the deployment stamp and the Geode pattern in this video. Now let's dive into the example to help us understand the Geode pattern better. Let's say that we have a website and we have deployed our website in Azure. And we have deployed our front end in Azure App Service, and we have deployed the backend in Azure Functions App, and we have deployed our database in Azure SQL Database, and we have hosted all of these components in US East region. Then we will have external clients that are interacting with our website. So far, so good. Over time, our website becomes more and more popular, and more users now are interacting with our website, sending more traffic and more requests to our website, which is great from a business perspective. But from the architecture perspective, we need to question ourselves. Is our website will be able to handle this extra workload we are receiving as a result of the increasing number of users that are using our website? And whatever the answer would be, we don't have an issue, because this is one of the powerful things of deploying our application in the cloud. We can easily scale up our application components to the higher tier or to the highest tier to allow our website to handle this extra workload we are receiving. So we can scale up the Azure App Service to a higher tier, similarly to the Function App, and also for the SQL database. So definitely by scaling up our services, it will allow us to react really quickly to the increased number of users that are using our website. But the problem with the scaling up, it's not reliable or it's not sustainable solution. And I will tell you why. Scaling up has a limit. And yes, we have a wide variety of tiers to choose from to deploy our different application components based on the workload we are getting. But at the end of the day, these tiers has limits. Imagine what would happen if you have scaled up your application components to the highest tier available in the cloud, and still your website or your different components are not able to handle the extra workload you are receiving. Then what would be the solution? This is one of the main things about the scaling up that you need to be aware of. Yes, scaling up will save the day if you are receiving a high workload from your client, but it's not a reliable or sustainable solution that you can rely on, especially if your website is a global website, has millions of users. So in other words, scaling up can save you in a short term, however you need to have another strategy for the long term. And what we can do is to allow our application to scale out across multiple regions to be able to handle this extra workload. So we have two options of scalability: scaling up and scaling out. Scaling up is limited to the computing capacity offered by Azure. However, scaling out has no limit. And let's say that we are going to use Australia East region to deploy another node of our application. So we are going to deploy an Azure App Service, an Azure Functions app, and let's say Azure SQL database. Then we can use something like Azure Global Front Door to direct the traffic coming from a particular users to the Azure region that are closer to these users. Now, the problem of this architecture is that we have a local database in each of these regions. Like Australia East region data will know nothing about the data that's stored in US East region. And we don't want to do that. We want to allow the data that's been written to the SQL server in Australia East region to be available in US East region as well. So according to this, we will take off the SQL database from Australia East region. And what we can do instead is to make our Functions app in Australia East region to communicate with the SQL server that's hosted in US East region. Similarly, for the Azure App Service that's hosted in Australia East region, it's going to communicate or read the data from SQL Server that's hosted in US East region. So by doing this, we can scale out our application to multiple nodes and deploy them in different regions, and then we are going to direct the users to the region that's closest to them, which is going to provide the lowest latency to the end user. At the same time, we are going to have all the data from all regions stored in one SQL server in one particular region. So we can access the same data from any node or from any part in the world. I hear what you are saying, it's a bottleneck in the architecture, and we are going to resolve it later on. And if we are going to follow the same pattern, and we are going to deploy another node of our application in UK region, then we are going to deploy an Azure App Service, an Azure Functions app. Then by using a service like Azure Front Door, we will be able to direct the traffic coming from users in Europe, for example, to use or communicate the UK node of our solution. Also, we are going to make the Functions app hosted in UK region to communicate with the SQL database that's hosted in US East region. Similarly for the Azure App Service in UK region as well. And you might have noticed that we are introducing too many traffic now to our SQL database that's hosted in US East region. And that's absolutely true. So we can go with the other option by scaling up the SQL database to a highest tier, or even apply the sharding techniques to the SQL database instance. But there is another problem. We have created a single point of failure on this SQL server that's hosted in US East region. In any unlikely event the US East region become unavailable, or the SQL server went down for any reason, all of the other nodes will not be able to perform its function and the application will not responding to the end user. So pretty much we haven't done anything useful by splitting or scaling out the application to multiple nodes around the globe. And this is exactly the challenge that the Geode pattern is trying to solve. Geode pattern will allow you to scale out your application and deploy them in multiple nodes around the globe, without having a primary node that's running the show. So in this architecture here, we have the US East region is the primary or master node, because if it's unavailable, pretty much all other nodes becomes ineffective. And the good thing about the Geode pattern is that there is no primary node or there is no master node, and every node in the architecture will have equal responsibilities and importance. And in any event, any of the nodes went down, it won't stop the whole solution. And this is one of the powerful things about the Geode pattern. Now let's have a look at a high-level architecture on the world map first, and then we are going to jump into the details later on. Assuming that we have a global website like Amazon or Google and we have deployed it in multiple regions, each of these regions will deploy a node of our application. Each node has an Azure App Service, Azure Functions app, and a database. But the key difference here, the database will not be a SQL database. And then there are going to be some kind of synchronization between the database instances in different regions or different nodes to allow the data or changes happens in one node to be replicated to other nodes. So we're ending up having no primary node for our architecture. And in an unlikely event, we lost one node altogether. It's not a big problem for us because the data that's primarily written in this node, it's already replicated to all other nodes in our architecture. And this is exactly what the Geode pattern is about. So we are going to host our application in 4 different regions: Asia Pacific, United States, Europe, and South America. Each of these regions hosts the same components: Azure API Management, Functions app, whatever you like. But the key difference here is in the database. We are going to use a Cosmos database instead of SQL Server. So we are going to host and deploy Cosmos DB in each region. And one of the powerful things about Cosmos DB, it will have an option to allow this synchronization to happen behind the scene. So the changes that you write to Asia Pacific region, it's going to be replicated behind the scene to the Cosmos DB instance hosted in United States and Europe and South America, and the other way around. Similarly, the changes that have been written to Cosmos DB instance in Europe, it's going to be replicated to South America and United States and Asia Pacific instances. So there is no primary or master node in this architecture here. All these 4 nodes have equal importance and equal responsibilities in our architecture. And then we are going to have an Azure front door which is going to accept traffic from all users around the globe, and it's going to direct the users to the node that's closest to their location. For example, if the user is connecting from Sydney, the front door is going to send them to Asia Pacific region or node because this is the most closest node to the user. And similarly, if someone is trying to connect to us from Brazil, Azure front door is going to direct them to the South American node because it's the closest node to the user. Now let's talk about high availability architecture or a disaster recovery scenario. And let's say that the Asia Pacific region for some reason become completely unavailable. Then when someone is trying to connect from Sydney, the Azure front door is going to direct them to the other nodes that are closer to their location. And given that Asia Pacific region is not available anymore, then Azure front door might send the user to the United States or South America region, which is going to ensure the high availability of our solution. And I hear some of you already saying, what about the data that the user has already written before to the Cosmos DB in the Asia Pacific region? What's going to happen to this data? And this is one of the things that I've highlighted before. One of the powerful features of using Cosmos DB is that it will allow us to do a synchronization behind the scene between different Cosmos instances in different regions. So all of the data that has been written or changed in the Cosmos DB in the Asia Pacific region has been already replicated to the Cosmos DB instance in the United States and Cosmos DB instance in Europe and Cosmos DB instance in South America. So when someone from Sydney is trying to use our website, the Azure front door is going to redirect them to either of these nodes, United States or South America. And from our perspective, it doesn't matter because the data that has been changed in Asia Pacific has been already replicated in the United States, and the user will find them when they connect to the United States node. Similarly, the data also has been replicated to South America node, and the user will find them if he had connected to South America node. So Geode pattern will ensure the high availability, resiliency, reliability of your architecture, and you must implement this pattern if you have a global website that's been used from users around the globe. And for a solid Geode pattern implementation, you need to implement additional things as well, like DevOps. To be able to rapidly deploy your latest components or latest version across different nodes around the globe, you need to have a really solid DevOps practice and tools that will allow you to do this. Then moving on to the auto-scaling. And yes, we have auto-scaled or scaled out our application from one region to multiple nodes around the globe. But you need to think of the auto-scaling strategy for each of these nodes separately, whether you are going to scale them up or even scale them out. Then moving on to the Azure front door or front-end service that you are going to use, and this is what's going to direct the users to the closest node based on their location. And in addition to the Azure front door, you need to consider using Cosmos DB, something that will allow you to replicate the data store across different nodes around the globe. Also, you need to consider the serverless technologies as much as possible in this architecture, because it's gonna benefit you a lot and it's gonna save you a lot of money. Imagine what would be the case if you're deploying your application in VMs and you're deploying them in multiple nodes. It's gonna cost you a lot of money whether you consume that capacity or not. But the good thing about the serverless technologies is that you are going to pay for what you use, which is gonna be perfect for the Geode implementation. And finally, we have an API layer, which is not mandatory, but it's gonna add a robust API integration layer for your architecture. And from the API, you can have a scalability to multiple regions from the API management itself. If you are running it on a premium tier, you are able to deploy unlimited API management instances to different regions, but definitely with an additional cost. Now, let's talk about some considerations you need to be aware of when you use this pattern. You need to choose whether you are going to keep your data locally in the region or you are going to replicate them with other nodes around the globe. And if you are going to stick with the first part, which is keeping the data stored in the local node, then your Geode pattern implementation is going to be pretty much like deployment stamp implementation. And I have done previously a video about the deployment stamp pattern. If you haven't seen it already, I highly recommend to give that a watch. Moving on to the Geode can work in tandem by using the Azure Cosmos DB. It will allow real-time communication or replication for the data with other nodes around the globe. One of the key things about the Geode pattern, it decouples everything and it's gonna end up having ultra highly distributed architecture. In addition to that, distributed deployments will have a greater number of secrets that you want to maintain and keep in each of these nodes separately, and you need to make sure that you have put the right security controls in each of them. Definitely the performance is going to be affected by the number of Geode nodes that you are going to deploy. So if you have thousands of Geode nodes around the globe, it's going to be definitely better than having 2 or 3 nodes deployed for your application. In addition to the app service plan that you are using as well. The higher the tier, the better the performance you are going to get. And again, moving again to the availability requirement for your data, whether your data has to stay in the same region or it has to be replicated to other nodes of your architecture. Moving on to the question of how you are going to orchestrate or distribute the traffic between different nodes. And we have already said before, you can use Azure Front Door to distribute or orchestrate the traffic between the users and the closest node to their location. Now let's see when you should use this pattern. When you want to have a solution that's going to be used by users around the globe, also if your solution is going to have an extreme availability or resiliency or reliability requirements. Now let's see when you shouldn't use this pattern in situations when there is no geographical distribution is required. Moving on to the situations where a legacy platform needs to be re-fortified. And finally, for simple architecture requirements where geo redundancy or geo distribution aren't required. Now we are coming to the end of this video. I hope now it's clear for you what the Geode pattern is about, how you implement it, how you use it to solve certain problems, what are the considerations you need to be aware of when you are using this pattern, and now finally we talked about when you should use it and when you shouldn't. I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hussein, and in this video we are going to talk about external configuration store pattern. This pattern comes under design and implementation and operational excellence categories of cloud design patterns. And it's about moving the configuration information out from the application deployment package. We are all aware that in Azure Functions app or Azure App Service, there is a local configuration settings that you can use to define different configuration items for your application. And what we are going to do in this pattern is to try to pull out this information from the local configuration settings from the Functions app or App Service to store them somewhere else. And there are a lot of benefits of doing this, and we are going to see them in more details in this video. Now let's dive into the example to help us understand this pattern better. Let's assume that our application deployment package is in Azure App Service, or Functions app, or even it could be an application deployed on a VM on Azure. Each of these components will have its own configuration settings, which is going to be a config file in the case of VM, and it's going to be the app configuration settings in case of the Functions app and App Service. There is already a built-in feature in Azure Portal that allows you to define different app settings configuration for your Functions app or App Service. And so far, so good, until we decide that we want to deploy multiple instances of the app service that we have. So all of these instances of the same application. And similarly for the Functions app, we might need to deploy different Functions app for different applications that still want to share some configuration information that's been already set up in one of the Functions app. And similarly for the VMs as well. And all of us know that the local configuration of the Functions app or an app service is very local to the running component. Like we cannot share certain configuration settings across multiple app services even if they are multiple instances of the same application. And this is one challenge. Also from the other side, if we have a totally different Functions app that still need to share some common configuration items, maybe like a database connection string or log analytics workspace that's going to send its logs to it. It's not possible at the moment to share a certain configuration item from one Functions app to be used across multiple Functions apps. So we are going to end up having multiple configuration items for each of these components in our architecture, which is going to make the life harder for us if we decided to change a certain configuration item in our system. So in this case, we will have to go through all of the config files or all of the config settings for all of these components to make sure that our changes has been changed correctly. Also, every time we change our configuration settings, we need to restart our Azure Functions app or app service in order for our changes to take place, which might cause a little bit of a downtime to our services, which might not be a good idea if you have a really high SLA that you need to maintain with your clients. So the challenges that we have now is that the local configuration in one Azure app service cannot share its settings across multiple app services of the same application. They might be multiple instances of the same application, and they might be different applications altogether, but still need to share or read the same configuration information. And more importantly, that we will need to restart our component every time we change the configuration settings. So these are the challenges that we have. Now let's see how can we use the external configuration store pattern to resolve these problems. Now let's clean this up, and what we are going to do in here is we are going to introduce a cloud-based storage, and we are going to move the local configuration settings from the app service and Functions app and from the VM and put them in the cloud-based storage. And the cloud-based storage could be a Key Vault or a blob storage or even a SQL database or any other cloud-based storage that you would like. But the idea is to moving the configuration settings out from the different components and put them in a highly available cloud-based storage, so all of the components can access it easily and directly. And by doing this, we have escaped away from having multiple configuration settings for each Azure component that we might have, because in complex architectures you might have hundreds or even thousands of Azure Functions app, and it's going to be a nightmare if you wanted to change a certain configuration settings across all of these Functions app at once. In addition to the need to restart the Functions app after you change the configuration settings. Also, it's very common to cache the configuration settings in a local cache to make the retriever even faster for different components that are trying to retrieve these configuration settings. It's going to be way more efficient and way more faster for these components to grab this data from a local cache. And you need to be aware of the cache expiration policy that you are going to define for your local cache. So in case you made some changes in the configuration settings in the cloud-based storage, it's going to take some time to be available in the local cache. Also, as an alternative, you can have a local cache for each of these Azure components, so you can cache the configuration settings that you are going to read from the cloud-based storage. But in this case, you are going to have a less control over the cache expiration policy and how often the cache is going to get refreshed from the source. And we have talked about the caching pattern in a previous video, so I'm going to put a link for this if you are interested to review it. Now let's have a look at this diagram that I've got from Microsoft documentation that explains it really well. So we are going to have a different sort of applications that reads from an external configuration store, which is going to be a cloud storage, SQL database, Key Vault, blob storage, any cloud storage you would like to use. And it's going to be even better if you are going to cache this configuration into a local store for faster retrieval. This is what the external configuration store pattern is about. Pulling out different application settings or configuration settings from the local application settings and store it externally to be shared across multiple applications. Now let's talk about some considerations you need to be aware of when you use this pattern. And the first thing you need to be aware of is the performance and availability of the cloud-based storage that you are going to use. We have already pulled out the application settings from the local configuration settings from different components and put them in this cloud-based storage. And you need to make sure it's highly available and can take many requests from different applications. And for any reason this cloud-based storage wasn't available, it might affect the availability of your applications if you are not using any cache. Also, you need to make sure that the cloud-based storage that you are going to use is flexible enough to support different schemas. We all know that most of the app config settings are key value pair, but some settings might require you to have a complex data types or even collection of data. In this case, you want to make sure that your cloud-based storage is flexible enough to support the different schemas that you might use in your application. Also, you need to be aware of that using an external configuration store won't solve all your problem at once, because you might use an XML config file that sits in a blob storage, and every time you want to get a certain configuration value, you need to parse the XML file in order to get the certain value. So yes, you might be using an external configuration store, but somehow you have added a lot of complexity to it, which is going to have a negative impact on the performance of the application or on the retrieval of these configuration settings. And you need to be aware of that. Also, you need to think of how are you going to control the scope of the configuration settings. So in some cases, you might have some configuration settings that you want to apply at the organization level, and some settings you want to apply at the application level, and some settings you want to apply at the local machine level. Also, it might need to prevent or allow certain applications from override the higher level settings. For example, you might define a certain configuration settings at the organization level, and you don't want any application to be able to override these settings. So you need to think of this as well. Also, you want to make sure that your external configuration store can deliver the data in the required format, whether it's a key value pair or type the data or collection of data. You want to avoid doing any transformation of the data while you are retrieving it from the external configuration store. Also, you need to consider how your configuration store will behave if settings contain errors, or they don't even exist at all. It might be a good idea to return a default settings and log this error to give you a chance to troubleshoot this later on. Also, you need to consider how are you going to handle the case sensitivity, upper and lower case for the key names. Also, how are you going to handle binary data? And how are you going to handle the null and empty values in your configuration store as well? Also, you need to consider how are you going to allow the access to the configuration store to just allow the valid users or application to be able to access your external configuration store. Also, you want to make sure that you have a clear separation between the roles required by different applications. Some applications might require to have a read-only access to the configuration store, and other applications might require to have a write access. So you might need to have a really clear separation on what permissions are required by different applications. And also it's going to be a good idea if you are going to store a sensitive information in your configuration store to encrypt this data. If it's a database username and password, it's definitely a good idea to encrypt this data in the external configuration store. And for the centrally stored configuration, we need to deal with it very carefully, and we have a more extensive testing for these kind of configurations. Because you might have one common configuration settings that's been used across multiple applications. And if you are going to change this setting, you want to make sure that all of these applications are going to behave well after you change this configuration. So part of your testing plan, you need to test all of the applications that might be using this certain configuration item that has been changed. This is to make sure that it won't affect any of the running applications. And as we said before, if you are going to cache your configuration settings, you want to make sure that you define a caching expiration policy, which is going to define how often you want your application to invalidate the data from the cache and grab a fresh information from the cloud-based storage. Now let's see when you should use this pattern. If you have a common configuration settings that are shared across multiple instances of the same application, or even shared across multiple different applications. Also, when you have a complex data types that are not supported by the standard configuration systems, like an image for example, or a complex data type, these kind of things are not supported by default in the standard configuration system. And if this is the case, the external configuration store pattern will be perfect for you. Also, if you want to define a default settings for all applications that are running in your organization, at the same time, you want to allow certain applications to override certain configuration settings that you have already defined at the organization level. And finally, and most importantly, it's going to make the administration task much easier. Imagine what would be the case if you want to update a certain configuration settings for hundreds or thousands of Azure Functions app. It's going to be way easier for you to change them once in an external configuration store than to go through all of the Functions app to try to change your settings one by one. Now we are coming to the end of this video. I hope now it's clear for you what the external configuration store pattern is about. How can we implement it? What are the different challenges we are trying to solve? And what are the different considerations we need to be aware of when we implement this pattern? I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about the Choreography Pattern. Choreography Pattern comes under messaging and performance efficiency categories of cloud design patterns. And we already know from previous videos that every time we see a messaging category, we should expect a message queue to be in the background. And we are going to see this in more details in this video. And the choreography pattern allows each system component to participate in the decision-making process about a certain business transaction. So in other words, there is no single point of control like the orchestrator pattern. And it's good to know other related patterns to the choreography pattern, like the ambassador pattern, queue-based load leveling pattern, and publisher-subscriber pattern. And I've done some videos about these three patterns. If you haven't seen them already, I recommend to give that a watch. Now, before we get started, let's see from where the choreography name comes from. Choreography in general is a practice or dance or an art that includes a sequence of movements using the human body. And the main thing I want you to know about the choreography is that there is no superstar or a single point of control on the stage. Every person on the stage is responsible for a sequence of movements and is accountable for the show's success. And this is the key difference if we are going to compare it with the orchestrator pattern, where we are going to have somebody that controls everything that happens on the stage. So if we are going to translate this to our terms, in the choreography pattern, every system component has a responsibility to do their own part of the business transaction. At the same time, each system component is accountable for the success of the whole business transaction. This is just to give you an idea from where the choreography name comes from and how we are trying to implement it in a system architecture. Now let's dive into the example to help us understand this pattern better. Let's say that we have implemented our system using a microservices architecture, and then we ended up having three main services for our system, like cache service, profile service, and fraud service. And in the perfect world, we want to design our services using the domain-driven design principles, or DDD, where we want to design each service to be accountable to a certain business domain and responsible to all business transactions coming under that business domain. So being said that, we want to design our cash service to be able to handle all cash transactions, like cash deposit or cash withdrawal. Also, we want to design our profile service to be able to handle all profile operations, like profile creation, deletion, or updates. And same for the fraud service, we want to design it to be able to handle all of the fraud operations, like fraud check or fraud reporting. So by implementing the domain-driven design in our microservices architecture, we are going to have a structured way for interacting with different services in our system. Since most business transactions would be able to be completed using just one service call, which is going to be efficient rather than having multiple service calls to achieve one business transaction. And by implementing the domain-driven design in our microservices architecture in our system, it's going to reduce the dependencies between our services, which we tend to call it coupling. And it's definitely a good idea to have a low coupling between your microservices in your system. So generally speaking, you need to keep a good balance between zero coupling and high coupling. Zero coupling means that each of your microservices sits by its own without any interaction with any other service in your system, which is not a good idea. Because if this is the case, then your services are going to be like islands. They are isolated, they don't communicate with each other, which doesn't make a good sense. While on the other end, the high coupling would increase the dependency between your services in your architecture, where every service in your system will need to communicate with other services in your system, which is going to make it complex and inefficient. So you need to keep a good balance between both, and there is no right or wrong here, it's more of an art, so to speak. So getting back to our example, by implementing domain-driven design is going to help most business transactions to be able to execute it using one service call. But we all know that this is not always the case. Every now and then you will have this really complex business transaction that needs to call multiple services to be able to execute the business transaction. And if you have designed your services correctly at the first place, you are going to be assured that you are going to have a really low coupling between your services. And as we just said, that the coupling between services is not a good idea, and our aim is to try to reduce it as much as possible. So what we can do in this case is to introduce the orchestrator pattern or service. So the orchestrator is going to receive the requests coming from the clients about the certain business transaction. Then the orchestrator service is going to orchestrate the work across all services that are involved in this business transaction. And by doing this, we would be able to remove the coupling we just introduced between our services, because the orchestrator here now will be running the show and orchestrate requests across all services that are involved in a certain business transaction. So we have removed the point-to-point communication between the microservices in our system, but there are some drawbacks we need to be aware of as well. We have increased the coupling, we have introduced another coupling between our microservices and the orchestrator service in our system. And in order for the orchestrator service to be able to execute a task with a sequence of steps, it will have to get a detailed domain knowledge about what's going on other services in our system. Also keep in mind that every now and then you might need to do some updates or changes to this business transaction, and you might need to add or update or delete a certain service from this business transaction. And every time you are going to do this, you will have to revisit your orchestrator service to make this change. So yes, definitely there are some added values from adding the orchestrator service, but it comes with its own cons that you need to be aware of. Now let's clean this up and see how can we use the choreography pattern to solve this problem. And what we are going to do is to introduce a message queue, which you might already expected as we have talked about the messaging category in the first slide. So the client is going to send their business transaction request to the message queue, and then from the other side, each service is going to pull the messages from the message queue to process it and puts the results back in the same message queue or in a different message queue in order to be processed by other services that are involved in the same business transaction. And by doing this, there is no single point of control in our architecture, and all services that are involved in a certain business transaction are just contributing to the work without having a single point of control to this solution. And I hear some of you already saying that having one message queue to handle the messages from all services, it might make it a little bit more complex. And I totally agree with you on that. That's why I'm going to show you another variation of this pattern, where we are going to have each message queue responsible for each service. So in here, the client is going to send their requests to a message queue, which is going to be the input for the cache service. And after the cache service completes its processing, it's going to put the output in another message queue, which is going to be the input for the profile service, and so on, until we finish the execution of all the services involved in the business transaction, and then we get back to the client with the result. So this is another variation of implementing the choreography pattern. Yes, it implements multiple queues, but it's more simpler than having all messages coming to the same message queue. And at the end of the day, it's your choice. You can choose whatever variation you are more comfortable with. Now let's talk about some considerations you need to be aware of when you use the choreography pattern. First of all, we are going to decentralize the orchestrator, so you might expect some issues while you are managing your workflow. Also, if a service fails to complete its part of a business transaction, sometimes it can be difficult to recover from that failure. One approach you can do is to make that service indicate failure by firing an event. So another services can subscribe to those failed events to take corrective actions, such as to undo the successful operation in a business transaction. Also, keep in mind that the failed service might also fail to fire an event for the failure, which is kind of inception thing, but it could happen. And in that case, you need to consider using other patterns like retry or timeout mechanisms to recognize that operation as a failure. And sometimes it's simple to implement a workflow when you want to process independent business operations in parallel, and you are absolutely fine to use a single message queue in this. However, the workflow can get a little bit more complicated when choreography needs to occur in a sequence. For example, service C can only start its operation only after service A and service B have completed their part of the operation successfully. And one approach you can have is to have multiple message queues to get messages in the required order, as we have talked about it already. Also keep in mind that the choreography pattern can be a challenge if the number of services grow rapidly. So you are going to end up having a high number of independent moving parts, which is going to make your solution complex. And also you need to keep in mind that the distributed tracing becomes difficult as well. Keep in mind that the orchestrator centrally manages the resiliency of a workflow, and it can become a single point of failure. And on the other hand, the choreography role is distributed between all services, and of course resiliency can become less robust. Finally, in choreography, each service is not only responsible for its part of the business operation, but it's accountable for the success of the whole workflow. And as we have already said before, each person on the stage is responsible to get the movements right, and also is accountable for the show success. So each service must retry transient, non-transient, and timeout failures so that the request terminates peacefully if needed. Also, the service must be diligent about communicating the success or failure of the operation to other services so they can act accordingly. Now let's see when you should use this pattern. When you want to have some flexibility adding, removing, or adding new services frequently. Also, if you are experiencing a performance bottleneck in the single orchestrator model. That's all I have for you for the choreography pattern. I hope you enjoyed this video. If you have any questions, please put it in the comments below, and thanks for watching. Hi everyone, my name is Hussein, and in this video we are going to talk about competing consumers pattern. Competing consumers pattern comes under messaging category of cloud design patterns. As we are going to see, this pattern is primarily focused on message queues or any messaging channel in general. And it's about enabling multiple concurrent consumers to process messages at the same time from the same messaging channel. And by having the ability to process multiple messages concurrently, it's going to optimize your throughput and improve your availability and scalability, and also balance the workload across multiple instances, as we are going to see in details in this video. Also, it's good to know the other related patterns to the competing consumers pattern, like queue-based load leveling pattern, and we have done a video about this in the past. I am going to put a link for this video if you are interested to review it. and also we have Compute Resource Consolidation Pattern. Now let's dive into the example to help us understand this pattern better. Let's say that we have a producer and a consumer, and we have decided to implement a synchronous communication between them. And from the previous patterns, we know that this is not ideal, because the performance of the producer is going to affect the performance of the consumer, and also the other way around. The availability of the consumer is going to affect the availability of the producer. So we call this a tightly coupled communication between the producer and the consumer, and it's gonna be ideal if we could break it down and decouple the communication between them. And from the previous videos, we have talked about introducing an Azure Service Bus queue. So the producer is going to publish its messages to the Azure Service Bus queue. And then from the other side, the consumer is going to pull messages from the message queue in order to process them. So by doing this, we have decoupled the communication between the producer and the consumer. So the availability of the consumer is not going to affect the producer anymore, and also the performance of the producer shouldn't affect the consumer as well. Now let's take it one step further. We all know that the number of messages in the message queue is not going to be the same at all times, because you might have an increased user activity or maybe an aggregated requests coming from different tenants if you have a SaaS platform, or even during the peak hours you might get 1,000 messages per second comparing to the off-peak hours while you are getting only few messages per second. Bottom line is the number of messages in the message queue is variable and unpredictable, and it doesn't make any sense to link something variable like the number of messages in the queue with a constant, like the consumer instance that's going to process all of these messages. And getting to handle all of these increased number of messages by just one single consumer instance, it doesn't make any sense, and actually it can make a bottleneck for your architecture. It will be even better if we can deploy a multiple consumer instances to be able to process messages from the same messaging channel at the same time. But it's very important to ensure that each message is going to be delivered and processed by just one consumer at any point of time. Also, we want to make sure that we distribute the workload evenly across the consumer instances, just to avoid having a single consumer instance to be the bottleneck for our solution or for our architecture. So this is exactly the challenge that this pattern is trying to solve. Now, after we have understood the problem, let's see how can we use the competing consumers pattern to solve this problem. So let's take off the consumer instance and we are going to put a consumer instance pool instead. Then we are able to deploy one consumer instance or even more based on the number of requests or number of messages we are receiving in the queue. Then each of these consumer instances is going to pull messages from the message queue to process them. And definitely we can scale up or down the number of consumer instances we have in the pool based on the number of requests or number of messages we have in our message queue. So what are the benefits for us? Now we have a load-leveled system that can handle a wide variation of the volume of requests that are being sent in the message queue, as we are going to be able to scale the number of consumer instances up and down based on the number of messages in the queue. Also, we have improved the reliability because there is no more direct communication between the producer and the consumer. So if the consumer is not available, it's not going to affect the producer from publish the messages to the message queue. Also, it doesn't require a complex coordination between the consumer instances or between the producer and the consumer. Also, it's scalable as we are able to scale up or down the number of consumer instances we have in our pool based on the number of requests or number of messages we are received in the queue. Also, it can improve the resiliency of your architecture. Let's say one of the consumer instances pulled a certain message to process it, and for some reason, it failed. So what's gonna happen is the message is gonna place the back again in the queue to be processed by other consumer instance. So it gives more chance for the message to be processed by multiple consumer instances in a case of failure. Maybe a certain consumer instance have a limited computing power or any kind of reason. That's exactly what the competing consumer pattern is about. Now let's talk about some considerations you need to be aware of when you use this pattern. And first of all, message ordering is not 100% guaranteed until you are using a FIFO queues. So the consumer is going to process messages, not particularly in the same order that the producer has published them to the message queue. Also, you want to design the consumer services for resiliency. In case of there is any error in the consumer service, you want to be able to detect it and restart it, and also placing the message again back in the message queue to allow it to be processed by another service instance that are not faulting. Also, you need to design your system to be able to detect poison messages. So what are the poison messages? It's a message that requires access to a certain resource that's not even available. So this particular message is gonna fail at all times, and if you are gonna place it back in the queue every time it failed, it's gonna be an infinite loop. And what you need to do, after a certain number of failures, you need to put this poison message in the poison queue to stop your consumer instances from processing this poison message anymore. Also, you need to think of how are you going to handle the results or response. In some scenarios, you might have only one-way communication between the producer and the consumer. But in other scenarios, the consumer might need to send some responses or results back to the producer. And if this is the case, you need to implement other patterns like Asynchronous Request Reply Pattern. And I'm going to put a link for it if you're interested to review it. As we have mentioned, we are able to scale the consumer instances up and down based on the number of requests or number of messages we received in the queue. And you should think of the scalability for your messaging system as well. Because sending millions of messages to one message queue is not gonna be an ideal situation. And what you can do instead is to partition the messaging system. So you are going to publish messages from a particular producer to a particular queue. So you are distributing the load across multiple queues instead of just one queue. And finally, you want to make sure that your messaging system is reliable for your architecture. Now let's see when you should use this pattern. When the workload for an application can be divided into tasks that can run asynchronously. Also, when the tasks are independent and can run in parallel, like your tasks are idempotent tasks, like they are not dependent on each other. Also, when the volume of work is highly variable and require a scalable solution. Also, when you want to have a high availability and high resiliency for your architecture. Now let's see when you shouldn't use this pattern, when it's not easy to separate the application workload into discrete tasks. Sometimes it's very hard to do it, like there is a high degree of dependency between tasks, and it's gonna be very hard for you to separate it. Also, when the tasks must be performed synchronously, like the application is gonna be waiting for the tasks to be completed before moving on to the next step. Also, when the tasks must be performed in a specific sequence. Now we are coming to the end of this video. I hope now it's clear for you what the competing consumer pattern is about. Why we should implement it, how we can implement it, what are the considerations we need to be aware of when we use this pattern. And also we talked about when we should use it and when we shouldn't. I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching. Hi everyone. My name is Hussein, and in this video we are going to talk about the cache-side pattern. Cache-side pattern comes under two categories of cloud design patterns: data management and performance efficiency. And the purpose of cache-side pattern is loading data on demand from the data store into the cache, while maintaining the consistency between the data stored in the cache and the data stored in the data store. There are many ways the application can use to load data into the cache. For example, loading static data at the application start is very common in some situations, like loading a list of countries or currencies at the application start is very common in many applications. But in this pattern, we are going to cover caching non-static data and loading it on demand when it's required from the data store and store it in the cache. Now let's go to the scenarios to understand the cache-side pattern better. Let's say that we have built our system based on serverless architecture, and our application layer could be anything like Azure App Service, or Functions app, or Logic apps, or even API management. This is the application layer of our system. And the data is stored in SQL database. And of course, there is kind of communication is going to be required between the application layer and the data layer. And this is sample of the data that's stored in the data store. And let's say we wanted to introduce cache into our system. And somehow we managed to cache the data for product ID 1. And we need to have some kind of communication between the cache instance and the application layer. So when the application layer gets a request to retrieve information about product ID 1, for example, the application layer is going to check for the value in the cache first. If it finds the value stored in the cache, it's going to retrieve it straight away. If it didn't find the value stored in the cache, then the application layer is going to get the value from the data store. This is how the caching works. Now let's say that we have updated the product name to XYZ in the data store. And still, we don't have any consistency built between the data in the data store and the data in the cache. So the data in the cache is still AA for the product name for product ID 1, while it's actually now become XYZ in the data store. So when the application layer gets a request to retrieve information about product ID 1, the application layer now will go check for the value in the cache, and it will find a value for product ID 1, and it will retrieve the old product name, even though it's been updated to something else. This is one of the challenges that this pattern is trying to solve. How we are gonna make sure that there is a consistency between the data in the data store and the data in the cache. And the other challenge is how and when we are going to load the data into the cache. Are we going to load it in the application start or at a certain event? And more importantly, what data to be cached? We want to cache the data that's going to have the most performance impact on our system. And these are the different challenges that the cache aside pattern is trying to solve. But before we get into that, I want to mention that you may already know that the API management comes with its internal caching. And if you are interested to see how it works and the different caching policies you can use for the API management, I'm going to put a link for this video so you can review it. Now let's talk about the different operations supported by different caching systems. We have a read-through operation, write-through operation, and write-behind operation. Let's go through them quickly to know what they are. For the read-through operation, the application is going to check the value in the cache. And if the application didn't find the value in the cache, then the application is going to get the value from the data store. And then the application is going to store the data in the cache. For the write-through operation, the application will update the value in the cache. At the same time, the application will update the value in the data store as well. There is additional latency you might expect in here because you are updating data in two places, in the data store and in the cache. For write-behind operation, the application is going to update the data in the cache and asynchronously is going to update the data in the data store using something like message queue. And eventually these values is going to be updated to the data store every minute, hour, or day based on your business requirements. Also, you can get these values updated to the data store in near real time by having an Azure function that gets triggered with every new message placed in the message queue. By this way, you can have the values updated to the data store in near real time. Also, I want you to be mindful of something using the write-behind operation. When the updated value gets stored in the cache and not yet updated in the data store, you want to make sure that you are using a multi-node cache cluster in this situation, because in an unlikely event, if one of the nodes get damaged and the data get lost, then you are assured that the updated value is stored in other cluster nodes. And what you want to avoid is have a single node cache cluster that might get lost or damaged. In this situation, the updated value is get lost from the cache and hasn't updated yet in the data store, and you don't want to be in this situation. These are the different operations supported in the commercial caching systems. Now let's see what we can do if we wanted to implement these mechanisms. Let's say that you want to implement this in your Azure Functions app or Azure App Service, and you can implement this by doing 3 simple steps. First step, you are going to check and see if the value is stored in the cache. If you didn't find the value stored in the cache, then you are going to grab it from the data store. And then finally, you are going to store this value in the cache for future use. Now let's see how the code looks like. And I got this template from Azure Online documentation, and I'm going to put a link for this page in the resources of this video. So this is the read function. And the first thing that you want to do is to check the cache or reading the value from the cache. And then if you get a cache miss, in this situation like you didn't find the value in the cache, then you are going to grab it from the data store. And then finally, you are going to store the value in the cache for future use. And what's going to happen in the update operation is really simple and straightforward as well. What you want to do is to go ahead and update the value in the data store. And then go ahead and delete the key from the cache or delete the value from the cache. This is to avoid your Functions app from reading the old value that's stored in the cache. Now you might be asking, how are we supposed to get the value again in the cache? And the answer is going to be in the next read operation. When we get a cache miss, because we have already deleted the value from the cache, then the application is going to grab the value from the data store and place it again in the cache. This is to make sure that the data stored in the cache is up to date and is consistent with the data stored in the data store. This is how you can use different caching operations in your application code. Now let's talk about some considerations you need to keep in mind while using the cache aside pattern. Time to live. All caching systems have this expiration policy that's going to invalidate the data and remove it from the cache if it hasn't been accessed for a certain amount of time. And you need to specify TTL value very carefully. Having TTL value too long, then there is a bigger chance that the value stored in the cache is going to be stale. And having TTL value too short, then your application might not have any chance to get the value from the cache, and then the cache will be useless in this situation. So you need to specify TTL value very carefully based on your situation. Evicting data. As you may already know, cache has a limited capacity compared to the data store, and you might run into situations where your cache instance run out of space, and you need to delete some data from the cache to free up some space for more important data to be cached. And there are a lot of evicting strategies you can apply, like first in, first out, last in, last out, removing data randomly from the cache, or least accessible data. You need to determine what's your evicting strategy you are gonna be for your application. Priming the cache. Remember when we said that the static data usually gets loaded into the cache at the application start. Now consider a situation when this static data gets deleted at the evicting data strategy you have specified for your application. And you don't want to restart your application in order to reload this static data into the cache again. What you can do instead is to implement the caching mechanism in the different read and write operation as we've already seen. This will give you a chance to reload the data, the static data into the cache if it got deleted in any evicting event or any memory dump event that might happen. Consistency. You might feel that by implementing cache aside pattern that you have achieved 100% consistency between the data stored in the data store and the data stored in the cache. But unfortunately, this is not the case. You might have an external process that updates the data in the data store, leaving the old data in the cache as it is. And to overcome this challenge, you need to consider implementing domain-driven design, or DDD, where you are going to have a certain service that's responsible to make updates to certain tables in the data store. And this service is going to be responsible for updating the cache as well, and making sure that the cache is up to date as the data store. Having DDD implementation will assure you 100% consistency between the data in the data store and the data in the cache. Then finally, you need to consider the deployment style for your cache, whether you are going to have a local cache or a single node cache instance or multi-node cache cluster. Now let's see when you should use this pattern. If you don't have a native read-through or write-through operations implemented already, you need to consider implement cache-side pattern yourself. Also, when the resource demand is unpredictable, you are not sure what data or which data is going to be required next, and you cannot load everything into the cache, then you need to implement cache-side pattern. And when you shouldn't use this pattern, when the dataset or cached dataset is static. As we said before, static data usually gets loaded into the cache at the application start. Also, you don't want to cache session state information in a web application hosted in a web farm. It's better to use a sticky session option in the Elastic Load Balancer or in your load balancer to achieve this. Now we are coming to the end of this video. I hope now it's clear for you what cache-side pattern is about, what are the different caching operations you can use, and how you can implement it yourself, what are the different considerations to keep in mind when using this pattern, and when you should use it, when you shouldn't. I hope you enjoyed this video. If you have any questions, please feel free to put it in the comments below. And thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about Sequential Convoy Pattern. Sequential Convoy Pattern comes under messaging category of cloud design patterns. And yes, your guess is correct, messaging category has a lot to do with message queues. And we are going to see this in more details in this video. And Sequential Convoy Pattern is about processing a set of related messages in a defined order, without blocking the processing of other groups of messages. And it's good to know other related patterns to the Sequential Convoy Pattern, like Priority Queue Pattern, and Publisher Subscriber Pattern, and Queue-based Load Leveling Pattern. And I've already done videos about these three patterns before. If you haven't already seen them, I recommend to give that a watch. Let's say that we have a group of users that's interacting with our application. Let's say it's an e-commerce application, like Amazon or eBay. And let's say that the user is going to perform a particular action, like create an online order with few items. And we all know that order creation process is not just a simple step, you can do it straight away. It actually involves a lot of steps that needs to be done in a particular order. So for example, order creation process will involve creating an order, then adding items to an order, then choosing the delivery type, then performing the payment, and then sending a confirmation to the user. So we have few steps here that needs to be done in sequence in order to create the order for the user. And having said that, it's going to be perfect for us if we are going to create a message queue and split all of these different steps in a separate message and place it in the message queue. And according to this, we will see that the first message you are going to place is the create an order message. Then it's going to be followed by adding the items that the user wants to purchase to this order. Then we are going to have the delivery fees calculation, whether it's internal or international delivery. Then we are going to perform the payment processing. And finally, we are going to send a confirmation to the end user that their order has been placed successfully. So all of these steps needs to be done in order, because it doesn't make sense to send a confirmation email to the end user telling them that their order has been placed successfully without checking if the warehouse has enough items that the user wants to add to their order. So these steps has to be done in order. And it's gonna be pretty easy and simple if we are going to use a FIFO queue, for example, because it guarantees that the messages are going to be processed in a certain sequence. Then we are going to have the consumer here at the other side of the queue, which is going to pull the messages from the message queue to execute them. When I say consumer here, I mean the backend services in our system that actually perform the actual action of creating an order or checking the delivery calculation or performing the payment, and it could be one or more background service or one or more consumer in this case. And so far everything is perfect. We have a group of messages that needs to be processed in a certain order, and we are able to achieve this by placing them in a FIFO queue, which is going to guarantee that the messages are going to be pulled or executed in a certain order. So what we have done so far is we have published the messages to the message queue in order to be processed in a particular order. And we will be able to achieve this by using a FIFO queues. First in, first out, which is kind of queues that guarantee the order of the execution of messages in the queue. So by using a FIFO queue, we are pretty sure that messages are going to be executed in sequence, which is pretty much what we need to achieve. However, in real life, things are not going to be as easy as simple as that. So in real life, we are going to have a group of messages related to multiple orders placed in the message queue at the same time. And we want to make sure that we are executing the related messages to a particular order in the same sequence. So for the green order, we want to make sure that we are processing the green messages in sequence, like creating an order first, then adding an items to the orders, then performing the delivery fees calculation and payment processing, and then sending a confirmation message to the client. All of these green messages has to be done in sequence, and they are unrelated to the purple or the blue orders. And this is exactly the challenge that the sequential convoy pattern is trying to solve. And now let's see how can we use the sequential convoy pattern to solve this challenge. And what we are going to do here is to have a categorization for our messages that we are placed in the queue. And I've already done it from the previous slides. So for a particular order, it's gonna have certain category. So the blue order messages is going to get assigned to a particular category and then placed in the message queue. Similarly, the purple order messages is going to get assigned to a particular category before being placed in the message queue, and same thing for the green order messages. And this categorization will allow us to have as many categories as we would like in the message queue. At the same time, we are sure that each category is going to be executed in the same order we have placed it in the queue. So from the consumer perspective or from the services perspective, we are going to have a blue service or a blue consumer that's going to process the blue order messages. And this is going to guarantee us that these blue order messages is going to be processed in sequence. Then we are going to have another consumer or another service that's going to process the purple order messages. And finally, we are going to have a green consumer, which is going to consume the green order messages to make sure that all of the green order messages are executed in the same order. It's as simple as that. Sequential convoy pattern is about assigning categories to messages before placing them in the message queue, and then from the other side you have a specific consumer that's going to execute each category of messages in a certain sequence. Now let's have a look at this diagram I have got from Microsoft documentation. So we are going to have a producer here, publishes messages to a message queue. And then in the message queue, messages are going to be split into 3 categories. Category A, Category B, and Category C. Each of these categories are going to be assigned to a particular consumer to ensure that the messages of Category A are going to be executed in the same order they are placed in the queue. Similarly for Category B messages and Category C messages. And if we look at this chart, it will make more sense. Now we have a group of messages that has been placed in the message queue in a certain order. However, the orange messages are related to each other and they have to be executed in a particular order. However, they are unrelated to the green order messages that can be placed under another category, which is in this case category 2. However, at the same time, we want to make sure that the green messages are executed in the same order. Similarly for the category 3 messages and category 4 message. This is exactly how you can use the sequential convoy pattern to solve this problem. Now let's talk about some considerations you need to be aware of when you use this pattern. First of all, the category or scale unit. You need to think of what property of the incoming messages that you will need to scale out based on it. In our case, it could be the order ID, for example. Then moving on to the throughput, you need to think of what's the target message throughput, and if it's too high, you might need to reconsider using the FIFO queue requirements. Then moving on to the service capability, you need to be aware of the capability of the message queue technology that you are using, whether it's able to process one message at a time or maybe multiple messages at a time. Then moving to the evolvability. You need to consider how easy or hard it's going to be for you to add a new category to your architecture. And finally, things can still go wrong, and the consumer can still receive the messages in the incorrect order, maybe because of a network latency or something. And what you can do from your side is to use sequence numbers in your messages, pretty much like we have used in our example already. And also it's gonna be good to have an end of sequence flag in your messages, so it's gonna indicate that this message is gonna end a certain sequence of messages. Now let's see when you should use this pattern. When you have messages that are arriving in order and must be processed in the same order. In addition to the arriving messages can be categorized in such a way that the category becomes a unit of scale for the system. Now let's see when you shouldn't use this pattern when you have an extremely high throughput scenarios, like millions of messages per second, as the FIFO queue requirement is going to limit the scaling that can be done by the system. Now we are coming to the end of this video. I hope now it's clear for you what the sequential convoy pattern is about, what kind of problems it's trying to solve, how we can use the sequential convoy pattern to solve certain problems. What are the different considerations we need to be aware of when we implement this pattern, and also when we should use it and when we shouldn't. I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching. Hi everyone, my name is Hassan, and in this video we are going to talk about compensating transaction pattern. Compensating transaction pattern comes under reliability category of cloud design patterns. And it's about undoing the work performed by a series of steps in an eventually consistent operation, if one or more steps has been failed. We all know that there are two models of consistency, strongly consistent model and eventually consistent model. And in the cloud environment, the eventually consistent model is more dominant to avoid having performance issues or a lot of latency. And we are going to see this in more details in this video. It's also good to know what are the other related patterns to the compensating transaction pattern, like Retry Pattern and Scheduler Agent Supervisor Pattern. Now let's dive into the example to help us understand this pattern better. Let's say that we are using Expedia website, which is kind of website that allows users to do flight booking, hotel room reservations, or even car rental at the same time, in the same operation or in the same workflow. So let's say we have a user that wants to book a seat on flight F1 from Seattle to London. And the same user then wants to book a seat on flight F2 from London to Paris. And then the user wants to book a seat on flight F3 from Paris to Seattle. And definitely the user is not going to be sleeping on the road during their trip. So they will need to make a hotel room reservation H1 in London and also to reserve a room at hotel H2 in Paris. All of these steps are part of the same operation, that all of them needs to be succeed or fail at once. And it's going to be a huge mistake if we decided to implement all of these steps as part of a strongly consistent transaction. Because if we look carefully here, we will see that there are a lot of integration points. So we have 3 flight tickets that we need to book, and most probably all of them are going to be with different airlines. Looking at the first flight, for example, from Seattle to London, it's most probably to be booked by American Airlines, which is going to suggest that the data is going to be stored in US region. However, for the second flight from London to Paris, it might get booked by European Airlines or something like that, and that suggests that the data is going to be stored in European data center. In addition to the separate hotel room reservations that we need to make. So there are a lot of integration points in this operation, and the data is scattered across multiple geographical regions. So it's going to be a huge mistake if we decided to put all of that in one strongly consistent transaction, because it's going to add a lot of latency and performance issues to our website or to the application itself. And what we can do instead is to perform each of these steps individually through an eventually consistent transaction. So we are going to have one task to book a seat on flight F1, then we have another task to book a seat on flight F2, then we will have a third task to book a seat on flight F3, then moving on to reserving a room at hotel H1, and then reserving a room at hotel H2. And all of these steps are independent of each other, so we might get a confirmation that we have successfully booked a seat on flight F1, while the booking process for a seat on flight F2 and F3 is still in progress. And once we get a confirmation on all of these steps involved in the operation, then we are going to mark the operation with the task as completed. So if all of these steps has been succeeded, we will not have any issue. But what if one of these steps had failed at a certain point? For example, what if we had successfully booked a seat on flight F1 and F2 and F3? And when we try to reserve a room at hotel H1, we didn't succeed. Then this step hasn't been completed, and definitely it won't send the execution to the next step to reserve a room at hotel H2, which make more sense. Now the question here is, what about the seats we have booked already for the other flights, F1 and F2 and F3? It won't be an easy rollback operation because booking a seat on flight actually involves a lot of steps needs to be done. Taxi calculation and payment collection and other stuff. So it won't be an easy rollback process to just making the seat vacant again for other users so they can book it. Now the question here is, when we are implementing an operation in an eventually consistent transaction, and we have got some successful tasks or steps and some failed tasks. The question here is, how are we going to revert the action of these successful tasks, or undo the work that's been performed by those successful tasks to return them back to the original state? This is exactly the challenge that the compensating transaction pattern is trying to solve. Now, after we have understand the problem, let's see how can we use our pattern to solve this problem. So as the original operation proceeds, the system needs to record information about each of these steps, and more importantly, how each of them can be undone to revert the system back to the original state. So if the operation failed at any point, then the system knows exactly what they need to do in order to bring the system back to the original state, and how they can cancel all of these successful steps that has been done through this operation. And having said that, we will find that we will have to implement a cancel seat on flight F1 logic, similarly for F2 and F3. And also we will need to implement a cancellation for room reservation at hotel H1 and H2. So what we have done here is we have implemented the original operation or tasks that we need to perform against our system. At the same time, we have implemented the revert or undo of that action. In case of any failure happen at any stage of the operation, we can revert it back to the original state without any problems. And based on that, we will see that the compensating logic could be implemented in the reverse order, so we can be reversing the actions that has been implemented in the original process. So back to our example, if we have successfully booked the seats on flights F1, F2 and F3 and then something wrong happened when we try to reserve a room at hotel H1, then we can successfully revert it back and go back to cancel seat on flight F3 and flight F2 and flight F1. So pretty much you are going to bring the system back to the original state, while we have implemented this workflow or this complex operation in an eventually consistent transaction. And this is exactly what the compensating transaction pattern is about. Now let's talk about some considerations you need to be aware of when you implement this pattern. First of all, it might not be easy to determine if a step has failed during an eventually consistent operation, because sometimes failure doesn't happen immediately and sometimes it can cause just a blocking in the operation. So it might be a good idea to implement some timeout mechanism in your operation. Then moving on to the compensation transactions are not easy to be generalized. Like you cannot have one magic function or class that gets called at every failure for every step in your workflow. It doesn't work that way. You will have to implement a very specific revert or rollback or cancellation logic for each step in your operation or your workflow. Then moving on to the idempotent commands. You should be implementing your steps as an idempotent commands. So in case of a failure, you could repeat these commands or these steps without any problems. Then moving on to the infrastructure, which must be resilient. You remember when I mentioned that the system is going to record the information about each step of the operation and also will know exactly how to revert or cancel it again. And there is no way you can achieve this without a resilient infrastructure. Also, the compensating transaction doesn't necessarily bring the system back to the original state at every time. It's just after cancelling or reverting the action that hasn't been completed through a certain workflow or a certain operation. And the order of steps in the compensating transaction doesn't necessarily to be in the same reverse order of the original transaction. It could be in any order. It wouldn't be an issue. And of course, placing timeouts for different steps in the eventually consistent operation is going to be a good idea, as well as implementing a retry mechanism in your operation or workflow as well. Now let's see when you should implement this pattern. Only for operations that must be undone if they fail. And having said that, you should be designing your system to avoid having the complexity to require you to implement compensating transactions. Because as we have seen already, it's not an easy or straightforward pattern to be implemented. Now we are coming to the end of this video. I hope now it's clear for you what the compensating transaction pattern is about, what kind of problems it tries to solve, and how we can use it to solve a certain problem or certain challenges. What are the considerations you need to be aware of when you implement this pattern, and also when you should use this pattern. I hope you enjoyed this video. If you have any question, please put it in the comments below. And thanks for watching.